Greetings! Welcome to the complete machine learning course with Python. Now, I'm sure you know by now that in the past decades, machine learning has really given us self-driving cars, speech recognition, Google Translate, effective web search, house price predictions, Netflix as well as Amazon recommendations, and guess what? There really only is just the tip of the iceberg of what's possible. In this course, you are going to learn how to build powerful machine learning model to solve any problems. You will go from a beginner, completely novice to extremely high level of competency, and your instructor will build each algorithm with you step by step. By the time you finish this course, you will have trained machine learning and deep learning algorithm to do the following: classify flowers, predict house prices, identify handwritings or digits, sentiment analysis, computer vision, identify staff that's most likely to leave prematurely, other things such as conduct medical diagnosis such as detecting cancerous cells, segment your customers, and identify those underserved profitable clients, and of course, much more. Welcome back everyone. In this lesson, what I will do is actually just to demonstrate to you how to create a new environment. The reason that we want to create a new environment is to make sure that whatever that we create in our applications for the purpose of, in our case, machine learning development, we want to have it self-contained, or the applications that we make use of, it's not tarnished or being confused by other applications installation. So in this case, we're going to create a brand new environment. So let me come to this screen here. So this is the landing screen. As soon as you start Anaconda Navigator, you will come to this screen here. And usually, once you have a few environments, the way for you to switch environment is just from this drop down. Notice that I have 3 environments here. I'm not going to make use of any of these. I'm going to create a brand new one. In order to create a brand new environment, what we do is that we come to the second tab here and just click on it. And you notice that it's highlighted in green. In order to create a new environment, we make use of this button down here called Create. Notice that once you toggle your mouse over it's lit up in green. So we'll click Create, and this new environment, I'm just going to call it ML Python, something meaningful for myself so that I can recall what it is. You can actually name it something that is relevant to you, that you can remember for the purpose of your project. So the next thing is to go and select the actual package. In our case, we're going to make use of the latest Python 3.7. Actually 3.8 is already out, but for the purpose of this, 3.7 is sufficient. And the other thing to take note of is the location where this environment is being created. And once you've actually taken note of all of that, all you have to do is just click Create. And usually this process takes somewhere between 3 to 5 minutes to complete. It's not too long. If you want to, feel free to actually go and freshen up, get a drink, or grab a cup of coffee or something or beverage that works for you. Once that's done, the progress bar will no longer show as it was installing. You would have noticed the progress bar was actually updating. And what you have here is that this portion tells you the actual environment that you are working on. And this portion here tells you a couple of things. By clicking on this drop down, it shows you the library that has been installed, what is installed, what is not installed. So these are the things that you can actually select. I'm going to leave it to you to play around with that as and when we do need to for some of the library that we need to make use of for the purpose of our lesson. I'll show you how to install those. Once the environment's been created, we come back to the home, and this is do take note the environment that we've selected. There are others, but in our case we do make use of this environment I created recently. And the next part is that I'm going to make use of Jupyter Lab and maybe Notebook as well. And to install these two, I can install within environments, but in this case, I'm just going to install it here just using just clicking on this install button. Don't worry about the so-called GUI. It's a little bit funny. I'm not too sure why it's always been like that for Anaconda, but doesn't actually do anything. There's not no damages here. It's just looks a little bit untidy, unfortunately. But once it's finished installed, it doesn't actually impact on the overall in terms of the actual running of the application itself. So that's pretty much it. Once you've installed, there will be a blue box with the word launch, and as you mouse over, the whole box is changed to into the color blue. So in this portion here, what we've covered in terms of this lesson is two things. One is how to select the environment, how to create the environment using the second tab here, and once basically click on create and put in the name, select the Python version and click the create button. And after that, I showed you how to install Jupyter Lab as well as Notebook. That's pretty much all that I want to cover. It is a short lesson just to actually show you how to actually get up and running really quickly for the purpose of learning and making use of Anaconda from here. So for that, I'm going to stop right here. Thank you once again for watching. Alright, let's get started with the first example, which is Hello World. As I mentioned previously, we need to first of all switch to the environment that we're working on, which is machine learning, Python 2019. So we're going to activate that to get started. Now the next thing is that I'm going to make use of Jupyter Lab for the purpose of this tutorial. So let's get started by clicking to launch. Give it a few minutes and it will actually switch to that screen for you. So let me just go back to my desktop, machine learning, and then under codes. Okay, so let's just close that off. I don't need that. Close without saying. Yep. Alright, so this is a clean slate. Normally this is what you will see unless this may be blank if you don't actually have any codes whatsoever or any files. So on this side of the screen, the launcher, you can launch either a notebook in Python 3 or console in Python 3 and a few other things as well. So in our case, what we want to do is actually select the Hello World file. Okay, this is a notebook file. So let's double click on that. Okay, and this is the purpose of this exercise really is to just get you comfortable with how Jupyter Notebook actually works. What we have here is that the first is actually a cell, which is also called markdown cell. There's a few types of cells here. There is the code cell, markdown, and raw. In this case, we want it markdown because it gives us the rich formatted text. The hash here basically means that this is header 1, double hash means header 2. So the font gets smaller as you go to header 2, header 3, and then this is just a normal text. But as you can see here, as I pressed Shift Return or just run the code cell using this, what you have here is that the details of the in the code cell get run, and you get this beautiful rich text format. Now I don't want to actually have all of these codes. I wanted to actually start with a blank slate. So what I can do is come to kernel. I can either restart kernel and restart clear all output, or alternatively I can actually select this clear all outputs, and all the outputs goes away. This is just really a very simple illustration of the actual notebook itself. What I'm going to do here is print the word text Hello World. You can see the syntax here is that the word print, and then you have an open bracket, close bracket, and then using the apostrophe as to encompass whatever that's within those apostrophe to actually be the text that's rendered onto the console. So let's run that, and what you have is the Hello World example. So I can actually come here, copy and paste across, and what I will do here now is that I'm going to change a little bit. instead of using single quote, I can use double quote, and just delete the single quote. Take a moment and have a think about it and ask yourself, what do you think will actually show? What would actually be illustrated? What would the outcome be different this time around? So let's run that. If you've guessed that they're exactly the same, you are absolutely correct. In Python, there are two ways to do the notation, either single quote or double quote, and both will actually render the output the same way. The other illustration I want to show you is that you can actually make use of Python, okay, as a calculator, okay, using Python as a calculator. All right, so the typical 1 plus 1, you get the answer 2. I would just want to show you something else here. Is the 1 plus 1, okay, and then 2 plus 2. Have a simple guess what could possibly be the output. Do you think that it will show 2 and 4? Well, this is where I want to do this to actually show you the output so that you can actually experiment with it, and from this exercise you learn how to interact with Python so that you can actually receive the output that you expect. So if I run this, strangely, interestingly, only 2 plus 2 is the outcome of 2 plus 2 is shown. 1 plus 1 is not shown. And I'm going to show you an example after I do the print part on how to actually print both of these examples out. So printing it out shows you the output of 1 plus 1. So let me add a cell. To add a cell, you can actually use plus to add a cell, or press the letter A. So let me just copy this across and repeat that again. Control C, Control V. Control C is to copy, Control V to paste. Now this is exactly the same as this, with the exception of the spacing. Alright, so now this is exactly the same. So if we run this, you'll notice that both the actual calculation or the computation output comes out. Alright, so that kind of like illustrates how you can make use of Python as a calculator. Coming back here, well, I've got a print text here onto the console, so let me just rename this. Print text to the console. Okay, so that's one way to do it. The other one is using Python. So that just makes the font looks a little bit nicer. I use tree hash so that these two are consistent. Right, I have this extra cell now. What do? I can actually use this clipper or scissors to delete that cell. Now, what I've shown you so far is not very useful, because basically all that I've done is that I tell Python to print hello world to the console and then print the actual computation onto the screen. And quite often this is fairly useless. It's not, you can't do much with it. Where the power of programming becomes really handy is to actually start storing the actual variable itself. So in this example here, we're storing 5 to the variable name or variable called var. And when we run this, there's no output, but if we want to see what kind of value is being stored into the variable var, we can run this and you can see the output is 5. Again, this is to illustrate what we had before. It only shows you the output, the latest computation. To see both, you can actually run these. Okay, you have to do print. And the other thing is that when you actually select these cells, you have the code. All right, and just another characteristics of Jupyter Notebook is that you notice that there are 2 solid blue bar here. That means that we have selected these cells. The top upper bar is the code. The second bar is actually the output console. If I find that there are 2, I want to actually minimize the output, I can actually click this blue bar to minimize that. Okay, to unpack it, I can actually click that again to see the full outcome of the actual output or console output. This is quite a neat way to actually clean up your console. Okay, the other thing is that I want to show you is that when you select this is a code cell. When you select this is actually a markdown, and this looks distinctively like a formula, mathematical formula. So if I double click, go in, you can see that you can actually write formula in the markdown state, and we'll render it really nicely. As you can see, the x is equal to 1/7. And this is quite a nice way for you to actually, well, especially when you're actually trying to illustrate some concepts. So there are a lot more functionality in it. For now, this is really what I want to illustrate to you. And the last computation I want to show you is that how do you do power? This is 4 to the power of 5. Probably a bit difficult to know, and I think probably 2 to the power of 3 is probably more useful. You're more likely to know the answer to that than 4 to the power of 5. So let's do 2 to the power of 3. The answer we know is 8. Let's run this, and sure enough, that is indeed the answer that we have in mind. But let's just check our understanding again. 2 to the power of 2, what you get should be 4, and sure enough, that is the answer that you get. Right, this is really a very quick rundown and illustration of the Python, the Jupyter Notebook, interface, how to work with it, and the fact that it comes in different format. Each code has the flexibility to be a code cell, to be a markdown cell, and also a raw cell. All that I've illustrated to you so far is code and markdown. And I've shown you that you can actually, when it is a code, you can use it as a calculator, perform computation, print screen, as well as storing the data into the variable in the RAM itself. And for now, that's really what I want to cover with you. I hope that you find it useful. And to close this off, all you have to do is when you actually have a blue or green dot here, it's telling you that you have data unsaved. To save this, you just press this diskette, and sure enough, that becomes a cross. The cross basically means that you already save all the contents that you've run in this cell. Right, having done that, I just want to sign off this lesson. Thank you for watching. Let me just close this off and see you in the next lesson. Hello everyone. In this lesson we're going to go into the so-called machine learning per se, but before we go into that in depth, we're going to start with again a little bit more of the familiarization of the Python environment, the Jupyter Notebook. It's really trying to get you to actually be comfortable with the environment. We're going to start with a project called Iris project, but before we start into the machine learning, dwell into it deeply, I just want to actually explain to you a couple of libraries that we do make use of quite extensively, as well as some of the data analysis that you need to do before going into full-on into the machine learning modeling itself. So let's just select this project, Iris project, and get started. I've titled this as Iris project. We're going to start with simple data exploration and analysis. A couple of things that we're doing, and also the so-called library that we make use of. NumPy is the first one, followed by Pandas as well as Seaborn. NumPy is the numerical Python. If I come here and say NumPy, there is actually a website dedicated to NumPy, and it shows you how to make use of API, what it is, and how to utilize it fully. So that's really the NumPy itself. The documentation is very extensive. It's really well supported. It is a mature. It is a very mature library, so I highly encourage you to actually make use of it and become familiar with it. It's really critical when it comes to be it data science, data analysis, analytics, or even machine learning. The second one is Pandas. Pandas, let me just pull that up. Pandas, not the actual animal itself. Pandas is really instrumental in propelling Python to become in the forefront of data analysis. So it is an open source. It is free for you to make use of. And again, this is really well supported. The documentation is great, and you can actually make use of it. Right now the version is still 0.25. It is still in the beta stage, not quite completely rolled out yet, but there's a lot of functionalities that is highly useful. Again, this is good for performing analysis on tabular structured data. So that's the Python data analysis library. And Seaborn is the third library that we're going to make use of. And let me just pull that up. Seaborn is short for Statistical Data Visualization. As you can see very quickly here, it renders really beautiful chart, and that's the reason why we are making use of it. It's just really handy for this purpose, rather than having to actually code it out. The last library is the Matplotlib. It's also a visualization library. Seaborn is a higher level library which actually make use of Matplotlib. Matplotlib has been around for quite some time. It is useful, it is highly flexible and extremely powerful. The only problem with that is whenever you have anything that's highly useful, highly functional, and highly customizationable, there are a lot of customization function there, it gets a bit complicated to learn. So let me just open this up. Matplotlib. So visualizations for plot, as you can see, this is under version 3.1.1. It's already mature, it's no longer at beta, it's full on for you to be able to use. And Seaborn is still 0.9. Okay, so looking at this, with the first few things that we're doing here is that we are importing NumPy, and we call it NP. Okay, rather than typing NumPy fully, we use the notation, shortened notation called NP, so that it's actually simplified substantially. And this is the custom notation. Pandas is denoted as PD, Seaborn as SNS. And we import matplotlib.pyplot, the sublibrary, as PLT. And there's a few codes here just setting the actual default and plotting the Matplotlib inline so that we can actually see it within the Jupyter Notebook itself. As before, we click play to run one cell. Okay, oops, we have one problem. Well, this is part of the plan to show you how to actually deal with these things as and when it comes out. So what it says is this, or the error is meant to be informative to a large extent. If you get stuck, you can either Google it to find out how to solve this problem, or if you can understand the English or what the error message is trying to inform you, then you probably can actually solve that yourself as well. Right, it says here, module not found error. Traceback, okay, the traceback basically tells you which line of code actually is giving you the trouble. So line 1 says import NumPy as NP. So basically it's saying that we don't have a module named NumPy. Now I'm going to show you two ways to solve this. I'm going to copy this single cell, come to Google and search. Right, well, I didn't really copy it, did I? So let me just copy, let me see, Control C. If that still doesn't work, I'm going to have to move to the next. Okay, there we go. Control C. Right, import error, no module name, NumPy. So you can actually, quite often for open source library, like mature library like Python, Pandas, and its well-used library, you have people posting questions in Stack Overflow. And this is where you can actually find answer to this. Basically, no module found. This is probably super basic, but I'm still learning. Thanks. Okay, it says here, check if there's a directory, blah, blah. And the next one is to begin with, you must download and install a newer version of NumPy. So very quickly, just by reading this, it's already informing you that you need to install it. If you don't have, you need to install it. Okay, you can either use this or this to install it. Okay, great. All right, so we roughly get an idea that, okay, we need to install this. Okay, but wait a second. These answers were given quite a wee while back. This is 2011. This is 2017, 2016. So is there a newer answer? Well, the new answer is probably exactly the same. Okay, there are some conda installed, and suddenly you realize, okay, my goodness, they are like, you know, for the same one question, there are so many solutions to it. And you have to get used to this. This is actually a common phenomenon. when you're actually dealing with open source library. You need to actually quickly sift through it. Don't get overwhelmed by it. I know you will in the beginning, but as you do more and more, you'll come to the realization that this is some of the barriers that you have to get through or get past to actually be comfortable with using this open source library. It is free after all. It does come at a cost. Okay, so we're stuck here. So what do we do? That's the first way to do it. Is I just illustrate to you Stack Overflow. If you don't have any way of solving that problem, then follow some of the suggestions by the community. Now those are all provided by the community. Right, let me just switch back to Anaconda Navigator. If you do recall, previously I did mention that you can actually tackle this when install it yourself. So I'm going to go over to environments and go over to not install and search for NumPy. Okay, here we go. I can find NumPy here. So what I need to do is select NumPy and then click apply. And this is actually telling you install package. All right, it will go through this blue bar solving, and this following package will be modified. So it's doing that exercise of locating it and downloading it, and now it's actually asking for confirmation to proceed to install. So I'm going to just click apply, and now it's installing. Okay, as you can see, it's actually installing NumPy. Right, let that run for a while. Okay, well, so far looks like it's okay, and NumPy is no longer showing as not installed. If I switch over to install, it is here. Okay, it is already installed as NumPy. So let's go back to this. Okay, so let's run this cell again one more time to see if we still encounter the same problem. All right. Okay, this time around it's drawing out a different error message. It seems like, well, this is one of those no news is good news. It didn't throw out the fact that can't find NumPy. So basically that means NumPy has already been installed. So that's why that line of code runs safely without any issue. So that's really the lesson that I want to actually cover today. I know that for this portion, I know that this is quite a long lesson already to actually illustrate to you how to actually deal with errors and how to install. This is a step-by-step process. I hope that you bear with me. Ideally, at some point, you will be able to go through this very quickly. For now, I'm going to leave you. I'm going to install pandas, Seaborn, and matplotlib. The background, when you come back, we should be able to run these cells without any issues at all. I'll leave that to you as an exercise to actually install pandas, Seaborn, and matplotlib. And I'll see you next time in the next lesson. Thank you for watching. Installing pandas. So right now we just come to not installed under the environments and type pandas. Okay, and you can see here pandas. That's really what we actually want to install, and I will close it off for now. That is already there. So if I type pandas again, you can see that it's been selected. What else? I want to install Seaborn. All right, select that, and then matplotlib is the third one. All right, so I've selected 3. So let's just apply. It's gonna search for pandas, Seaborn, as well as matplotlib. These are the 3 main ones that I wanted to install in one go rather than doing it 3 times. Okay, so we can see that matplotlib, pandas, and Seaborn. So let's just apply this and let it install these. All right, the installation is done. So let's come back to install. Okay, matplotlib's there. All right. Let's run this cell one more time and see if there's any errors being thrown up. Let's play this. This time all good. Finish running without any error being thrown out. So we are good to go. So let's have a look at a couple of things here. I'm printing the actual version so that you can actually see which version of Python I'm using, which version of NumPy I'm using, pandas, as well as the Seaborn. All right, so as you can see here, these all the versions are being printed out. Okay, right. Okay, the next thing we want to do is to actually read the data into our memory. Okay, the first thing is that we are looking at reading the file called iris.data. That's the source file that we have, the data file that we have under the directory called data. And I know beforehand that this is actually a CSV file, so you can see that we are using pandas. There is a sub module called read CSV. I'm using the read CSV to read the iris.data file into our memory. So let's show you a little bit. Within the data, I do have a couple of sample data for you to utilize in the purpose of our lesson, and this is the iris.data that I've already placed there. So let me just hide this so that we can actually have a bit more space. So let's run this cell, and basically I'm reading this and I'm storing it into the variable called df. df's short for data frame. Remember that I mentioned pandas is good and useful for tabular structure, Excel-like data format, or the actual formatting of the data. So let's have a look at the first few rows of the data by using this module called .head, also called method. So let's run this. And you can see that, okay, right, notice what I mentioned before, these are in tabular format, in columns and rows format. There is one problem though, is that this is actually a data, this row is actually a row of data, and what pandas, the read CSV method or thought it was the column header, and naturally we know that that's actually incorrect. So what we can do here is that we can add a little parameter here called comma, and then header is equal to -1. That basically says, look, this data, this raw data as it comes through, has no header at all, and just take the first row as data. So we're going to read that directly and then show the head. Okay, the head meaning the first 5 rows of data. So if we run that, and I get this interesting error message, right? It's fairly wrong. So what it actually is saying is value error. Again, how do you read error messages? Passing negative integer to header is invalid. For no header, use header is equal to none instead. Oh, very good. Okay, so what happened is that -1 used to be the method to actually say there's no header. The library has changed, so we'll switch it over to none. Run that again, no harm done. So now the column name is called 0, 1, 2, 3, 4 now. So that's useful for the purpose of for this exercise, and basically this shows us that yeah, we have the data and we are able to actually resolve the problem of not using the first row of data as our column header. Right, seeing that we don't actually have any column header, what we also want is to actually have something that inform us of what these columns and columns of data actually meant. Of course, they come with meaning. So I have actually pre-populated this cell here and calling it the variable column name, column underscore name, sepal length, sepal width, petal length, petal width, and also finally the class. Okay, so at this point, if you don't know what I'm talking about, then you probably have not come across the iris dataset. The iris dataset is a really great introductory dataset to help you get familiar with how to actually make use of Python for data analysis using pandas, interacting with the data, pulling it into memory for computation, for manipulation, to get a really good understanding. The iris dataset is fairly simple, it's not complicated. Although you might not know what I'm referring to when I keep saying the word iris, So let me come over here and type iris dataset using our good friend Google. You can actually go to this, the UCI machine learning repository. This is actually where I obtained the data from. Under Wikipedia, this iris flower dataset. There's also Kaggle. Both of these are fine for the purpose of what we're looking to do. Right, so iris flower dataset or Fisher's dataset is actually originally introduced by Ronald Fisher in 1936. Okay, so let's flip down here. Couple of things, just wanted to highlight to you. Iris setosa is this flower, versicolor is this, looks like this, and virginica looks like this. So there's actually 3 types of flowers in the actual data set itself. How we actually measure them or compare them or describe the flower itself is you saw before the actual petal length and width, and also the sepal length and width. Okay, so let's come back here. The only thing here is that it didn't really describe to you what is sepal, what is petal. So let's have a look at the iris flower set to see if it actually did provide the information. No, it does not. So we're going to come over the images and let's see if we can actually get a little bit more. Some kind soul has gone in there and described for us. Alright, here it is. Some kind soul has already shown us this is what a sepal looks like, this is what a petal looks like. Okay, great. This is really what I was looking for. So we have 4 measurements, the length width of both petal and sepal. And that's where we have, there are 4 columns here to describe that. And the last column, column number 4, is to describe the 3 types of iris flower set that we saw earlier. Okay, so let's run this to store these 5 column names. Now that I've stored this in this variable, I need to actually tell pandas to rename these columns to these name. Okay, so that's what I do. .df.columns. That's how I access the columns, the name itself, and replace it with code names. Run that, and as I run the header again, you can see that the column names now is much more meaningful. Sepal length, sepal width, and on it goes. Right, I'm going to stop this lesson here. Just a quick summary of what we've gone through here is that we have very quickly, in the beginning of it, I installed the pandas, seaborn, and matplotlib. I'll show you how to actually extract the actual version that we use, how to read data, raw CSV file into memory, how to look at the data, inspect it, and how to actually change the header, and also how to rename the actual column names and actually converting that or applying that to our data frame. Last but not least, we see for the first time the iris data set so that you actually get familiar with it, and also show you where you can actually access the data, either using Google, look up Wikipedia or Kaggle, or look out the image search within Google itself so that you can actually quickly visualize. Some kind soul has already visualized that for you. Of course, there are some videos as well, but for now, this is what we actually want to access for the purpose of this simple tutorial. With that, I'm going to stop right here. Thank you once again for watching. Welcome back. Previously, what we've done is import a couple of libraries for the purpose of data analysis, the NumPy, the pandas, the seaborn, as well as the matplotlib. We haven't fully utilized them yet. What we have done though is that we did make use of pandas to read the iris dataset into memory. So right now, having done all of that, renaming the columns, hey, we're gonna compare the same dataset which is provided for within seaborn itself. Now, bearing in mind that I mentioned before the NumPy, which is, let's come back here a little bit, the version that we use, NumPy is version 1, so it's no longer in beta. Both pandas as well as seaborn are still in beta, okay, so 0.25 and 0.9, so they can, the actual API code that we're using like read CSV can change, okay, which is why just now the -1 threw out an error in the last lesson. But those are things to keep in mind. But again, usually the error message provide sufficient information for you to actually make correction or deal with the problem. Alternatively, I did show you how to actually go to Google, just search the error message, and then usually some kind soul has already asked the question in Stack Overflow to how to deal with it. Right, this is to show you under Seaborn, which we use SNS to denote that you can actually load the dataset. There are some toy datasets that's already been preloaded in Seaborn for you to actually make use of. So let's run that. So load dataset, we are looking for the iris. I'm storing it into the variable called iris. And let's have a look at the first 5 rows of data. And sure enough, as you can see here, the data already is straight from Seaborn. Looks similar but also different at the same time. You notice that the column name is a bit different. Is the user underscore to connect the two terms, sepal length, instead of what we use is actually just space. And the other one is that when it comes to the class, we call it class, they call it species, and they've stripped off the iris dash and leave it setosa, I think, and then the other two. But inspecting the raw data, it looks roughly similar. I don't think they're exactly the same. There will be some variation, but that's okay. At least from the surface of it, you can tell that they are the same data, more or less to a large extent. That's useful for the purpose. And as you can see here, that once somebody has actually kindly loaded the data set, it makes it a lot easier for you to utilize it. So let's make use of dataframe.describe, which is a method that's provided for within the pandas itself. So if you look at this, it describes to you that the number count, or count basically tells you how many rows of data that you have, is 150. Also gives you some basic information. Sepal length is 5.8, the width is 3.05, petal length is 3.75, petal width is 1.19. So these are descriptive stats, okay? Hence, it's probably why it's called describe. You have the mean, you have STD, mean to standard deviation, you have the minimum, 25th percentile, 50th percentile, 75th percentile, and maximum. If you're not familiar with what I just said there, like mean, standard deviation, minimum, and or to maximum and the percentile, you probably want to refresh that. It's slightly beyond the scope. I assume that prerequisites or the foundation that you already have those basic foundational knowledge. Otherwise, this course will just going to be run too long. But don't be too concerned with that. Just Google it. Most of the information are already online somewhere that you can actually quickly refer to it just to refresh yourself. But it's useful to know that. Okay, so this is the DF from what we had before, which is this DF here. All right, so if we look at the iris, which is from the dataset is from Seaborn, let's have a look at the describe, and just to compare, are they vastly different? So looking at it broadly, they look almost the same. Okay, almost. I say almost because, yeah, they have 150 rows of data, but I do notice that the sepal width mean is a bit different. Okay, and this, yep, likewise the petal length is a bit different. The petal width is a bit different, and some of these are probably because of the treatment of the data. And once you actually go down the track of learning machine learning and data science, you will very, very quickly come to an appreciation that the data are usually very, very dirty. Yes, dirty. Okay, there are a lot of manipulation, cleaning, sorting, munging that you have to do to actually get it to a steady state whereby you can actually properly analyze it. But for now, I just wanted to highlight to you that despite the fact that they are two same data set, there are some variation. Okay, the DF, which is the data frame, which we install or imported from pandas itself, using pandas to import it, the raw data set is directly from the UCI machine learning repository, and iris, which is of course from Seaborn, and likewise Seaborn actually extract this directly from UCI as well, because they're all from the same source file, which is Robert, what's his name again? Robert Fisher. It's all from the same source, but somehow along the way something changed. So that's really to actually give you a rough idea and just an appreciation that these things can and do happen. So moving on from there, I just want to illustrate to you that you can actually use this method called info, and I'm going to print it to the screen. It gives you some really quick summary information, like how many rows of data, the type of data. You have the length and width are in the form of float, 64, and species is in the form of an object. Okay, so keep that in mind. You have four floats, 64, and one object. And I'm using slightly more advanced Panda features, which is grouping them. I'm saying the data frame called iris, group them by the column called species, and using a chain method size to tell me the number of observations for those respective species that is in the data itself. So looking at this, we have 3 different classes or 3 different species, Setosa, versicolor, and virginica. Each of them have a size of 50, the count of 50. Okay, so that's the one part to keep in mind. And you can see that they are balanced, okay, 50 each, which is useful for the purpose of our exercise. Okay, so for that, I hope that you found that useful. Just to do a quick summary, what have we done so far with the previous lessons? We extract the data directly from the UCI machine learning, already provided to you in the form of CSV in the data directory, and you read it using the pandas read CSV method. Okay, that one there. And this lesson we cover how to load the same toy dataset directly from Seaborn itself, and we make use of some basic descriptive statistics methodology or methods that's provided for in pandas in the form of describe, which allows you to actually have information very quickly in the ways of count, and the ways of mean, standard deviation, and the percentiles, plus minimum, maximum as well. Now, I just want to move on to cover visualization as well. Okay, this part is a little bit more on the complex side if you're not familiar with it, but just do bear with me. I just want to illustrate to you how you can actually very quickly conduct very beautiful plots using Seaborn for the purpose of analysis, and quite often a lot of these codes can be recycled. Right, remember that iris is our data set. There are a couple of parameters that we can provide. There are a couple of parameters that we can provide. So let's run this cell. Okay, this is actually performing a pair plot. Okay, straight away I'm getting an error. Okay, user warning, the size parameter has been renamed to height. Please update your code. Okay, so that gives me the information, and okay, to replace that, run that again, and wait for that cell to finish running. We no longer get an error message, and we get this beautiful chart. Alright, it kindly also provides us with some color coding. Blue is Setosa, this is orange, versicolor, and green is virginica. Okay, so very quickly you can see that this is in the form of a pair plot. Let me see if I can actually minimize this so that you can see the whole lot. Okay, not very ideal because it's a bit on the small side, but there are labels. The good thing is that you have your own notebook for you to draw in further. So I'm going to draw in a little bit now. This is, go back to 100%. This is sepal length, plotting against sepal length. So the diagonal is actually plotting against itself. When you're plotting against itself, what you see is actually the distribution. This is the sepal length distribution for setosa. You can see the setosa has the shortest sepal length. The vesica and virginica, these two is almost you can't distinguish them in terms of their this distribution. Although for setosa you can. Come to the width, yeah, barely perceptible difference there. Although you can see setosa is a bit slightly on the fatter side. Now these are distribution. Okay, what is distribution? Again, these are built upon statistical understanding and foundation for machine learning. You do need to actually refresh some of these basic principle and concepts in statistics. Basically, this distribution plot is kind of like plotting a histogram of all the possible data that's within the so-called variable itself. And in our case, if you look at petal length, you can see that setosa is much shorter in terms of distribution compared to the other two. The other two is almost, you can't tell. Okay, they're basically a lot of overlap. But for petal length of setosa, you can see that it's definitely shorter than the other two. Likewise with the petal width as well. So that's what the column or the diagonal actually tells you. Now if I plot sepal width against sepal length, this is the information that I have. It's a little bit hard to interpret, that's for sure. If I plot the, let's just say, petal length against petal width, I can see that the setosa is on its own here. There's some mixture, let me just blow it in. There's some mixture of the other two species here. There's actually intermix here, which is, you know, understandable. So this is a two-dimensional plot. This is a single-dimensional plot. So with this, I'm actually plotting the petal length to petal width here. And of course, that gives me a little bit more information as well in terms of how to distinguish them. This is really a very quick visualization to help you to actually get a preliminary understanding of the actual underlying data distribution, so that later on when you do machine learning, it gives you some foundations. For now, that's sufficient for what we actually want to do. So continue on, we can actually plot histogram as well. So let's just run this. And this is the histogram of the iris data for all four of the numerical data. So this is actually plotting, you can see the petal length, width, sepal length, and width. But this is actually combining all three species together, so you can't really tell which is which. It's just all the data is being plotted. Right, so the next one is actually plotting the violin plot. So we have 1, 2, 3, 4 violin plot, plotting the actual sepal length with sepal petal length width as well. And looking at these, it will inform you very similar to these pair plot here, except they're slightly different in the form of violin plot. You can see that the petal width for setosa and the petal length is definitely much shorter than the other two. If you drill into each of these, the white dot, that white dot there is the mean. And then you have the 25th percentile, the 75th percentile, that's the max, that's the min, and the actual distribution itself. There are a lot of information contained within the violin plot, so it pays to actually get comfortable with it as well. Next one is box plot. This is just really a quick illustration of the different types of plot that you can actually do with the Seaborn. So this is actually a box plot. Box plot basically looks kind of similar, or rather it actually displays similar information to the violin plot. So if I dig in a little bit and take this for example, the green line is the mean. Okay, this bigger box here, this is a lower quantile, upper quantile. Lower and upper is the 25th and 75th percentile. The solid bar here tells you the minimum and maximum, and this is for one of the species, which is Virginica, provided here. So again, box plot, this is grouped by species, so these are 3 different species here, so that's hopefully provide you with some useful information to actually judge. You can see that these 2 plots is actually sharing, in fact all 4 of them are actually sharing the same y-axis, 0 to 8. And you can see that this is actually squash, whereby this is distributed out. This is more squash, this is actually a little bit more widely distributed. So clearly the petal width is actually much shorter. As you read these charts, just be mindful that they are not quite in the same model order. In bar and plot, you can see the sepal length here and then petal length. For this, petal length is on top, followed by the sepal length. So they are in slightly different order, so just be mindful of that. Right, the next one that I want to show you is the scatter plot and also matrix. Similar information, probably not as useful as the pair plot. It does have its own place to display different information. Personally, I prefer the pair plot, partially because it's color coded. Of course, you need to provide the species to allow the hue to be generated as well. And finally, just as the pair plot again, but slightly different in that I want the diagonal to be a KDE plot, which happens to be the same as before. So that kind of like defeat the purpose. Well, you can actually change a different kind of plot as well to look up the actual API provided by Seaborn itself. So that's pretty much what I wanted to cover in this lesson in a very quick, fairly not really in-depth fashion. I'm mindful of that, but just the purpose of this is not so much to teach you visualization as the purpose of it is much more to illustrate to you what are the sum of the possibilities that can be done using Seaborn. You can see here that you can actually plot really beautiful chart, which is substantially harder to actually perform if you're using Excel. So you can perform pair plot using providing a couple of parameters. Likewise, you can actually perform histogram, violin plot, box plot, scatter, as well as the scatter matrix plot, and finally we'll come back to a pair plot again. So that's really a fairly quick whirlwind tour on what you can do with Seaborn. I hope you found it useful, and thank you once again for watching. Welcome back everyone. Let's just do a quick walkthrough in terms of how to open up our environment. Once you've started up the Anaconda Navigator, you will come to this landing page. The first thing to do is to change to the environment that you are using for your projects. Once that is up and running, I'm going to make use of Jupyter Lab instead of Notebook, and fire that away and give it a few seconds to actually start up. The reason that I prefer to use Jupyter Lab instead of or ahead of Notebook is because of this additional features that allows me to view what file is the files that I have in the directory. That's the first thing, the directory structure, and as well as what Notebook is actually running. So right now I don't really need this Iris project. I'm going to close that off, but you can notice that it is still running with that green dot there. So I come to this second tab, which tells me that I still have one kernel sessions running. So I just click the shutdown to shut it down and come back here. And coming back to this directory, I can select Boston Housing. Doesn't show the full name because of the real estate issue. And then I can Control B to hide that portion. It will still show up here as an icon, but it won't get in the way of what I am doing. Okay, so in this example, we're going to look at regression. Specifically, we're going to look at Boston housing price prediction. In terms of the dataset, you can come by here in Google and type Boston housing dataset. It is a fairly well-known and common dataset that is used for machine learning for instructional purpose. You can see here that you can read it in Medium, you can actually find it in Kaggle, and the list actually goes on a fair bit. It is also available as a dataset in scikit-learn as well. I'm making use of the Boston housing data price. It's not complicated. It's very good for instructional purpose, but it's also complex enough to make it an interesting data set to make use of. It can be really simple, and it can be as complicated as you like it to be, or complex as you like it to be, because of the underlying data behavior of the data. It is not linear. Some of the columns or the features are fairly complex, and there's a lot of in there to like about this data set itself. So coming back to the actual dashboard or the Jupyter Notebook itself, what we need is NumPy, pandas, and we also need sklearn, also called scikit-learn. This is a library from Python or within Python itself. It's created by the community. I won't go into the history of it. You can actually read about scikit-learn in a little bit more details. It's created by Jack and a few other collaborators. It's a really easy to use API and fantastic for machine learning. This is actually part of it that makes part of the one of the reasons why Python became such a popular machine learning language, or used for machine learning, simply because of how the ease of use with scikit-learn. So let's just run this, and we should expect an error message, as you can see on screen. Reason being, we haven't installed this. You feel free to skip this portion of the error diagnosis. I want to leave this here to help those who struggle with this when this kind of problem pops up. But if you are familiar with Python, you're familiar with how to deal with error message, then feel free to skip this portion. And so here, what you can see here is it says no module name scikit-learn. Hopefully you remember what we talked about in our earlier section that talks about how to deal with error. You have to read the error message, and the arrow here basically tells you, okay, this is the line that's giving you the problem, and what was the error? No module name sklearn. So we come back to our Anaconda Navigator, and you should be able to see this basic screen here. We then go over to the environment, and within the same environment, make sure that you have the correct environment selected, and go to not install and look for sklearn. Okay, it might not be in this spelling or in this name, so you have to look up the exact name, which is let me just show you, scikit. Okay, so here, scikit-learn. This is actually the exact and precise name of scikit-learn. sklearn is the library name, unfortunately, which makes it a little bit tricky when you do want to search for it, but nothing that Googling won't help you or won't solve it for you. So just apply by clicking the button here and let the installation run. It may take, again, a couple of minutes. I'm going to speed this portion of the video. Welcome back. Now that this complete the installation, we'll come back to our Jupyter Notebook, our lab, and run this cell again. And this time around, the error message disappeared altogether, and the number count has gone up to 2. And let's run this, and you can see the actual version of the various type of library that I'm using, and scikit-learn is 0.221.3. Having gotten that portion out of the way, the next step then is to actually load the data. You can of course load this via the scikit-learn dataset, as the library has a documentation here. What I have done instead is actually store the data for you in the actual data subfolder. So if you look at the subfolder, I've already loaded the data here. I've got that from the UCI website, and just really to make your life a bit easier, and so that you can actually just refer to it right away. So since I've downloaded it as a CSV, so we're gonna just basically read it in using pandas as a CSV. And we can look at the first 5 rows of data. As you can see here, is that what we have is 14 columns of data, and that's basically in this kind of format. And I've added a code here to help you to understand what each column means. Now, although right now I've given you the description, there's no heading label or column label. I have added this row of codes here, or line of codes here, and with the name of CRIM ZN following this order. And again, the documentation is from the UCI machine learning repository. And I just need to rename the columns, and that should actually allow us to have clean up prepared data for our exploratory data analysis. This is a fair bit of preparation work, but we'll need to do this so that we know the data that we are looking at or working with. Right now, what will be a good exercise for you to do is actually to read through each and every line or descriptors or description of the actual column label to help you to actually get a sense and a feel of what each column signify, or what kind of information is it supposed to provide. In machine learning, we call this feature. Feature really is a form of descriptors, or supposed to describe the actual data, underlying data itself. Some of it is useful, some of it is not. But here is all the data that we have for us to work with. And yeah, please do that before we go to the next lecture. Google around a little bit, either read it in Kaggle or some other blogs or mediums that people have actually written about it. Develop some intuitions before we move on to the next portion. I'll leave that with you as an exercise. Right, let's look at exploratory data analysis in this lesson. We have installed and downloaded the data with the Boston dataset. I've shown you how do you load it from the CSV. Part of the reason I use CSV instead of the scikit-learn toy dataset, although they're exactly the same, really, is that the CSV is probably more likely to be the more common way that you extract data from the real world. So hence the reason why I want to demonstrate that over the scikit-learn. In saying that, however, I have included some codes on how you can actually load it. It is in between. I don't have a lesson to cover that, although I provided some documentation that you can refer to in this notebook itself for you to actually explore around. Right, let's start with this. And we've already run the file, already run and loaded it onto the RAM. So I'm going to run the descript, which basically is a Python pandas libraries, very quick descriptor statistics for each of the features that we have. So you can see here for each of them we have basically input count, or rather a count of 506 rows of data, or 506 samples. We have the mean of each of the columns, the standard deviation, the minimum, the maximum, and then also each of the 25th, 50th, and 75th percentile. And that gives you a really broad overview of things. Now, what would you look for? Now, this is the part whereby you do need some statistics background, which I can't cover in this course itself. The couple of things that I do want to point you to, although we can't cover everything, is the first thing is you can look at the means. Not the most accurate way of telling where the middle part is. You can of course augment it using the median, which is also the 50th percentile. You can see the mean here is 3.61. The median, however, is 0.25. You can see they're vastly different. That tells you this data is not, or at least for this column of data, it's not very normal from the perspective of normal distribution. Again, I have to refer you to some statistics reference, and I need to trouble you to actually go and look it up yourself to understand what that actually means, because that will have a bearing in terms of how we actually create our model or machine learning model to replicate or emulate or to describe the underlying data. At the end of the day, machine learning is really about creating an algorithm that mimics the underlying data, the behavior of it. So we do need to actually have a fairly good understanding of the behavior of the underlying data or whatever that's generating the data to be able to create a reasonably useful machine learning algorithm. Okay, so looking through ZNs, likewise, mean is 11, but the median is 50%. And you can continue down. That's one of the data point that I look at, mean, median. That's one. The other one that I will look at is the standard deviation, and to look at it with reference to the mean itself and to see how large. You can see that the standard deviation for this is really large comparatively to the actual mean itself. In comparison, if I look at RM and also NOx, the difference isn't as, if you look at this, the standard deviation is almost 3 times, 2 to 3 times of the mean itself, compared to this, which is only a 1/5, 25%. And then if you look at the RM itself, it's even smaller. That tells you something. With the standard deviation substantially larger than the mean itself, it tells you that the data is really, really noisy. And if you look at the likes of RM, I think this is number of room. With the standard deviation being so small, it means that your data is not as scattered and it's fairly concentrated. It distributed around the mean itself. Then that's the data that I can have some confidence with, to play with. I know that when I actually say this is the mean, then most of the data will fall in this near the mean itself. Whereas when I look at this CRIM, hey, it can be all over the place. Later on, I'll show you some of the actual chart itself. That's where the visualization itself is really useful. So keep that in mind. I want to compare CRIM versus RM for later lessons or later part of this lesson, if not this next lesson, from the visualization perspective, so that you can actually see the vast difference between them. So those are the 2 things I look at. Mean, median, standard deviation. And the third thing, of course, you can look at, which also describe the similar behavior of it, is the minimum and maximum, the range of it. You can see here it ranges from 0.006 all the way to 88, which is a really large range, especially when you compare it to the mean itself. Zn likewise goes from 0 all the way to 100. Again, a massive range. And that, so far what I've done is that I am looking at the data to itself to a large extent. The second thing that we need to understand is the machine learning algorithm itself is, when we actually try to model something, we want the data to be relatively similar from columns to columns, or in machine learning lingo, we call it features to features to features. We would like their mean to be very similar, standard deviation to be similar. That's when the pre-processing will come in. And if you look at this, you can see that the mean across the board is vastly different. Text is really large at 408, and if you look at chars, it's substantially multitude, about 1,000 to 10,000 times smaller at 0.07 with the mean that way. You will have a problem, or the machine learning algorithm will have a problem, when the difference between the data is so large. And what will happen is that the movement in, for example, the text and from the actual step from 407 to 408 versus the movement in chars, which is 0.06 to 0.07, one step movement here is going to be massive in chars. And what would happen is that it will have an uneven behavior, and you're going to get unpredictable behavior when you actually don't actually pre-process or standardize the data. We will cover that a little later in our later lessons on pre-processing. That's the part whereby we standardize all of our data so that the mean are the same or the standard deviation are the same. Either way is to make sure that the movement of one doesn't suppress the other, or the movement of the other doesn't actually magnify the significance of it so much more than the other part. Right, that was a fairly long spiel, so let's dig into it a little bit. The matplotlib itself, we're going to run that. I believe, the Seaborn, we're using 0.9. Okay, so there's some basic configuration that I'm doing here. Let's see, the size has been renamed to height. So let's just do that. It's still running. Okay, how I can tell is just that asterisk there. So let's just let it run for a while. It might take a while. I believe it will take a while because it is a rather large file. I mean, we're trying to plot all 13, is it 13 features that we have? Let me just, yep, 13 features. We're trying to plot all 13. I think if you include the target variable, which is the median value, that's MEDV, then you are looking at a 14 by 14 matrix sort of chart, and as you can see here, it's massive and it's really large. I'm going to rerun this code here, having changed the height, but I'm going to skip it so that you don't actually have to watch this. Take 30 seconds, 45 seconds to run. In the meantime, let me just quickly run that. In the meantime, I will describe the actual column that we are drilling in. We're going to drill in these 4 columns, but I think what I did mention earlier is that we want to actually look at specifically CRIM versus RM. So I'm going to select that so that CRIM and then put a comma here, and also RM. I want to actually visualize that or drill in that a little bit so that we can actually compare the difference between the two in terms of our plot. That way we have a better understanding of what I just mentioned earlier. I mean, this is way too large for us to see, so I'm going to run this again. Here we're running all 14 columns. Here we actually selected 1, 2, 3, 4, 5. Yeah, 5. And then we're plotting only 5 to study. So CRIM here and RM here. Okay, if you look at CRIM, what you can see here is that most of the distribution is down this way. If you look at RM, which is over here, you notice that it starts from 0 and 50 is here, and then it carries on substantially. And where's our room? Okay, our room is here, so my apologies. Let's start here. This is actually plotting CRIM versus RM. So I just want to look at CRIM itself as well as the RM distribution itself. This doesn't tell me what, okay, 50 is here. This is actually the y-axis. So this is CRIM plotting against itself. 50 is here, 0 is here. So you can see bulk of the data is actually distributed between 0 and 10. Each of these blocks is by 10, by the way. So if you count 1, 2, 3, 4, 5 blocks here, this roughly from, we need to drill in a little bit more to see. You can't, but this is just a really rough sketch so that you can actually get a kind of like a helicopter view of the underlying data. You can see the bulk of the data is actually distributed between here to here, 0 to 10. And if we go to the room, this is, I believe RM, meaning average number of rooms per dwelling. You notice that bulk of it is actually, well, around 6 rooms, and they are really tightly banded between 4 to 8, 9 rooms. But you can see, as I mentioned before, in terms of the statistics, this is nicely distributed, really almost normal, but ultimately it's actually really compact. The data is really centered around the mean, whereas the CRIM itself has bulk of it distributed here, but there's a long tail. Although you can't see it, there's some here. And from our descriptive state, let me just hide this. Remember, we can hide this way. The maximum is 88. Although it doesn't show here, there's actually a bar here, so it actually has a really long tail for CRIM itself. Likewise with ZN, bulk of the data is distributed here, and it is actually a long tail on that side. Induced likewise is 60. This seems to be 2 mode here. Anox as well, it's not really normal. RM is what is normal. And when you actually start modeling the data using your machine learning algorithm, you do need to be mindful of this type of behavior, which is rather more challenging to model. And that's why we actually perform this preliminary EDA to really understand our underlying data, the actual behavior of it, and yeah, that's what the descriptive step is for, and as well as the visualization is for. Now I'm gonna do this once more. Let me just run those and just change this part. Because you can see I'm way too lazy to type. This time around, I'm gonna drill into another 4 columns or 4 features we want to look at. The median value is distributed fairly normal, but there's some long tail at the top end. And likewise, you can also see the other data, they are normal at all. Okay, the one thing I didn't really explain is that along the diagonal is the data plotting against itself. So this is really the distribution of the underlying data. So if you look at PT ratio, this plot with the histogram is just a plot against itself. It tells you the underlying data's behavior. The plot here is a plot of B against PT ratio. Okay, and you can see here it's weird. I don't even know how to describe it. And this is a flip of the same data, but the axis has been flipped. The axis, y-axis now is PT ratio. The x-axis is now B. So it's basically like these two are actually it's a 90-degree clockwise rotation of the data itself. So really, you can actually just look at one side of this. One side of it, which is this part, rather than looking at both. They basically, the other side is just a flip of it anyway. You can see that this is not linear, and it's really difficult to actually tell what's going on between median value as well as B. It just seems like there are 2 classes of data, and notice that there's some sort of truncation around the 400, and the data seems to be all chopped up here. It actually seems to be higher, but somehow the data collection seems to have clipped the actual data at a higher value. It doesn't seem like the data is actually very clean for this portion at all. Whereas this doesn't seem to have any relationship whatsoever. It's just random all over the place. So when I'm actually performing any machine learning modeling, if I want to actually select the features to describe my data, I want one that is actually give me some value, some information to describe the underlying data. So in our case, let me contextualize it a little bit. I'm trying to predict house price. And I want to select something that this can help me to predict the house price. Number of rooms, yep, I think that can actually help me in terms of providing some information about the house itself. Age of the house is also useful. Some things that's not really useful could be things such as, I'll just pick a random example. The month of the year, for example. Now, I know that's a really ridiculous example, but you can see what I mean. The month of the year is not going to have any impact on the house value itself. If you actually happen to have a data that have that kind of column, which is month of the year and also the median value of your house price, you're going to see the number all over the place. It's really random. There's no relationship, much like something like this. Maybe not exactly that shape in terms of form, but that feature, which is the month of the year, will be one of those features that you will drop. This is what we meant by feature selection. Okay, you're selecting the feature to actually describe the underlying data itself. And the other portion, if I give you another example in terms of if I want to select features to describe the face of a cat, for example, it seems like cats and dogs are still very popular on the internet. I would choose number of eyes, number of ears, those standard features to describe the actual animals itself. Selecting things such as the size of the lawn, or cat food, or those aren't gonna provide me with any information about the look of the cat or the dog. I hope that kind of like ridiculously obvious example will help you to understand that feature selection is important, and how you translate this into what we are looking at in terms of this Boston housing data set here is that it's not everything is so obvious, like the month of the year or the size of your lawn versus the feature or the looks of your cat or dogs. So what we have to rely on sometimes is statistics or visualization technique to inform us likewise. So when you actually see something like this chart here, which is the plot is, the scatter plot is all over the place, that is a sign that the underlying data has no relationship with what we are trying to predict, which is the median house value. Okay, I think that kind of like hammered that to death a little bit. I hope that has been useful for you. Yeah, so I hope that actually helps you to understand a little bit about feature selection. So what we really have covered in this session is exploratory data analysis. I provided a little bit about the descriptive statistics and the necessary part about plotting, visualizing, just really playing with your data, and sometimes selecting a smaller subset of the data, the columns of data, and drill in a little bit more to get a better intuition and understand your data and look at the relevance of the data, whether you want to include it in your machine learning algorithm later, for the development of the algorithm later. With that, I'm going to stop, and thank you once again for watching. Welcome back. In this previous section, we downloaded the Boston housing dataset, performed some exploratory data analysis, and just to actually get ourselves familiar with the features that has been provided. Just as a reminder, the features that's been provided, we'll start from the bottom here. The last column being the median house price. You have the lower status of the population of blacks, the pupil-teacher ratio, the property tax rate per 10,000, also the accessibility, or how close it is from the highway, the distance from the employment center, the age of the buildings, the number of rooms per dwelling, the nitric oxide concentration, Charles River dummy variable, whether it's actually tracked along it or not, the proportion of non-retail business, acres per town, the proportion of residential land zone for lots over 25,000, and finally the per capita crime rate by town. So it's necessary for us to actually be familiar with them. So the next thing that we are going to do is just get another sense, another scan through, a bit like X-ray, to understand the correlation between the actual individual features, meaning each column, how do they relate to each other, and more importantly, how does it actually relate to the so-called median price that we are trying to predict here. The beauty of it is that we, in pandas, has a function or method called core, basically that is correlation analysis. All you have to do is take the pandas data frame.core and runs it, and you will get a correlation matrix like this. This is probably one of the key features that you can use to get a really quick appreciation and understanding of how the underlying data or the features interact with each other. Alright, I made some modification because it was rather difficult to read before with 4 decimals, and it just looks too cluttered. So I've just set the, using the pandas option, set the float format to just 3 decimals. It makes it a bit easier to read now. Now, because we are trying to model a basic simple linear regression with only one variable on the median value, we would like to look at something that actually is high. So if you scan through this, this whole column here, and basically this is relating to each and every one of these. Obviously 2 itself is really high. It also has a high correlation with LSTAT. The other one is RM, and this is one way that you can select your features using RM and using LSTAT, which is actually directly opposite. So our LSTAT is basically the percentage of lower status of the population. So the greater the proportion, the more it has a direct correlation. They are inversely correlated. The other way to do this is to just plot a figure, a heat map using the Seaborn. So if we plot this out, this is what it looks like. What I've done is that I've set the figure a little bit larger so that we can actually visualize this easily, and the other one is just annotated so that you can actually see the value here. So here you can see the RM is fairly high. Of course, to itself is 100%, and it's really blue here for the lower stats. So looking through this, if you're going to do multiple linear regression, you probably will choose this. Anything that is larger than 0.5 is probably worthwhile looking at it. At least that's the first cut as you add. And there are quite a few that's negative correlated. So you have the text, distance from the road. This is the PT ratio, which is the parent-teacher ratio, and also the lower stats. And finally, this is the industry, the percentage that is allocated to non-retail. And also, not surprisingly, is inversely correlated to crime as well. So there's quite a few things that explain why house prices go down. There's only really one that explains why house prices goes up, which is the number of room. Okay, so that's really the end of what I want to show you here in terms of the correlation analysis and feature selection. I'd like to give you an opportunity to try this out because it's necessary for you to play around with this just to actually get yourself familiar with it. The first thing is that you might want to try the float to see what it looks like in terms of the presentation. This is really crucial, especially when you're presenting to management. If it's like this, they're gonna find it really difficult to understand, and most people have a phobia with numbers. So if you present it with this way, again, on a table of 14 by 14, it's just too much for people to take in one go. However, if you actually change the so-called to a heat map and present it this way, it's much more palatable to people. There are a couple of features that comes with the Seaborn heat map. I just want to show you heat map. And this is one of the beauty of the Jupyter Notebook is if you just press question, it brings up all of the doc string, okay, or the documentation. You can actually there are a few things that you can actually modify here. You can actually change the color setting to make it choose the so-called the color type that you like. Obviously, I've chosen to annotate. There are a few other things to actually beautify the whole chart that is suitable for your use. So I highly encourage you to actually play around with it. So I'm gonna pause the video, let you try typing the actual code in first of all, and play around with it, and better still, see if you can actually select, let's just say, these 4 columns: Crim, ZN, Indus, and cars. Rather than plotting such a big heat map, just plot these first 4 against MEDV, okay, and see what does the actual heat map looks like. So that will be your challenge. I encourage you to pause the video. I'll come back and wrap this up. Welcome back. Did you manage that? How did that work out? I really hope that it went well, and obviously you probably will encounter some problems. What I want to illustrate here is that when it comes to the pandas selection in terms of the columns, you do need to put a double quote. So I've selected Crim, ZN, Indus, CHAS, as well as MEDV. So let's just plot this heat map out, and this is what it looks like. So if we narrow down to just these 4 variables along with the medium value, this is what it looks like. So you have Crim, again, this is actually negatively inversely correlated. The number of non-retail also inversely correlated, which is not surprising because most people prefer to not live nearby a factory, okay, especially a non-retail factory. It could be steel plant, that gives out fume and then noise right throughout the night, or manufacturing plant that runs throughout the day in 24 hours. So people usually don't like that. So that's understandable. So that's really the end of this video. I hope you have found that really useful. In the next video, we will move into the actual linear regression itself using the variable that we've selected, and we're going to use scikit-learn to perform our modeling and also just to see what the actual looks like, okay, what the chart looks like, and also do some visualization as well. So I look forward to seeing you in the next video. Welcome back, everyone. In this video, we're going to go into correlation analysis as well as feature selection. What we did previously was just looking at the visualization as well as some of the actual underlying features in terms of the statistical distribution. So we did some exploratory data analysis to understand our data a little bit. We didn't go into depth for every single one of the features. We just demonstrated some of the ways that you will approach the actual problem itself so that you actually develop some intuition of the actual data. Now, just to extend it a little bit further, we will perform some correlation analysis just so that we understand the actual relationship between the variable itself along with the actual target variable. Now, the target, which is what our ultimate goals of wanting to predict, is the actual median value itself. Now I'm starting off with setting some options with the pandas. What I wanted to do is that just to tidy up the actual display. What we have earlier when we look at the table, which is this table here, you notice that we have 1, 2, 3, 4, 6 digits. It's a tad long, it's unnecessary because we don't really need that many digits. For the purpose of this exercise, what I actually have done is that keep it at float and just 2 decimal. So I'm setting the format and run the correlation. .corr stands for correlation analysis or correlation between the variable itself. So having run that, this is what you see for all the basically cross correlation amongst all of the variables itself. When the correlation is between itself, like cream with cream is 1, so if you pay close attention along the diagonal, they're all 1. And what we're really interested in is between the actual variable itself with the median value. And cream, as you can see, has the negative correlation, which makes sense because if you look under the actual feature description itself, you know that CRIM stands for criminal, okay, the criminal ratio or the criminal numbers. Of course, the higher the criminal value, the natural understanding or the intuition is that the price will drop, which makes sense, as you know, so they are inversely related to each other, and so on and so forth. Okay, so that's really what we are looking for. The positive. The strong positive is room number, the strongly negative is LSTAT. Let me just have a quick look what LSTAT stands for, which is percentage of lower status of the population. Again, this is from the perspective of income, and what you can see here is that the lower the income, it actually brings down the so-called or the so-called where there's a higher distribution of lower income social class, the median value is lower as well. So that is a form of a useful guide to help us to understand how each variable, how is it related or correlated with the target variable, which is the median value that we are looking at. This is one way to visualize it, is to look at the table itself. The alternative way is to plot what we call a heat map. So what we've done here is that we set the figure size to fairly large, 16 by 10, using the heat map features or the module that's built within the Seaborn, which is SNS, and plot the correlation coefficient and asking it to annotate, meaning have the actual correlation value plotted as well. And the last line of code here is really just show the actual chart itself or the figure itself. I'll let that run for a wee while, and there's a bit of cropping here. Let me just make it smaller, 14, or maybe just try 8. Okay, there's still some cropping, unfortunately. Probably have to reset that a little bit, but nevertheless, what I really wanted to show you is there is one here. So along the diagonal is one white here. Well, I guess you can say off-white here, or cream is basically 1. 1 is actually up here, and negative is black. So the really black one here is the low income percentage or proportion of lower income to the median value. So the higher the low social or low income class, the higher the percentage, the lower the median value is. And then the other end is the cream. Unfortunately, it's got cropped off. I will have to look at this to see how we can actually tidy this up a little bit. I'm not too sure why it actually is cropped off. Sometimes a bit of reset will help, but right now that's not ideal. I'll sort that out a little bit. And again, if you look at this, it's a little bit on the large side. It's a little bit sometimes we want to drill in a little bit. So what we can do is actually select a few of the features, so to actually drill in a little bit more. So in this case, what we've selected is 1, 2, 3, 4, 5, basically 4 variable that we wanted to look at in details versus the median value, and just repeat the exercise. It's doing the same here again. Unfortunately, there's a crop off. It's a bit unfortunate. Okay, let me continue and talk about feature selection a bit, because that's really the title, one of the 2 topics that we wanted to talk about. How do you actually select the features that you are interested in? Of course, you do look at the EDA itself, or exploratory data analysis, and look at the so-called underlying data, but we also want to look at the so-called correlation analysis, and just to get some intuition out of this. Looking at this, what you really want to do is select those variables which are strongly correlated, meaning either strong, just bearing in mind correlation coefficient range from -1 to +1. If it is 0, what you have is that they are independent of each other. That's really statistics speak for, they're not correlated, there's no relationship between each other at all. So there's no point adding that feature in to the so-called prediction using one variable which has no relationship with another. You're not going to get any value out of using that variable to predict, in our case, the median house value at all. So hence what we are interested in is something that is strongly positive or something that's strongly negative. So it has to be close to +1 and close to -1. So in this case, if we select the variable, how would we choose? -0.74 is good, -0.51, -0.47, 0.38 maybe. It really depends on how many variables we want to put in. If we want to actually, there are 2 ways to approach this. You can actually incrementally add them in, those strongly negative ones. So -0.74, you add that in, 0.7, you add that in. Okay, that's included. Now the next step then is I shall try 0.51, see if it doesn't make any difference in terms of our prediction. Okay, if it does, then I'll continue down to -0.48, -0.43, so on and so forth. Whereas some of them, which is like 0.25, or 0.18, I basically might not touch those or might not include those into the ultimate or the final analysis as a predictor at all. So this is using correlation coefficient as a way to select the features that that you like to attempt. This is just really a first cut to try it out to see if it actually has some sort of predictive value. And usually correlation coefficient is pretty good as a first cut to tell you, hey, look at me. It's basically the features crying out saying that I'm strongly positively or negatively correlated. It's asking you to pay attention to it so that you will include it for the predictor as the predictor, or the so-called independent variable, or the variable to predict your ultimate target value. And in our case, for this Boston housing, is really the median house value. Right, let me just quickly show you how I would tackle this problem. The lesson on correlation analysis as well as feature selection has already been covered. What I wanted to do here really is to just show you how to actually solve this problem. So you can feel free to skip this lesson. So first thing I'm going to do is just have a look at the version of matplotlib that I'm looking at, which is not going to play with me, plotlib. Yep, import it first, matplotlib as mpl. Okay, let's just have a look, mpl. So 3.1.1. Okay, so the reason I want to do that is that after we've closed off that portion, you can actually do a quick Google seaborn heat map crop. What I've discovered quickly reading through it, looks like some people are having the same issues here. And the reason really was that introduced in 3.1.1, which has been fixed in 3.1.2, still forthcoming, hasn't been rolled out. This is 9th of July, hasn't been rolled out yet when we actually install the Anaconda. And what we can do really is to actually perform what is called a const install matplotlib equal to 3.03. So I'm going to copy that line and come to this portion here in terms of the environment, and then open up a terminal. Right, so this actually comes to the command line. I know that some of you may not be comfortable with this, but all that we are doing here is just copy that line of code that is suggested by one of the developer, I believe it's developer, and then copy and paste it here and run that to see what will actually, or basically allow it to actually install or go down in terms of the matplotlib from 3.1 down to downgrading it. So let's just run that. Notice that it does say here it will be downgraded. Okay, it highlights to you from 3.1.1 to 3.0.3. Okay, so I might have to reset this, but what we will do is just come back here, re-import matplotlib, and rerun this. Yeah, okay. I'm gonna have to save this, shut this down, and close this off, and then reset. Come back here, refresh this, and relaunch the Jupyter Lab. Close that off. Reopen our project, which is Boston Housing, and rerun all of these code cells all the way to where we were just now. Okay, and have a look at what happened to our figure. Right, as you can see, what was suggested by the developers themselves did indeed solve the problem. There was a conflict between the matplotlib and the seaborn itself. As a result, this was cut off. And as you can see here, the problem has indeed been solved. Welcome back, everyone. In this session, we're going to look at linear regression, except we're going to make use of the scikit-learn library for this machine learning algorithm building exercise. This is just a simple linear regression with only one feature that we are making use of. Going forward in the future lesson, we will look at multiple regressions, but let's start with something more straightforward and simple for now, and get the so-called foundation set before we move on to something that's a little bit more complicated. Linear regression hopefully is something that you are fairly familiar with, or at least have had some exposure to it, either under your statistics background. If not, that is okay. We're going to make use of scikit-learn, and the beauty of scikit-learn is that it has made this whole process of building machine learning model extremely straightforward and simple, although there are some precautions that you do need to take, and some of it we will cover here, and others as it surfaces, I will highlight it and bring it to your attention. Let's start with, we'll still continue on with Boston housing price prediction. And the same data set is what we are working with right now. If you look at this, you have the first 5 rows of data. And you can see, as we mentioned before, there are 13 columns of features that we can use for the building of our machine learning model to predict the median house value. But to keep things simple for now, we're going to just make use of one feature, and that's the RM here, which is the room number. And what I'm going to use, because this is our so-called feature, it will be our independent variable, which is also our predictor here. Hence, I've only selected it for this purpose, and I'm converting it to values and reshaping it in such a way that the scikit-learn will require so that it can accept this value. So if I run that, and the value has been stored into X, and I also need to extract the median house value and store it as values as well in Y. So Y is what you will call a dependent variable. We're using the independent variable to predict our dependent variable. That is in statistic speech. If you are more in tune or more familiar with the machine learning speech, what we have would be the features, which is X, and the target variable, which is Y here. Right, so the next step then is that we need to make use of the scikit-learn linear regression model. You can import that from the linear model library, and the line or the code to import that will be from scikit-learn or sklearn.linear_model import linear regression. Running that, the next thing is that we need to actually instantiate the so-called machine learning model. Now, instantiating really is a fancy word for one example or one instance, really. That's what it meant. You can have multiple examples or multiple instances. In this case, we are creating one. And for this case, we are calling this model or machine learning model just with a very simple, straightforward term called model. Of course, you can have M1, M2, or M_LR, whichever way that you want to name it is perfectly fine. And of course, you can actually build your machine learning model or linear regression model using different types of features, standalone features, since it's a simple linear regression. Say, for example, you can have model 1, make use of RM, model 2, make use of H, model 3, make use of DIS. And step by on, on and on, and so forth it goes. So this is the instantiation process. Nothing happened really. We're just telling the scikit-learn library that we want a separate instance on its own. We haven't done anything with the actual underlying data. The next step then is to actually provide the machine learning model with the underlying data and how it relates to the target variable. Hence, what you have here is that model.fit x, y. So you need to provide with the target variable, which is y, and the so-called features, which is x. Then the step then is really just to run the fitting of the model. It gives you very straightforward feedback. And you can, of course, look at the model itself, look at the coefficient, which is beta, if you are familiar with the statistics modeling, and also the intercept, which is also called C in statistics. Now, if we plot it out in terms of the relationship between the X and Y, I'm making use of Seaborn. There's a regression plot here, and it's plotting the relationship between the X and the Y, and where X is the average number of rooms per dwelling, Y label is the median value, which is our target variable. So when you plot that out, this is just to visualize in terms of the relationship between the two. So let me see if I can minimize this a little bit so that we can see the whole thing on screen. Okay, looking at this, you have as the number of rooms increases, the median house value increases. By and large, it's fairly accurate, but you can also see that not all the data falls in line. There's a fair bit of noise here. Strangely, I think around 3 rooms here, the house value is roughly the same as the 7 room. So there are a fair few outliers. There are a few of these strange data, as you can see here, is that 5 room is at 500,000. It just seems like somebody, or rather the underlying data, is not exactly very clean. It seems to have a ceiling. Maybe the price is higher, but it's input with a maximum of 50,000. So, and you also have a strange situation whereby the room is almost 9 room and it's less than the value of the house with 3.2 rooms. So there's a few things that you can see the underlying data is a bit noisy. It's not exactly clean, or neither does the actual model completely explain the variability of the underlying data. Nevertheless, it's fairly, in general, it's around as the number of room increases. Without looking at the line, you can see that as the number of room increases per dwelling, generally the house price goes up. There are a few outliers or exceptions. So this plot here gave you the so-called underlying intuition. From visualization, we can tell that indeed there is actually a relationship. This is another way of plotting it. Size has been changed to height, so let me just update the code. Okay, so plotting it, again, you see the same plot. This is a distribution plot of the underlying data. This is the median value. This is the room number per dwelling. That essentially really is the actual so-called model building process. Right now we have built the model. We haven't done any predictions, so we also can't tell whether it's actually accurate or not. But what we can say is this. We have already provided the machine learning algorithm with the data, the link between the feature and also the target. With that, we've created a model that we can now utilize to make prediction. If it's 4-bedroom, what would this model predict in terms of the house value likely to be? That's really the actual underlying model itself. In the future lesson, we can look at other types of data. But for now, this is really the whole idea of the model building process. And of course, no one's going to build a machine learning model and don't make prediction with it. What we do next is to just do that very prediction, just so that we actually get a rough idea of how this complete process works. So in terms of the machine learning building process, using scikit-learn, what you do is that, first of all, of course, you choose a model. In this case, we've already chosen a model, which is the linear regression model. Then we, of course, obtain the data, which in this case, we are using the Boston housing data. Then the next thing then is to instantiate, which is this instantiation steps here, or this line of code. Really straightforward, as you can see. Then the fourth step is really fitting the actual data so that the model, the algorithm, can learn from the underlying pattern of the data. Having done all of that, then the last step then really is to make a prediction. So let's just say what we want to do is actually make a prediction. We can perform model. Let me just add a few space and zoom back in again. Predict. Okay, what we do need to do is actually input this as an array and provide a value. Let's just say we're looking at 5 rooms, but we do need to reshape this. That's because of the way that NumPy takes in the actual underlying value. Hence, we actually do need to add that line of code. Let me shrink this a little bit so that we can see the outcome or the output in terms of the predict and look at how it works relative to the underlying data. So running that, oops, we have an error. It says list data we're missing one close bracket. Run that. Embedded syntax, we have an extra, okay, extra close bracket. So with this 5-room, it is predicting that the house price to be around 10. So if you look at 5, the prediction is actually around 10. Now when you look at the actual original data, you can see here that for 5, there are values at 10, there are values at, well, not quite 20, about 22, and all the way to roughly 50. Of course, you can actually go to 7 and see what it's like. It's around 7 is, well, bulk of the data is around 30. So 29 is the actual predicted value. Of course, we do want our underlying model that we've built, the machine learning model that we've built, to be more accurate. Accurately depicts the actual underlying randomness or the patterns of the underlying data. And that's the whole point of keep feeding it with more data so that it learns the pattern with increasing accuracy. For now, this is really what I want to show you in terms of the machine learning building process, building your model until the prediction. Hope that's the complete so-called workflow of building a machine learning model. Indeed, from here on in, you're just going to hear me continuously repeat these steps again and again and again. And they're all the same. As long as you're using scikit-learn, they are built the same way. In one of the lecture, I will touch on a little bit of the API of the scikit-learn to help you understand a little bit further on how the way that it was designed it is designed in such a way to make the actual job of prediction of building a machine learning model extremely simple, so that you can actually focus on the task of understanding the data, modeling the data, and perform the prediction. So with that, I'm going to stop right here. Thank you once again for watching. I hope that has been useful, and I look forward to seeing you in the next lesson. Alright, in the previous lesson, we briefly discussed how you can build the linear regression model using scikit-learn. I just want to put it on the record that this whole idea is actually from one of the author of the scikit-learn API design, Jack Vanderplas. In his text, Python Data Science Handbook, Essential Tools for Working with Data, he lists down the 5 steps, which I would like to credit, and that's really the so-called step-by-step process that you can utilize, and which I've described to a large extent with some variation. Didn't follow exactly to the exact 5 steps, although I would encourage you to follow his 5 steps. That's actually it's from the author, so it's best that you follow his guide. And how do you find out a little bit more about the API design for machine learning for the scikit-learn library? These are the authors, and what you can do is just Google it, look for API design for machine learning, and also include the word scikit-learn. It will bring up, these are all the original author. You can of course download the PDF itself, and where you can actually see all the information of the actual authors who authored this journals, and it discussed a fair few things about the underlying design and the concepts that they undertook to actually build this scikit-learn library. And I highly encourage you to read it so that you can understand the actual general principles that they utilize to develop it. Okay, having said all that, the 5 steps that I want to actually reiterate based on Jack's books, also called Jacob, are these. First thing is choose a class of model by importing the appropriate estimator class from scikit-learn, which we did in our previous lesson. So let me just highlight this. Step 1, choose a model. Okay, this is the first step here, which is selecting a linear regression model. And then the step 2 is actually choose a model hyperparameter and also instantiating this class with desired values, which is this step here. Okay, we didn't actually provide any hyperparameter there, if you want to, within here, you can actually specify the actual hyperparameter itself. Then the next step is actually arrange the data into features, matrix, and target vectors following. So let me just delete this. This is actually originating from his text. I don't actually, or rather I did not include that discussion. So arrange the data into feature matrix and target vector. We did that prior to the whole exercise down here. So that's this portion here. So arrange the so-called target matrix. In this case, is actually, instead of a matrix, it's just a vector. And the dependent variable, which is the target variable, in this case, we're actually following the guideline, which is actually a vector itself. And step 4 is actually fitting the data by calling the fit method, which is actually this step here. And finally, the final step is actually for supervised learning, which we've been doing so far. It's actually use the predict method. In the future lessons, we will cover the unsupervised learning method, and which is where the portion on the predict here, which is right here, this step here. This is step 5 of the machine learning process. I want to highlight that, and with that in mind, I'm going to go and demonstrate with another example. In the previous lesson, what we did actually was making use of room. We can also look at another one, which is LSTAT. Notice that I tidy up the data first, and I'm using the same model. Probably not a good idea. So let me just rearrange it exactly to the steps that was described here. So I'll call this ML2. Okay, is equal to linear regression. So this is step 1, selecting a model. Well, step 1 is that I've chosen. Okay, let me just, okay, step 1. Okay, selecting a model. Okay, so that's selecting model. Step 2 is instantiating. So we are doing step 2 right here. Okay, so that's that portion there. And then step 3 is actually, so let me just make sure this is in capital letter, just for consistency's sake. Step 3 here is arranging the data into features matrix, which is our X, and target vector, which is our Y, and fitting the actual model itself. Fitting the model itself is actually step 4. And finally is the predict method, which is, this is plotting. We don't have the prediction here. Let me just do it in the next cell. Just run this first. Okay, so we have this example. So we're going to run a predict, which is ML2 predict, and we have array, and let's just put in the value of 15, and then we need to reshape this because we only have one data, and run this. And what is the error? ML2 is not defined. I use ML_2, so let's keep that consistent. List object. Why do I keep missing that close bracket? And it gives me another error. It's not fitted yet. We have run the fit. Oh, ML model ML2. Let's just keep that consistent. So we ML2, so we need to fit that before we run that. Okay, this is step 5, which is the actual prediction itself. So we say 15, predict the actual medium hash value to be 20,000. So that's 1,000, 20,000. So this is really the step-by-step process that's actually highlighted in Jack's book. And it's actually a pretty good 5 steps to follow, and it really helps you to, in terms of framework, to understand and to easy to remember really. So let me just clean this up a little bit with the actual plotting there. I'll tell you what, to make it cleaner for you to visualize, I'm gonna put this here so that you have the 5-step process, including the prediction, and then the plotting. That way you can actually see step 1, step 2, step 3, step 4, step 5. Okay, and the actual visualization. And this is really a joint plot. It will do the exact same thing. The size has been changed to height. This is just another way of displaying the data, really. There's nothing especially special about that. Okay, so this is the lesson that I really want to cover in terms of the 5 steps to help you in terms of when you're actually building a machine learning model going forward. This is the framework that you can actually make use of. And going forward, we're going to cover something that's a little bit different, which is robust regression, partially to address the so-called noisiness of our data and the non-randomness, and there are a lot of outliers, which violates the linear regression underlying assumptions. Yeah, we'll cover that in the next lessons. I hope you found this useful. Thank you so much. Alright, let's look into robust regression this time around. Let me just illustrate the purpose of looking at robust regression. If you quite simply do a simple search with regards to linear regression and its assumptions, you will notice that a lot of the empirical data, empirical means real-world data, have a tendency to actually violate the assumptions that come with linear regression. And notwithstanding, one of the most basic one is the susceptibility of linear regression to outliers. I'm not gonna, again, it's probably not the best place to actually go through all of the assumptions. I just want to highlight one way to deal with the issue of outliers, the effect that it has on the actual slope that you estimated. The slope here, really, I'm referring to beta, how steep it is. I've provided a link here for illustration purpose. This is really a simple applet, and the beauty of this is that you just need to draw 2 points, and what it can do is actually it can create number 1, a mean line, and then it can actually plot what is called a line of least squares, meaning the best fit line. I can show the residuals. I'll explain that in future lesson. Just as right now, all you can see is, because of it's only two points, you see a perfect straight line. If I add a dot here, what it will do is that it will try to find the least distance between the line and the dots. So it will continue doing that as you add more and more points. Okay, and it will continue to do so, as you can see. Alright, so this is the whole idea of line of least squares. The purpose of line of least squares, or it is so-called least squares, is basically it tries to calculate the line distance between the line and all the dots and try to minimize the distance. It's actually a comparison between the actual estimated line as well as the actual dots, points, and then bracket square. Alright, so that's really the function, and what we're trying to do here, or rather the algorithm try to do here, is actually just to minimize the distance. So the whole point of using squares is because it is to actually avoid the issue of directional, that actually you ended up pushing it one way or the other, or summing it up. I'm not really explaining that clearly. The whole purpose of squaring it is to remove the sign. Okay, what we're interested in is to minimize the value rather than the direction. Okay, whether it's be it positive or negative. All right. Okay, hopefully that actually helps a little bit for you. Let me just finish it off with 50 points. What you have now is that it's fairly positive correlated. Well, it is actually quite highly positively correlated at 0.9486. It's almost a perfect one. Now what you can see here is that there's hardly any outliers. The lines behave perfectly. There's nothing, and this is really in a way an ideal distribution for you to model or plot a line of least squares or linear regression, because to a large extent this actually fit into the assumptions of linear regression. Let me just illustrate to you what happened when you actually have a couple outliers. And this is the same thing that happens with the mean issue with mean. A mean have a tendency to be affected greatly by outliers. So let me just show you this. Let me add one point. Okay, let me just delete that point. Notice the line coefficient is 9486. Let me add that. Notice that it fall substantially. Add one more. These extreme lines is actually tilting it substantially. And if I add some more here, okay, notice that it actually tilts it. Now for greater effect, let me just remove these dots again altogether. Okay, there's a bug in the system. Let me add, let's just say 5 points here and see what happens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Those 10 points literally tilt the whole line the opposite direction. Those outliers on their own essentially basically shift the whole line of least squares to a point whereby it's absolutely useless now. Most of the data, although it's actually here, if I continue, it will tilt it a little bit, okay, but the outliers have a larger effect on the data than the actual plot itself, as you can see. It was starting to tilt back a little bit, but if I add 2 points, it essentially nullifies most of the 20-30 points that I just added. Well, I hope that kind of illustrate the rationale of why we want to look at robust regression, because linear regression have a tendency to be affected substantially by outliers, and in the real world you do see a lot of outliers which have a major impact on the accuracy of your machine learning algorithm prediction. At the end, but that's really what we're interested in, is the accuracy of your machine learning models. You want it to be able to, well, generalize it to a such extent whereby it is accurate most of the time for the core of your data. Okay, you don't want it to model everything. If it's perfectly modeling everything, then you're likely to have the issue of overfitting. Again, we start with look at our raw data, and what we're looking at here is the random sample consensus, also called RANSAC algorithm. This is a form of or a type of robust regression. The algorithm works like this, okay, but I just want to show you the iteration, or rather the process first of all, just to help you to get an intuition of how it works. The idea here is to highlight to you what the outliers are, so that it actually highlight the outliers and drop those when it actually perform the so-called estimation in building the machine learning algorithm. As before, we have to tidy up our x and y, our feature as well as our target value, import the algorithm, instantiate it. Okay, so instantiation, let me just highlight to you, just help you recall here the 5 steps. Okay, select the model, instantiate, arrange the data, model fitting, and finally perform the prediction. Okay, so we're now into fitting. Okay, it's fitted, and I need to create what is called a mask. Right, this mask is already done by the machine learning model itself, or the algorithm itself. After I fit, the algorithm actually create a method or subclass, and this is really an attribute. It's actually stored in this portion here called the inner mask. The inner mask are those data that is inlier, and the outlier are, well, the outlier mask is the outlier. Now this is logical NOT, meaning is the opposite of inlier. So anything that's not the inlier, then it is outlier. So that's really creating these 2 masks for us to visualize it. This is for the purpose of plotting it out. Now I'll create this mp.arrange 3 to 10. Now essentially this is basically creating 3, 4, 5, 6, 7, 8, 9. So this is for me to plot the points to plot basically to ask the algorithm to create dots, okay, and to make predictions at point 3, point 4, these are x, point 5, point 6, point 7, 8, and 9. And this is this portion here asking it to perform prediction. Line x is this value here. I'm storing this into line x. Why do I actually repeat this line? This is to actually help people who will struggle with understanding the line of code there. I had people asking me that many times before, so I thought I'll just print it out so that you can see what the value. Essentially, this is start at 3, finish at 10, step 1. Stop at 10 meaning it doesn't, just bear in mind that with a range, it doesn't actually do the last value. It will stop at what the value before, which is 10 minus 1, which is 9. Okay, so in terms of predict, to get our y value, okay, based on the ransack algorithm, so we provide line x, which is these values here, and reshape it in such a way that the ransack can understand. You run that. Okay, so that means we now have the x value, we have the y value. Let me just stop for a moment and explain this. We've done the machine learning model building process. Okay, we have gone through the 5 steps, okay, including the prediction step. The only problem with having completed the 5 steps is that you have no idea what we've done because everything is written in the code. It is useful if you understood what has already transpired. You can actually deploy it into real-world use. But for a person who's learning from an instructional sense, you would like to see, okay, what actually did happen? You want to open up the mystery box or the magic box and just tinker with it. Since you can't open it up, what we can do is that we can look at the output. Okay, from the output, we can actually see, oh, okay, so if there's this input, this is the behavior that we can see that comes out at the other end. So through the input and output relationship, we get an idea and develop an understanding of the behavior of the algorithm. And that's really the approach that we are taking here. So that's this few line of code. Don't worry about setting the style, plotting the figure size. We want to actually plot the scatter plot, okay, of the inlier, and we are also plotting the outlier. With the inlier, it is blue, the color is blue. With the outlier, the color is brown. And we actually plot the line itself, which is the predicted value, x and y. We need to provide the x value and x value, and this is the red. So the fitted line is in the color of red, the inlier color is in blue, and the outlier color is in brown. Okay, let's plot that out and visualize this. So you can see the red color is the, as I mentioned before, is the fitted line or best fit line, and the blue color is the inliers, and the brown ones are the outliers. Essentially, what the algorithm has done is that it performed a few things. During the fitting process, it calculates and identify the outliers. It just dropped those all together. That's the first thing. The second thing it did is that it performed the actual fitting in terms of narrow it down what the inliers are. So when the machine learning algorithm is built and the model was built, and when we actually perform the prediction, it just makes use of the value of the inliers, which of course you've created a model for it to perform the actual prediction itself. So it basically disallowed any of the outliers to have any impact whatsoever in the bad line that we have here. These are just inspecting the coefficient. It doesn't mean much really. It does actually susceptible to actually changes. So what we did do earlier, really, this is on the room number, okay, and also median value. We'll just repeat the same exercise with LSTAT, low income or percentage of low income, the statistics of it. Run the exact same thing and this is what you have in terms of the line of the RANSAC line, the regularized regression, okay, or robust regression, sorry, I should say. And what you can see here is that it discards all of these. Otherwise, your line would have been different. It would have been higher at this end as a result of the effect of the outliers. And this way, although you can't really see it here, and by the way, RANSAC might not be the best machine learning algorithm for this purpose. From my perspective, the ideal way when you actually perform machine learning modeling is that it is a straight line, okay? But sometimes your underlying data generating behavior is not a straight line. And for this, it may be a downward sloping line like this. So meaning it's not a straight line at all. It's actually a curved line here. It's basically hyperbolic. So with that, you can use this if you prefer not to use x to the power 2 or x to the power minus 2 algorithm, type of algorithm. You can actually ignore those, set those aside, and just use basically a linear line to fit your model. Because the chances of using higher power machine learning algorithm is that it is more likely to create errors and have a higher tendency of errors. But sometimes if you know and understand your data really well, then then make use of those. By and large, most of the time we use linear model to solve our problem. Okay, so this is really the lesson. I know there's quite a fair bit to actually take in. The whole idea here is to actually illustrate to you what to do when you actually have a violation of the linear regression assumptions. So just to illustrate this, linear regression assumptions. Okay, so assumptions. Okay, have a go through them. Because these are important, so whatever that you actually make use of, it will have an impact. So it's necessary that you understand the range or the condition that the algorithm will work. Anything outside of that, if you use those, chances are you're going to create a garbage in, garbage out model, and one that is useless in the real world. And that's the whole purpose of machine learning or AI, is that it is useful and practical in the real world rather than in lab situations. So what we did, let me summarize, is to illustrate what to do when linear regression assumptions has been violated. One way to solve that is to make use of robust regression, and the algorithm that we make use of is random sample consensus or RANSAC algorithm. We perform the usual process, the 5-step process. And after we perform the 5-step process, that's done. Okay, when you get up to the prediction part, it is done. But for sometimes you want to actually inspect the behavior to understand the behavior of the RANSAC algorithm. You might want to visualize it like this, give it some X value, perform some prediction using the machine learning algorithm that you built or the model that you've built, perform some prediction, plot it out just to actually visualize so that you understand what it has done or the actual behavior of it. Of course, one exercise I'd like you to do is run the same algorithm except using linear regression. Have a look at it and contrast the difference between the two. That's a good homework for you to do because it really helps you to compare and contrast. That way you can actually understand the difference between the two, and that's one way to actually get familiar with the algorithm itself. With that, I'm going to stop right now. Thank you for watching. I hope that you found that instructions video useful. Good day, everyone. This time we are going to evaluate the performance of a model, and specifically we are looking at regression model. Having done the RANSAC, which is robust regression from the previous lesson, as well as linear regression, the next step then is to evaluate which is actually the better model, or evaluate your regression model to see its actual performance. In machine learning algorithm development or model development, what we tend to do is that we don't actually really have a good way of assessing our model's performance. Ultimately, it's not the intrinsic model performance that we're interested in. What we are really interested in is the actual performance. How well does it actually predict the performance of its prediction, or the accuracy of its prediction? That's the portion that we are really interested in. Now, how do you approach this? Typically, what the practitioner tends to do is split the data into two portions. There is the one portion of the data being reserved specifically for testing, and the remaining portion is used for training the actual model itself. So the scikit-learn has this model selection library package that is built in called train and test split. It does the actual splitting of the X and Y, which is the feature as well as target, for you. And basically what we're going to do here is just to step through the process of looking at the actual performance of the regression model out of model, meaning using data that it has not seen before. So let's step through this, go through it step by step. We first of all import the train test split. The next thing that we want to do is to actually extract the value of purely the X. All right. Now let me just show you what I mean by that. So if we look at the first 5 rows of data of the data frame, what you will be able to see is that these are the first 5 row of data, and all of these up all the way up to here is basically our features. All right, our feature data that we use to actually train our machine learning model. Now, we know the MEDV, which is median value, is our target variable. So we need to actually take this whole chunk here and store it as X, and take this chunk here and store it as Y. All right, so we need to actually prepare the data that way so that the scikit-learn will be able to split it for us properly. And part of the reason for doing that is because the train test split take in X and take in Y. And hence, before you even start using the actual functionality of the train test module, you need to actually prepare your data to X and Y. And the next thing is that the next parameter it takes in is called test. You need to specify how large your test size. In this case, we are reserving 20%. The random state is not really crucial in the building of machine learning model, but in the current case that we are doing now is that we want to actually set the starting point so that we always start at the same starting point. This links in with the so-called random number generation come under the so-called mathematics arena. We set the random state to 0 so that the random number that is being generated always starts from the sequence of 0 here. You can set it to 42, which is what a lot of people do, set it to 100, any number that you like. Now, why do we want to actually set our pseudo-random number to start at the specific same point? The reason being is that we want to actually have a way to benchmark one model after another. If you have a different starting point, you have no way of telling which model or which machine learning model performed better than the other. Hence, we actually choose to fix the starting point. In this case, I'm setting the random state to start at 0 so that it is fixed. And if should I actually run another machine learning model, I can actually compare the performance of the two in a proper manner, in a controlled manner as well. So this is the actual parameter that we take in, which is the XY test as well as random state. The actual method is train test split, and the actual so-called output is X underscore train, Y underscore test, Y underscore train, and Y underscore test. It always spits out the data in 4 so-called array, and you need to actually prepare and sort them this way. It's always X train, X test, Y train, Y test. Okay, let's run that, and we just go through the normal 5-step. instantiate our linear regression, perform the fitting, and then perform the training, and finally perform the actual prediction in terms of test. Okay, I'm going to take a moment and explain what we're doing so that you know the next few methods that we are using to actually compare or evaluate the performance of our machine learning algorithm. Typically, after you model the data, the supposed residual should really be random. It just looks like noise without any patterns whatsoever. So that's the ideal state. So we are doing residual analysis to look at the actual leftover, so-called errors or residual, to see if there's any underlying pattern to it. That's the first thing we do. The other method is look at purely a number to summarize it all, which is really attractive, which is mean square error. Of course, with this, the lower the number, the better. And you have the coefficient of determination R squared. The interpretation of this is that the higher the R squared, the better. So these are the three different methods that we use to evaluate our the performance of our machine learning algorithm. So let me just start with residual analysis. We are plotting a chart, as you can see here. We're plotting a scatter chart, Y-train predict, and the difference, or the difference basically between the Y-train predict and Y-train, the actual prediction versus the actual training. And then we're plotting another scatter graph again, or scatter plot again, looking at the Y-test and looking at the difference between the Y-test predict and also the Y-test itself. The training portion will be in blue, the test portion will be in orange. So the rest is just labeling, some legend issue, some horizontal line issue. That's pretty much it. So let's plot this. Okay, now what can you actually see from this plot? It might not be very obvious. So let's look at let's just remove the test for now. Usually hash basically in Python is just commented out. So this is the so-called training data. If you look at this, it's fairly random. There's a few outlier here and there's a few outlier here. Apart from that, generally it doesn't look like there's any pattern whatsoever. So let me just comment that out. Now let's just plot the test. Well, it has pretty much similar kind of pattern, and again there's some outliers that's out here. Apart from that, it generally is fairly random, but you can see that there are actually large errors or large, the data is not properly modeled. The errors here is actually fairly large, which is okay. I mean, you can't always get it perfect in the real world. We are dealing with real world data after all, and what you can see here is that having shuffled, having split our train test data as we did here, the so-called performance of the training data, or rather the residual of the training data, is pretty much similar to those of the test data, and that's actually what we like to see, and it's a good sign. Good sign being that we split it, but they're both representative, or really the test data is representative of the training data, and vice versa. What you really want to do in an ideal state is that the data that you use, which is the training data, is representative of the real world data or the test data. Okay, so that's really what we actually want to get in, and it seems like that is indeed the case. Judging by this, you can see that there's a fair bit of errors, and the errors are fairly large. So the predictive value of this model is not great, but it's okay, but it's not great. All right, so the next thing that we want to look at is the sum of squares of error. So the lower the number, the better. So ultimately, this is really averaging, which is the 1 over n here. And this is really calculating the actual difference between the training, the actual versus the predicted value, and then squared. So for here, from scikit-learn, we import the matrix and then import specifically the mean square error function that we want to use. So run that and calculate that out, and from this you can see that the errors in the training data is lower than the errors in the test data. So not a good sign, but common. Okay, very common. You're almost always going to get the case whereby your test is always gonna, of your model, always typically perform worse than your training data, the data that you use to train it. Okay, the next one is what we call coefficient of determination. With this, again, the step-by-step process, this is the higher the better. If there's no errors whatsoever, it will be a perfect one. So again, from matrix, we import r square underscore score, and then run the actual r square for the training and the r square for the test. And you can see clearly method 3, which is coefficient of determination, shows the same picture as the mean square error. The so-called test, the testing of the model that we built using the training data, perform worse using the test data. Right, so that's really the 3 things I wanted to show you. One is residual analysis, a second one is the mean square error, third one is r square. These are typically the 3 matrix that you use, or 2 matrix. One is actually visualization inspection that you use to look at and evaluate the performance of your model, both in and out of sample. It's always good though to actually do a comparison against what a perfect model should look like. Now, the approach that we've taken in terms of a perfect model really is that we want to generate some random numbers. So this is actually setting the state to 0 once again. We're using basically x is equal to 10 multiplied by some random number and generate some random number. And y is equal to 3x plus some noise. Okay, and then let's plot this out to see what it actually looks like. So it essentially is the straight line. The relationship is that, well, every step is multiplied by 3, okay, with some random noise. So let's conduct the same process here, do the train test split for our data, and then perform import the linear regression model, perform the actual fitting, and then perform the so-called prediction. And then run our residual analysis. The codes are exactly the same. And you notice that the errors is so much smaller. It's very compact, very tight, pretty much between -5 and 5. And if you look at that and compare it to what we have here, this is vary from minus, well, I'll guess this is close to -30 to all the way to 15, and it's not consistent. There's some part that's worse than the others. And comparing it to this is really nice, compact, and it's consistent right throughout. And we look at the mean square error for both the train and test. Well, it's small. Okay, it's quite a few magnitudes smaller. This is only 0.86 compared to what we had before, which is 19. You can see that it's quite a few, quite a fair bit smaller in terms of the errors. But you can also see that the actual test is, our sample was worse than the in sample. Once more, if we run the r square, the number is substantially higher, 98%, 0.8 versus 98.6, but it's still substantially higher than the 66 and around 58% that we had before with real-world data. So this is as close to a perfect model as you can, near perfect model as you can get. Of course, you don't get this in real life. Why do I actually show you what a perfect model looks like with simulated data? This is akin to teaching a child what an apple look like. You show the child green apple, red apple, and the various type of apple, and basically the child has been trained to identify what is authentic. So when you show him an orange, they will be able to identify, well, that doesn't look like an apple. So essentially you've shown him or her an example of what the real thing is. They will be able to identify what a fake example looks like. With that, I'm going to stop here. In future lessons, we'll try to cover as much of this as possible, but it's going to be a step-by-step process. So for now, I'd like to thank you for following through to the end of this lesson, and thank you once again for watching. Welcome back everyone. In this portion we're going to look at multiple regression. Now the difference between simple linear regression and also multiple regression really is the number of features that you provide for the building of your machine learning algorithm or model. Now in simple linear regression, what you are doing is that you are providing one simple feature, which is called x here. And when you're actually doing multiple linear regression, you are providing multiple features. Here, if you look at simple linear regression, you have one x. In multiple linear regression, you have x1, x2, x3, on and on it goes. For each of the feature on its own, you have a coefficient that you need to estimate, which is beta 1, and beta 0 here is really the actual intercept itself. Now, of course, multiple regression has been well studied in statistics. In the section here that I want to cover, the main focus will be on what is relevant really for data science or machine learning. Essentially, the aspects that we want to pay more attention on is the practical portion as well as relevant for prediction. So let's start with the code portion. We're importing the usual libraries, the NumPy pandas, matplotlib for visualization, seaborn for visualization, and also scikit-learn, which is our machine learning library. So run that, and the next code itself is just to show you the version that I'm using for this lesson. All right, the next portion is to load the dataset. We are still using the Boston dataset, except this time around we're just going to import directly from scikit-learn itself. This dataset is, as I mentioned previously in previous lesson, is embedded within scikit-learn itself. So we import that, but having imported it, the function of load underscore Boston, we need to store the data somewhere. So we're storing it into this variable called Boston underscore data, and the actual data structure is such that Boston data has an attribute called data, which has all the feature data, and the feature name is the name of the column itself. So we are making use of pandas data frame, whereby we providing the parameter Boston underscore data dot data as the actual data, whereby the column names we are using what it was provided, what has been given within Boston underscore data itself, where they named it feature names. So let me run that cell and store it in df, our variable name, and just so that you can actually see what we actually have done. You can see the first 5 rows of data. These are the column names. Notice that what is missing is the actual target, which is the median value. Now, before we get to looking at the target variable, let's extract some information about the data frame, which is we call df. Shape here tells you the actual dimension of the underlying data. You have 2 numbers there, 506, 13. 506 means there's 506 rows of data. 13 means there are 13 columns, or we also call them features. Now, storing this into x, because x is typically in statistics, we call that the independent variable. And as always, when you are building an algorithm, building a model, you will always have a dependent feature. It's the one that we are trying to predict. In machine learning, we call it target variable. In statistics, we call it dependent variable. And we're going to store the data, target data, which in our case is median value. We're going to store that into y. How we extract target is that it is stored, it comes from the Boston underscore data, which we loaded using the load features, and then we store it in Boston underscore data. The attributes, you can access it by using the dot and then followed by target. And we stored it in y, and when I actually print it out, you can see that these are all the median value. Just probably need you to check that to prove that I am indeed correct and stating that these are the actual median value. So pays that you get some understanding. So just dig into it, just the document itself, so that you can actually develop a deeper understanding. So let me just hide this so that we can get on to building the actual model. I'm going to show you one way to do this, to build a machine learning model. The first approach is to make use of stats models, which is a library on its own. And the way that we import it or bring it into our console here is import stats models .api, and instead of typing this whole long thing, which is called SM, and also importing from stats model formula.api, and instead of typing this whole thing, we just call SMF. All right, so importing that. Now the first thing that we need to do is actually to create a model. Now what we need to do first of all is to create a constant term to allow the stats model.api to calculate the bias or intercepts. Now let me just illustrate this a little bit. Now if we don't provide a constant term, now our constant term is going to be just 1 all the way. If we don't provide that, we ended up going to create a model which is mx. Okay, that will be our model. What we really want, let me just do that, is actually creating a model which is y is equal to mx. That should really be small m. M being the slope, also beta 0 sometimes called, plus c. So that's really, this is the second one that we are interested in, not the first one. The last thing that you really want is to have your intercept information. By the way, it's called intercept in stats. In machine learning, it's called bias. Okay, the last thing that we want is to have the bias or intercept incorporated into the slope itself. So we want to actually model that separately. So we actually add a constant term here, so that this is actually modeled separately from the actual slope itself. How do we add a constant? Well, the stats model, the API itself has a built-in function or model, which is @_constant, and we're going to store that into this variable called x_constant. Let me just show you what x_constant looks like by creating a data frame. And if you look at the x_constant, you can see that it is actually 1 all the way through. Essentially, we've added the constant into the x that we created here. Okay, so basically this is adding the constant into the x, which is the independent variables, and we created a new independent variable called x_constant. Basically the x with constant added. So essentially all these portions are exactly the same. Now the difference is that we have an additional constant term so that we can actually create a machine learning model with C being modeled within our machine learning model here. So let me minimize that. Now a little bit of diversion here, just to guide you a little bit, so to help you understand the nature of how Python work and the way that most of these machine learning library is built. There are always some documentation. Now how you can actually pull out those documentation is to use a question mark after the actual name of the library that you are looking for. I have an OLS is what I'm interested in, but I don't quite know the documentation. I might not be familiar with it because I might use it every now and then. I want to know what are the compulsory variables or parameters I need to provide. I also want to know what else do I need to provide for this to work properly. So instead of having a guessing game or go online to search, I can actually just type sm.ols question mark, and it will tell you the endogenous, the exogenous, missing, excluded, none. So basically there are no compulsory variables here, okay, which makes it quite good. These are all optional. The endogenous is the so-called compulsory or something that I do need to provide. The endogenous here, notice that it doesn't have an equal to anything, means that this is actually compulsory. I do need to provide some sort of parameters. The none here means that this is by default is none. The rest actually already have a default value, so you can actually ignore these unless you have those available. The docstring said a simple ordinary least square model, and it has a few other information provided there for you to refer to. I won't go through them all here. There's a bit too much information. It even actually provides some examples of how you do that. Right. Coming to the modeling part. Okay, we've already seen that we have sm.ols. What I really wanted to do is actually provide my endogenous, which is the dependent variable, and then the exogenous, which is our x underscore constant. So we have, coming back here, endogenous, that's the one that I'm trying to model. Exogenous, although it's not compulsory, well, it's good to have because we need something to predict something. So in this case, we are using the x constant, which is all of the independent variables that we have, or the features that we have, plus the constant term. And once we actually run that, we want to store that into our model called model, surprisingly. Okay, there's no feedback. Looks like everything runs properly. All the data is provided. All that we need to do now to activate the fitting of the data to the data being provided, we need to actually use the dot fit method. Now, this earlier line here didn't do anything. It just created an instance of the model, and this happened to be called model. The dot fit here is actually the fitting of it, and now we store all of the key variables into this variable called LR. So if we actually generate a summary of it, it creates this really standard, I suppose you can call it ANOVA or basic regression parameters information for you to refer to. There are a lot of information to look at, but for now, just dive into a few things that we are fairly interested in because it is relevant for what we are actually doing. First thing, it's a least square method. Second thing, R square, which we talked about in previous lecture. So 0.74, which is in translation, if you convert it to percentage, is 74.1%, which is quite decent. And then we have the constant term, all right, and the coefficient of it, and then followed by all of the so-called each of the features coefficient. Negative means this variable is negatively correlated to the target variable. All right, so it's negatively correlated to the dependent variable. Remember, we are trying to use features to estimate the median value, median house price value. So naturally, the higher the crime rate, the lower the house price. Okay, so notice that they are inversely related to each other. So there's CRIM, and then the rest on and on it goes. There are some that's positive, some negative, and it goes on from there. So those are the key things that we're looking for, and that's what we are actually interested in. Other things that you also want to look at in the traditional statistics framework perspective is to look at the p-value. Typically, we look at if the p-value is less than 5% or 0.05, then we take that as significant. Okay, we don't look at it whether it's 0.049 or 0.01. It doesn't matter. As long as it's less than 0.05, it is significant. So looking down, you can see that this is not significant. Looking down, this is not significant. Apart from that, the rest are all significant. Okay, so those are the pretty generic information that I wanted to provide you so that you actually get a grasp of how the actual modeling is done. Continuing on from what we've discussed, I just want to highlight some key points that I placed here. There are a lot of statistical tests and information provided here. Probably far too much to be useful for data science. Nevertheless, if you are trained in statistics and you want to dig into those, it does have information that's useful. We don't necessarily need all of these for data science because the key portion or key focus of data science is the prediction and having models that work on predicting real data. So that's one of the key difference between data science and statistics. Okay, so I've provided all of these information really more for your reference. I won't go through them all here. It's just far too much to be of use. But the so-called description here, it's basically provided here for completeness sake. So do make use of it if you feel that it is relevant for your case. Right, I just want to highlight another way of making use of stats models. Before, what we did is that we used stats model dot the API. So let me just come back here. Right about here. Okay, we made use of stats models.api and we call it SMF. We're going to make use of another way of modeling, which is what quite a few people are more familiar with, which is .formula.ap, so meaning specifying the actual formula itself. Right here, we are using the SMF and we created a formula here. So what you can see here is something that's, especially if you are statistically trained, you're probably more familiar with this. So you have y with the approximate is equal to approximately equal to all of these parameters. So basically you are specifying all the parameters that you want the API to generate the so-called model. So again, we specify that, instantiating it, specifying our model, and then the following line is to actually fit it. And then we call this variable MLR. And if you view the summary, you will get the same information. Well, a good reason for having it exactly the same, because we really specified the same variable. Of course, you can come back here from the earlier information and look at this and say, I don't think indus should be there. I don't think age should be there. Well, technically, I could have actually read it from here as well. So let's come to this here. And then we create another model, right? And then let's visualize this at the same time. Okay. Right, just create some space there. So we said remove indus and we remove age. And basically just run that. Okay. Well, I probably could have changed the name a little bit, but never mind. As long as we don't run it again, we kept the original information. Okay, so notice that indus is gone, as is age, and the rest of all of these parameters are actually significant. If you look at the R-square, well, no change, 74.1 versus 74.1. Okay, so by and large, that portion really didn't actually change much at all. Did it improve? Maybe from the adjusted R-square perspective, we can use that as a comparison. Usually when you are looking at multiple variables, you use the adjusted R-square. So this is 73.5%. This is 73.4. It did improve. Okay, it did improve. That's really pretty much all that I want to actually cover for multiple linear regression. Right, I've been talking non-stop for a wee while. It's probably a good time. In fact, I think it is a good time for you to actually, well, do some exercise just to solidify your understanding a bit. And also so that you can actually get some hands-on practice. So to begin with, really this exercise is the following. I would like you to create a model, again using the same data, which is the Boston housing data. Except I want you to actually, instead of making use of all of the features, I want you to actually create a model using the following 4 features: CRIM, ZN, CHAS, and NOx. Okay, so that will be your exercise. I'd like you to stop the video. In the next video, I will cover the solutions that I come up with. So I'll see you in the next lesson. Okay, in our last lesson, I asked you to try this exercise to create a model to predict the median house price value using these 4 parameters, okay, or for features. Well, here's the how I would tackle it. I am using the formula API, and this is how I would model it. The formula will be equal to y with the the approximate sign to crim plus zn plus chas plus nox, and as I mentioned, this is the API that I'll call. We already imported the SMF earlier, which is the stats model.formula.api, and then we name it as SMF rather than typing the full name. So the next thing then is to create an instance fitting the data, and I'll call it MLR as before, and then print the summary out. And that's really the outcome of the actual model itself. Is actually substantially worse than before, 29.5%, but nevertheless, the purpose of this exercise, not so much for that, is to get you familiar with the API call itself so that you understand the actual procedures or how to call it and extract the data, and so that you can actually do some analysis and develop some understanding of the process to create a machine learning model using stats model. Okay. There's one output I'm not too sure if you did actually pay attention to. There's no warnings here, which is a good sign, but there was a warning here. I don't know if you see this. Number 2, the condition number is high, 1 to the power of 4, 10 to the power of 4. And it actually gives you this indication. This might indicate that there are strong multicollinearity or other numerical problems with the underlying model that we use. Multicollinearity basically means that there are 2 or 3 features. Basically, we have features that actually are correlated with each other or closely correlated. That would create a problem, and basically will create very unstable estimation of our coefficient, and that's not something that you really want. So having that warning, which is this conditional number here, means that we should actually delve in a little bit. The conditional number for this is substantially lower at 327. So going back to the documentation that I provided earlier, and this one is here. This is a test for multicollinearity, which is the conditional number. Anything greater than 30 indicates unstable result. So that's something that you do want to pay attention to. So let's scroll down to how we actually deal with this. You can use the correlation matrix. It's something that we've seen before. I want to actually reuse this. This is some way what we can actually use to help in terms of identifying features that are closely correlated or have multicollinearity problem. I'm going to use 2 decimal places and create the so-called correlation matrix. And of course, this is a little bit hard to read. So I'm going to create a mask, meaning anything that's actually less than 0.6, less than 0.6, or greater than minus 0.6, we're going to make it 0. So that's the mask that I'm creating. I'm just basically going to make them 0. Leaving anything that's greater than 0.6 or less than minus 0.6 for us to study. So we're going to dig into those with greater than 0.6 or less than minus 0.6. Okay, so run that. Again, this is hard to read, so I'm going to create a heat map. Let me make it smaller so that we can actually visualize it in one screen. And here it is. So you notice that they are low or 0. They are not actually 0. They are those that's between minus 0.6 and positive 0.6. So everything in that range is being 0. Okay, made null. And as you can see here, whatever numbers left is 1 or greater than 0.6 or less than minus 0.6. And 0.6 here, minus 0.61, minus 0.75. So if we just look one side of this, then you notice the indus is actually quite closely correlated to a few things. The Zn is closely related to DIS, Crim is correlated to RAD. So these are the things that you probably do want to dig in a little bit more to develop further intuition and understanding as to why it is like that. There are other ways. I'm going to show you another way, which is using eigenvalues. And what it shows here is that note that index 8, which is highlighted here, with the eigenvalue of 0.0635, well, because I actually set this to, let me just change this. Okay, so just copy that line of code, come back down here. Okay, so that you can actually see the whole thing. Change it to 4 decimal. Okay, that's better. Because it's near to 0 or very small compared to others, small value here really mean that there is a present of collinearity. What exactly is number 8? So you can actually see here that's there. And likewise, you can see index 982 have very high loading when compared against the rest. So which one are these? So let's dig in. They are Indus, RAD, and text, which we already identified here earlier. Indus, text, and RAD. Those seems to be the troublemakers in all of these. Okay, so essentially we can identify using either what I showed you earlier, which is the heat map using correlation matrix, or using eigenvectors. Okay, from eigenvectors you can actually pick that up, those with small eigenvalues, or using eigenvectors, large eigenvectors. Okay, so those are the two ways of picking them up. Coming from another angle, we want to revisit the feature importance, and as well as the extraction itself. We can check for the direction of the coefficient and also the actual impact of the variable or factor on the model. So we have these 13. So if I plot the so-called text and also plot the NOx itself, there's something that should actually stand out if you look carefully. Number one, when I plot the tags, you can see it range from 200 to 700. If you look at NOx, it range from 0.4 to 1. The scale of these two are really quite large, and it will suppress the so-called coefficient itself, which is not an ideal situation. What we can do is actually standardize the variable. Okay, that's one way to do it. I'm going to quickly show you the outcome of this, but not showing you how to do it. Okay, but I will go through the how to standardize variable in future lesson. For now, we're going to use scikit-learn to build the model, and we're also going to standardize our variable so that it is between 0 and 1. Okay, so let's run these codes of cells. So just trust me in this. Okay, I'm not going to talk through these because they're just far too much information. I will go through them one by one with you, but trust me that I will come back to this in the future lesson so that you actually get a better and deeper appreciation of this. Right, having run all that, the coefficient of the so-called model comes out to be this. And one thing you probably will notice is that the coefficient is a lot more uniform now. Okay, it starts from 0.02 to 3.7. Not as bad as what we had before in terms of the beta. Let me just try to go back there. In terms of beta, let me just go back there. So we look at the beta here, it ranged from, what is the smallest? 0.0093, yeah, and all the way to 36. The range is substantially larger and wider than what we have here after you have actually standardized it. Okay, so that's the one thing that I want to highlight. Okay, and one of the last method that you can utilize is to use R-squares to identify the features, the so-called key features. How do you do that? Is compare R-square of the models against R-square of models without a feature. Okay, when you have a significant change in R-square, Basically that signify the importance of the variable or the feature that is not present. So the compare and contrast is useful. We're going to do one example here with or without LSAT. So let's just run this. Okay, so when you actually take away LSAT, notice that there's 4 here. And what about if we actually remove age? Well, when you remove age, notice that from here to here, there's no difference. But from here to here, there's a substantial drop. Else that then is actually a significant feature or more significant feature when you compare that with age. And likewise, it's pretty clear from what we have done before. After the so-called standardized version, you can see the LSTAT is the most significant of the lot versus age, which is a very small part of the actual model itself. Well, I hope that has been somewhat enlightening. I know there are a lot of information that's been gone through there. You're probably feeling a little bit overloaded now, which is totally understandable. But I hope the step-by-step process help you to actually get some grasp of the flow at the very least, and the approach as the second thing that I want to highlight to you. And last but not least, do practice. I believe there's no substitute to practicing, so that you actually have some appreciation of the steps, the process. And last but not least, and I think it's probably one of the more important approach to learning machine learning, is to actually play around. To play around with each of the features. So what I've illustrated to you is taking our stat out, taking age out. Try that with each and every one of those variables. And trust me in this, the more you play with it, the more intuition that you will develop, the better that you actually understand how the whole system works. With that, I'm going to stop. Thank you for watching. I look forward to seeing you in the next lesson. Good day, everyone. We're going to venture into a very unique method, but very popular as well. Sometimes it's not utilized enough, I believe, especially when you're dealing with linear regression that's not working with data that's normal at all and has lots and lots of outliers. This method is called regularized methods for regression. Without going into a lot of the math, I just want to highlight 3 different types of regularization method and when to use them, and I think that's probably as deep as I want to go. The times past, I have a tendency to probably explore the math part. Well, I'm a math geek. What do you do? And that probably turned quite a fair few people off. I don't want to do that. I want you to be able to make use of the method and not get bogged down by the details at all. Ultimately, none of us really want to know how the car engine work and and the so-called percentage efficiency of it, and also what's burning and and the RPM and all of the details. Most of us just want to get in the car, start the car, and get me from point A to point B. That's really all that we want to know. So I'm going to focus here in this lesson on 3. Ridge regression, least square shrinkage and selection operator, which is a really terrible name. We just call it lasso, okay, LASSO. And the last one is called elastic net. So those are the 3 that I'm really going to just dwell in there. Let me just highlight the difference between ridge regression and lasso. What ridge regression trying to do is minimize this term. Okay, this is what's called the square, okay, to the power of 2. Okay, so this is what we're actually trying to minimize here. It is also called the L2 penalized method. Compare this to lasso, notice there's no square. This is the L1 penalized regularizer. Whereas elastic net combine the 2, which you have the square as well as no square, which is fairly straightforward or highlighted here. Well, not exactly straightforward, but you can see what I mean. Okay, going into the so-called intervention development part. I want to show you the outliers. Okay, the actual impact of it, not found. Okay, and just illustrate to you. Now, if we just do a straight linear regression, this is a simple linear regression. Okay, I'm gonna add some outliers. Okay, if you look at the outliers that's being added here, notice that the coefficient goes from 0.47 to 1.5. The whole line has been tilted, pushed downward this way and pushed upward this way because of this outlier here. Now, if we look at ridge regression, it doesn't actually, well, it did move, it still moved, but not as bad as the linear regression. If we come back to the effect of the outlier is from 0.47 to 1. Okay, not as bad as the 1.5. Okay, so this is ridge regression. So this regularized method basically restrict the actual movement. It doesn't allow it to flow so easily. That way it's not so poorly or badly penalized by this outlier and this outlier. Okay, so let me just look at lasso. Lasso, likewise, is very similar to ridge regression. It's still affected, but not as badly affected as the linear regression on its own. So if we look at elastic net, and you will see that it performed the best of the two. Basically, it actually combines the two method altogether. So from 0.47, it's still slightly affected. 0.47 or 0.49 from memory, it moved to 0.74 instead of 1.5. So really, in summary, when should I use lasso, ridge, or elastic net? Now I've got this answer from Stack Exchange. You can Google it and you will be able to actually get the answer as well. Now, ridge regression can't zero out coefficients. You either end up including all the coefficients in the model or none of them. Lasso, on the other hand, does both parameter shrinkage and variable selection automatically. Okay, and if some of your covariants are highly correlated, you may want to look at elastic net, which is a combination of lasso as well as the ridge itself. So I hope that actually provides some foundation for you to explore, not necessarily answer all your questions. You might not even have a really deep understanding of ridge or lasso. I highly doubt that you have. But at the very least, I think this lesson hopefully will provide you with some exposure to understand that in the future, if should you come across lots and lots of outliers, you feel that it's actually having a major impact on your model, you can start think about, hey, Anthony mentioned that there is such a thing called regularized regression method. I can't remember whether it was ridge or lasso or elastic net. Let me go back to this lesson and dig into it a little bit more, or if I can't find this lesson anymore, I can Google ridge or regularized regression. So if I have achieved that, that's really what I actually want you to actually get out of this lesson. Not so much the intricacy of it, but just develop enough intuition and understanding so that you remember there's such a thing called regularized regression to solve the problem of outliers problem. With that, I thank you. I really appreciate that you pay attention right throughout. It's probably not easy, and I know it's actually not easy to follow along with all that math, especially if you're not mathematically inclined. And I hope you, this lesson help you somewhat in solving some of the common problems in machine learning. Thank you so much. Welcome back, everyone. In this lesson, we're going to go into polynomial regression. Polynomial regression is particularly useful when you're dealing with non-linear relationship, which is what we're going to explore. Again, I'm going to skip through the math without going into depth on those. I just want to illustrate with example the basic concepts of how to deal with non-linear relationship, but using polynomial regression. Again, we import the usual library and the basic scikit-learn, and so this is just to illustrate to you which version of NumPy pandas and the rest of the packages and libraries that I'm using. Now, more to the point really is this portion here, this formula, this math formula, as you can tell here, is x to the power 3, clearly is not linear, plus 100, which means we are raising the offset by 100, plus error term. And I'm going to model that using random numbers, and we're going to do 100 samples. Linear space here basically means that we're breaking the x from 0 to 10, 100 subsegments. And we're generating 100 random numbers here by 100 multiplied by 100 just to increase the scale. And for this is y is equal to x to the power 3 plus random number that we generated here plus 100. So basically that's this formula here. So x to the power 3, random number, and 100. And I'm plotting it out just so that you can actually see what it looks like using a scatter diagram. Looking at this, you can see that the so-called it is not linear. That's the first thing that you can observe. Second of all, you probably can't see clearly here is that the so-called line has been raised by 100. Okay, so it's 100. The reason that we can't really see the clear line here is because what I have done is this function here. All right, this multiplied by 100 created a substantial amount of noise, which I want the machine learning model to actually model that, okay, to see through the noise and to be able to identify the underlying pattern that's being generated. Now, in real life, you're not going to have access to this formula, okay? All that you're going to see is when you plot a scatter diagram or visualize it, you're going to see something that looks like this. And from that, you're going to have to deduce that, well, there's no way that the relationship between x and y is going to be linear. No matter how I draw a straight line, it's just not going to fit the data. There is a certain underlying pattern here which goes fairly flat and then start to accelerate upwards as x increases. All right, so those are the things that you have to observe. Of course, this will come with intuition, and as you exposed to more and more examples, you start to get the idea of how to actually tackle the problem directly. Now, I'm going to just show you something here, just so that it's clear. Now, what happens if I remove the error term? And how you remove that is just basically remove this term altogether like that. Okay, just cut it away. And you can actually run this again. And you can see, right, the clear pattern that comes with it. And if you look carefully, this is actually, well, it ought to be 100 really. X to the power 3 plus 100. So the starting point should really be 100, but visually it doesn't look like that, but it should be. And the second thing is that you can see that this is not linear. Okay, the noise kind of masks it. Okay, let me just remove that and just make it like so that it actually emulate this formula here, x to the power 3 plus 100 plus random number that's generated. And from this, you can actually see the so-called, it is not linear. Technically, it's x to the power 3, but you don't know that. So the only way to do that is just visualize and then start generating model and using performance evaluation to see how close we are to the empirical data that we observe. So let's go back to what we had before, which is really the noise. And what we did here is that we generate 100 sample based on what we specify here, and then we multiply the number by 100. So the scale of those random number generated are magnified by 100 times. Okay, the random number, as you're probably aware, is it generates 100, but it's between 0 and 1. By multiplying by 100, sorry, this should be minus 1 to 1, okay, with the mean of 0. Multiplied by 100, it magnified, so you can see that from 100, we go below and we go above, depending on whether the number is positive or negative. All right, I've gone through that at length. The next part then is really looking at how we model the data using linear models. All right, so let's start with the matrix of R square, and this you have seen it before, generating in terms of creating a model, selecting the model, predicting the model from the data that we have, and try to see if we are able to, Well, come close to modeling the data using the underlying machine learning model. From R-squared, it says 76%. Well, close. As always, there's no way for you to tell whether this is the best ML model. So the next best way, since you don't have something to compare against, is to actually create another model just as a comparison. Now, I mentioned before, looking at the underlying, just purely the visualization aspect of it, you should have been able to actually identify that it is not normal, right? Meaning it's not linear. So what we do here is we import from scikit-learn pre-processing, import what's called polynomial features. And we stated that we want to actually go up to second degree, meaning x to the power 2. And we perform fit transform of x, all right, using polyrect, which we instantiate here. And basically, we're actually transforming the x itself. And again, we perform a linear regression. This time, we call this model lin_regression_2. This is the second model. This was the first model. The LR here is the first model. So fit the actual x poly, which we actually generated here, and then y, and then perform our so-called prediction. And plotting that out, it fits the data substantially better. Okay. Now remembering our formula which we use to generate this data is x to the power of 3. Okay, let's come back here. X to the power of 3. Now, when we actually stated polynomial features degree is equal to 2, right? So what does that actually mean? So let me just go over to scikit-learn. Polynomial features, go to the documentation. Okay, so you can see here that it actually states how the default is 2. Okay, and the degree allows you to state, so x to the power of 0, x to the power 1, x to the power 2, x to the power 3. Let me come back here to look at the actual underlying data itself. Right, remember that we are looking at feature generating this feature degree is equal to 2. All right, so just remember x, capital X. Okay, let me just show you the first 5. Okay, let's try x poly. Okay, I need to be capital X, capital XP. Okay, and we'll look at the first 5 value. Looking at this, we are generating a constant term followed by the original data term followed by the x to the power of 2 term. Okay, so this is x to the power 2. Now, if you want to go one step further, meaning degree 3, okay, then you can polynomial features and then the specified degree is equal to 3, and we generate something that's similar to this. Okay, but we're gonna call this degree 3 and example. All right, so basically fit transforming the actual x. Again, just to show you, now if we look at example and look at the first 5 values, it's gonna be a repeat of this. You have the constant term, you have the original term, x to the power of 0, which is 1 really, so the actual underlying value itself, and you have the x to the power of 2, and then you have the x to the power of 3. With the example, hopefully that's a little bit clearer. Let me just to go one step further, just to ensure that you really understand this. I'm going to go one step further. I'm going to use 0, 1, 2, 3, 4, 5. Okay, that ought to be pretty clear now. And the next thing is we're going to just directly make use of the polynomial degree. Okay, so result 2. Fit transform, except that this time we are fit transforming RES, and so that you can see the data right away. Okay, so looking at RES, which is really 0, 1, 2, 3, 4, 5. So you can see here we have the constant term 0, 1, 2, 3, 4, 5. Now this is the square term. I hope that's substantially clearer. Just to go one step further, just so that we can actually kick this out the ballpark with clarity. And finally, this is not polyreg. This is called degree 3. And if I run that, you should be able to see that there's 1 and then the value itself to the power 2 to the power 3. Okay, having done that, let's we've already seen this. This is substantially closer than the linear that we saw before, which is over here. And if you go to x to the power 2, it's substantially closer. We know the answer is x to the power 3. Within the range that we're looking at from 0 to 10, it's not so obvious. Once you actually have data going to 20, x equal to 20, x to the 40, x to the 100, then it becomes very obvious. But within this range is substantially close. Okay, that's the problem of the fact that we haven't gathered enough data in too narrow a range, which is why we weren't able to observe empirically that this model is not quite the best one. Okay, although it's better than linear, but it's not the best one. It should really be x to the power 3. So these you have to actually, as you collect more data, you might have to revise your model over time. Now, having done that, we'll just go one step further and look at real data. And I want to look at this two variable here, dis and nox, and just to illustrate the concept. Slightly different. This notice that this is a decreasing function. As it gets closer and closer to 0.4 or 0, it starts to flatten out. Okay, the actual speed of decline decreases. Clearly, this is not linear either, but we can actually start with the linear modeling, and you can see the R square is 0.59. Now, I'm not going to go through this. I'll leave it to you to actually go through the line, because really it's a repeat of before. I've gone through that, except my code now is substantially more compact. This is the actual, the first 3 line is the modeling, the following 4 line really is just plotting. And the best fit line of best fit is here, and you can see the R square is 59. If we try to the power 2, okay, to the power 2 really again is that we have the polynomial features, fit transform, and then instantiate the model, fit the actual data itself, and this part here really is rearranging so that we have a we extract the minimum and we extract the largest with a step of 1, just so that we can actually have the x fitted x-axis data so that we can actually perform the prediction. All right, so that's where the y underscore prediction is about. Now, the reason of doing this step is so that I'm really trying to chop up x in an even interval, and I'm going to use that as my independent data to predict my dependent variable, which is y in this case. Ultimately, after you created a model, you want to actually run the prediction just to see what the outcome looks like. How close is it to the actual original data? In our case, because from my intuition of looking at it is that I just want to actually have an evenly spaced x so that I can actually run the prediction to generate and see what the y is mapped to, and then compare to the original data. And then after that, really it's just a matter of visualizing it. And if you look at this, well, although R squared tells you is better, this part is a problem. Okay, so that means we need to actually use something else, maybe log or some other method to model this better. But nevertheless, I wanted to illustrate 2 things. Just using polynomial might not solve your problem. That's the first thing. Second thing is that R squared, although has improved, might not be the best thing. Okay, it might have worked between the range from 0 to 8, but beyond that, it actually is a terrible model. And this is also part of building the machine learning model, is that you need to understand the range that your ML is good at, and keep it working within the optimal zone. Beyond that, you might want to actually consider not utilizing the model at all. And quite often in real world, you use multiple models. One, it basically kind of like benchmarking and always having multiple ML to compete against each other, so that they will act as a check and balances against each other. Let's try cubic, so meaning to the degree of 3, and run this whole exercise again. And as you plot it out, okay, the R-square improved in very marginally, 0.01, and as you can see, it did improve, although start to dip towards this end here. Now this is one of the problem of using higher polynomial, meaning x to the power 3 and higher. You're gonna have overfitting start to kick in. It's a concept that I haven't talked about much. It's something that we'll start to talk about in future lessons. I just want to wrap up this lesson to just give you basically the whole idea of this lesson is to give you another perspective that you can utilize, and another tools or techniques that in your armory to solve the problem that you have to model after the real world data. And the polynomial is quite often a good way to do it, because it's technically not what you will call higher dimensional, in that sense. Basically, it's still linear. The model that you've created is still linear, whereas the difference is that you are just adding the so-called x term, but using the original data. But this original data you created x to the power 2, x to the power 3, so that there are a bit more flexibility. Okay, so that's really the basic idea of polynomial, just really extending the linear models to so that it becomes more flexible and more powerful. I hope this lesson has been useful, and thank you for watching. Good day everyone. In this lesson we're going to go into nonlinear relationships. Once we get to this point whereby the underlying data is clearly nonlinear, we have to actually start moving away from the simple ordinary least square or linear regression or the polynomial. As best as we can, we try to make use of those even as a baseline. But once you actually start looking at data that is substantially more complex and there are a lot more interesting features, I suppose you can say it, then we have to start looking at models. They're a lot more complicated and a lot more rich to describe, and try to model, use those to model our underlying data. The usual drill here is importing the libraries that we need for the purpose of our lesson, loading the data, have a preview of the data, and just basically read our data in. Okay, while that's running in the background, the first regressor that we're going to make use of is called decision tree. This may not be very common knowledge to a lot of people. Decision trees aren't just purely for classification-based machine learning. It can be used for regression-based. A quick differentiation between regression versus classification really is that classification is often binary in nature, or things are boxed into different classes. Apples, orange, dogs, cats, those are distinct classes on their own. 0 and 1 is obviously another example. Whereas if you're talking about regression, it's the numbers that you're dealing with are continuous in nature. With the example we've been looking at so far is house price projection, or the median value that we're looking at modeling. And with that, you can see that the value is continuous. There isn't a distinct category to it. So that's the basic idea here. Is that under scikit-learn, there's a decision tree library that's built in, and yes, you can use decision tree, except that you do need to import the decision tree regressor. And we are looking specifically at just one of the feature, in this case LSTAT. I just want to use this as an illustration lesson for instructional purpose rather than full-on model building. For now, we need to understand what is it that we are working with, the actual features and the stylized characteristics of decision tree regressor rather than full-on modeling of the underlying data. One of the so-called parameters that we need to specify is how deep or how big do we want to build our tree. In this case, we specify maximum depth of 5. We have no way of knowing whether that's too deep or not. We have to iterate this process until we develop some intuition of the underlying data. So let's try that and then fit it. Okay, these are the outputs. There are a lot of parameters that you can actually tune, but for now, we just really want to make use of just one, which is max depth. And the next thing is just plot it. The blue dots are the underlying data, and the black line is our predicted prediction using the decision tree. That's where the prediction part comes in here. Now, this function here is just really x is, it comes in an array. What we wanted to do is just flatten it so that it becomes it can, well, originally when it came in the form of vector. We want to just flatten it so that it's just a continuous, it's just an array. And then the next thing we want to do is actually just sort it from the lowest to the largest. Otherwise, it gets a bit problematic when it comes to the plotting. So that's really the basic idea there. And as we actually performing the prediction, this is the x value and this is the y value. And as you can see here, if you plot a linear regression, it would have been like this. And this is not what you would normally call a normal model. You can see that it's all over the place. This is what we call a telltale sign of the model overfitting. We might have given it far too many degrees of freedom and it starts fitting this way. And one of the way to actually reduce that is just to change it to, let's just say 2. And you can see that it's substantially better. But what we might have done in doing that exercise is that we might have restricted it so much, kind of like a the regularization technique that we talked about earlier, having a bit of tongue-tied today, just to restrict it from being able to model the data too much. And 3 seems okay, but I just want to go back to 5 just to illustrate to you. As you can see, this is quite a lengthy process and one that you need to iterate through just so that you actually understand the model that you've built. So we've looked at 2, we looked at 3, and we looked at 5, and it seems like 3 is probably one of the best. And we also, well, highlight this whole exercise here using 2. Decision tree is one. We can also look at another, which is called random forest. We're going to make use of this model. To begin with, I'm splitting the data into train and test. I'll explain that in a minute, and keeping 30% as our test. And we import the random forest regressor. This is under ensemble. It's a different type of model. Random forest technically is a combination of decision trees. It's not just one tree, but many of them. And a couple of criterions that we need to provide for now. Don't wait to worry about these. Essentially, it's just I'm saying, look, estimated 500 times using mean square errors. Don't worry about the random state. I just want to fix it so that I get the same output, and also use all the threads my computer calls to actually does the computation. Because if you're working with lots of data, random forest is actually computationally quite intensive. Fit the data, perform the prediction for our training data, and perform the prediction for our test data. And look at the mean square error. Kind of hard to tell whether that's good or bad. If you look at the R square, it's 97.87 for the training, and then in the out of sample or the test is 87%. And if you look at the mean square error, in sample is 1.87, then test is substantially worse. So that tells you, our model is still not great. There seems to be something else that's actually at play here. But R squared does tell you that it is an improvement or somewhat better. And the next model that I want to look at is called AdaBoost, also an ensemble method. So let's run this and look at the direct comparison between the mean square error as well as the R square. You notice that the AdaBoost did not perform as well as the random forest. So in this case, we may revert to random forest, but quite often in real life, you will still continue to run the AdaBoost on the side as a check, especially if it's useful to help you to evaluate random forest, especially if both models are deteriorating concurrently. It tells you that something is changing in the underlying data. Right, with that, I'm going to stop. And just to summarize the lesson here, when we're dealing with non-linear relationships, we may deviate from the normal linear regressions or polynomial regression model when we start looking at decision trees, random forests, as well as AdaBoost. And there are more, but ultimately this is just to show you these models that you can actually make use of as for regression as well. In our previous lesson, we talked about decision tree. Well, really, this is actually a very brief introduction to decision tree, random forest, as well as AdaBoost. As an added benefits of using those two models, let me take a step back. Remember when we were looking at the Boston housing, there were a lot of features. Let me see if I actually did provide. Yeah. There are a lot of features. You have no idea which is the important feature. I did talk about adding one by one and observe using R squared to tell if the actual data, the feature itself is important and provide any significant value add in the machine learning model's prediction. There's a shortcut or a workaround to get to those answers really quickly. That's where this random forest as well as AdaBoost comes in really handy. So this is the part whereby we want to revisit the feature importance, which we did earlier. The questions that we want to ask is that we have 13 features for the Boston housing. Are they all equally important? Which features are more important? And can scikit-learn help us with this exercise rather than going through process of elimination one by one? Well, if we use the AdaBoost, we already performed the modeling earlier. AdaBoost have this special feature, or you can call it method, called feature underscore importances, and it generates this so-called values. And if I look at the columns of our underlying data, I just need to, combine the two and view them concurrently, which is why I'm using pandas data frame here and label the column as feature, sort them in ascending order, descending order, because I set it to false. Then you can see that LSTAT has the highest value, followed by room number, and all the way down to CHAS. So this is in ranking order, the importance or the feature importance. You can also plot them to see in terms of the value, absolute value relative to the rest. And you can see that the first three, although this is not in percentage format, provide substantial amount of the explanatory power towards the so-called median value of the house. If we look at random forest, it also have the same feature importance, and as we plot it, it pretty much state these same LSTAT, RM, and DIS as well, although in slightly different so-called scale, but they still pick these three as the most important. After that, there's some shuffling and slightly different in terms of order. Okay, so a bit of exercise for you, looking at decision tree, regressor, and just to actually compare. Now what we did earlier is that we did the random forest, and we also did edibles. And what we did is that we split the data to train and test set. What we didn't do is to calculate the mean square error as well as R square. What I'd like you to do is actually do that exercise using decision tree regressor and see what the actual outcomes are. I will provide the code for you to view as a comparison. Bearing in mind, there's one more thing that we cover in these two lessons is also the so-called feature importance. I'd like you to actually try that exercise using the decision tree to help you with the, to not just watch me go through the whole process, but also you actually get your hands dirty as well. So let's walk through this exercise. We perform the prediction. Of course, we create the instance of the model, perform the prediction, followed by running the mean square error and then the R square. It performed far worse than both the random forest as well as the edibles. And finally, when you look at the feature importance, the order is slightly different, but they are still the same three variable, else that rm and this, else that rm and this. Okay, with that, I'm gonna stop right now. Hopefully you've got the same result. Feel free to dig in a little bit more just to understand the whole exercise. Welcome back everyone. We're looking at data pre-processing, which is really a very important lesson for you in terms of the workflow of building machine learning models. Let's start with the basic, importing the usual, importing the data, preparing it, and plotting the data itself. So we're looking at just basically LSTAT, again, the non-linear characteristics of it, and just have a quick comparison. Of course, if you are familiar with gradient descent, this is what we're really doing here. But rather than going through the extreme details of talking about the mechanics of gradient descent, I'm just going to show you the illustration of what happens if you are not, or if you have not pre-processed your data. And the whole idea of gradient descent is it's an algorithm to identify what we call the lowest errors. So basically, it's a method to descend down, meaning the idea, as you can tell from the name, is gradient descent. So it's following the actual gradient itself to go downhill, and the actual gradient is measure of the losses. Okay, so you're going from high loss to lower loss to lower loss, and the steeper the gradient, meaning the faster the rate of drop, that's the path that it chooses until it reaches a point whereby it cannot go any lower. That was what we call the minima. And the idea of doing this is that you are trying to lower the loss, okay, or lower the difference between your prediction versus the actual real world value. So it's really trying to minimize your losses or come to a point whereby your prediction is really close to the real world or the real world sample data that you have. So that's a 1 minute explanation of gradient descent. I don't want to get in the way of you understanding the pre-processing, the idea of pre-processing that I'm trying to actually explain here. Now, when it comes to pre-processing, I'm going to compare now without pre-processing versus with pre-processing. And the speed is one, although I can't illustrate here. And the second thing really is what I will call the, you might not get to your ultimate goal of getting an optimal estimates of your coefficient or the value for your machine learning model if you don't pre-process your data. All right, so let's just plot this out. And you will note that as we actually go through the so-called epoch. Epoch is each cycle of looking at the data to estimate the so-called coefficient. You'll notice that it seems to be okay until we reach, well, closer and closer to our final estimate of our coefficient. Come this point, it explodes. And the explosion really shows you how unstable the coefficient that we have come to derived when we don't pre-process the data. Compare this to the pre-processed data. It starts with high error. This is sums of squares of error. And it continues to descend lower and lower until the point whereby it's just stable. And this is the kind of behavior that we prefer to see when it comes to estimating our coefficient. And that's the two comparison. I hope I made a point of trying to pre-process your data. It's always a good practice to pre-process your data beforehand, before you start building your machine learning model. Okay, so that really gives you a very quick rundown of one of the benefits of performing data preprocessing. There are others. As we go through the idea of preprocessing, you will be able to see more and more the difference between them. And just an extension of the preprocessed data, we have the histogram of X. The original data looks from 0 to 40, and after scaling, you will notice that it actually ranges from -4 to 4, and with the center mean of around 0. And the mean of this is around 10 for the LSTAT. Okay, so this is the actual data itself. Right, so let's look at data preprocessing. There are 4 types. There is the mean removal. Basically, you are looking to shift your data to mean of 0, standard deviation of 1. Min-max is basically scaling it to a range, quite often is between 0 and 1. Then you have the other two, which is normalization and binarization. I'll go into a little bit more detail when we actually get to that point. There are a couple of things here. Is that there are some assumptions that comes with pre-processing, data pre-processing, and these are academic assumptions that's been made, and this is scikit-learn, the documentation stating how it works in real life. There are a couple of assumptions. First is that it follows a normal distribution, and we know how, well, basically how impossible that the data that we have in real world come close, or if it remotely come close to normal distribution. Second thing is that it says that most methods are based on linear assumptions. Of course, this is going to be broken from time to time, and quite often actually. And the third one is most machine learning requires data to be standard normally distributed and Gaussian, which is normal really, in other words, with zero mean, the mean of 0, and unit variance, which is another word for variance is equal to 1. And when it comes to scikit-learn, the documentation from the practitioner basically say that it quite often ignore the shape of the distribution and just transform the data to center it by removing the mean value. Removing mean value means we have a bias. The bias here is not in the English word of the word bias. Bias here means basically we have the value y is above 0 or below 0, meaning it deviates from 0. So we're trying to center it so that y, which is a dependent value, is 0. And then scale it by dividing non-constant features by their standard deviation. So ultimately that means we are converting the standard deviation down to 1, or variance of 1 to be more exact. Let me just show you from scikit-learn, and the training data here is really those that we are looking at specifically. So you have 1, -1, 2, 2, 0, 0, and 0, 1, 0. And the mean here, the axis is 0, meaning along this, okay? And along this and along this. So it's 1, 2, 0, -0, 1, and 2, 0, 1. So as you can tell from here, that's why this mean is 0. There's also axis equal to 1, which is actually along. Okay, so this is vertical instead of horizontal. Let me show you one by one each of the 4 different types that we talked about here. You have standardization / mean removal / variance scaling. I'll leave you to delve into the math. That's not important for the purpose of machine learning. it is useful to know. It's important to know as well, but it's not as important when it comes to the actual practical application of it, to understand how it's used in the real world. But I will still strongly encourage you to actually dig into the data itself, or dig into the algorithm, what is done, and the implications of not doing it versus the implications of doing it, and the pitfalls as well. Those are the things that to keep in mind. For now, the focus of this lesson really is how do you actually pre-process the data. So we have the pre-processing, which we actually import here. This is the actual library itself. Remember, these are our original raw data. And after you pre-process it, you'll notice that the mean is now 0 for all of the vertical, and the standard deviation is all 1. So this is under standardization or mean removal or variance scaling. So this is really the first method that I wanted to cover with you. There's one thing to keep in mind though, is that when you are performing machine learning, so far we haven't talked about the topic of splitting your data into training data versus test data. You need to be mindful of the process of preparing your data and building the machine learning model. And when you are actually pre-processing your data, you should not pre-process all your data. You should only pre-process your training data. Okay, and using the same scalar, okay, you don't fit it again when it comes to working with the test data. You only need to transform your test data. Otherwise, the so-called creep forward, or you are peeping at your answer, start to creep in. Okay, so that's the one part to be very mindful of. So we first of all notice it's just the training data, and these are the mean, these are the scale, and you just transform your training data. You don't actually go and fit your test data. Okay, that part is important. And when we plot it out, this is what it looks like. And now you only utilize the transform for your test data. Okay, that part is really crucial to understand, else you're gonna make the cardinal mistakes of allowing your algorithm to be trained on your test data. Okay, it's just like taking an exam. You have already seen the test questions as well as the answer. Of course you're gonna perform well, but what's the point of doing that? If you've done that, it doesn't, you have no idea whether you've learned the subject matters or not. So that's the whole idea of ensuring you don't fit your test data. The second method is really on what we call min-max, or scaling the feature to a range. In this case, we are scaling it to between 0 and 1. So in the training data, this is what we're looking at. Once you scale it and transform it, and if you look at the actual data itself, notice that by and large it's between 0 and 1. Once you perform your fitting and transformation of your training data, notice that I'm emphasizing on the training data, then the data of the transform training data should only be between 0 and 1. Okay, it doesn't have to be 0, doesn't have to be 1, but it needs to be in that range of 0 to 1. There shouldn't be any values that's below 0, nor should it be any value that's above 1. That is not the case, however, when you apply this transform algorithm that you have fitted on the training data and apply it to the test data. In the test data, it can go below 0 or above 1. All right, so that's the one key part here. So looking at our original data is pretty much between -1 and 2. If you look at here, we have -3. And we have a 4. Okay, so obviously that these exceed the training data range. And if I provide it as a test data and transform it, if you look at test data, notice that it does exceed 1. It does go below 0. So that part is important. It's not a characteristic that it's not unexpected. It's something that you need to be mindful of. A max absolute scalar. So this works in very similar fashion, but scales in a way that the training data lies between the range of -1 and 1, whereas before we have 0 and 1. So for this is -1 and 1. Okay, so there is some underlying assumptions with this, is that it's meant for data that's already centered at 0. Okay, so all sparse data, but it is centered around 0. So that's the one part that you need to keep in mind. And if you haven't centered your data, then you're going to have a problem. It doesn't actually center it for you. Hence, this is part of the reason why we don't always use this. We use another method, which I will come to in a minute. So just a quick revision. What have we covered? We've covered standardization, and we have covered min-max, and we have covered max absolute scalar. I'm gonna lightly touch on these two, scaling sparse data. Quite often when you center sparse data, you destroy the sparseness structure in the data, and it's not exactly the most sensible things to do. Okay, so that's one thing to keep in mind. Sometimes, however, it makes sense to scale sparse inputs, especially if features on a different scale. Okay, so you can actually use max app scalar or max apps underscore scalar for that. Okay, but I won't go into details for this. Please refer to the link that I provide in this notebook. The other thing is scaling versus whitening. Sometimes it's not enough to center and scale the features independently, since the model itself can make further assumptions on the linear independence of the feature. So sometimes to address it, you do need to actually apply principal component analysis to remove the what we call linear correlation across features. Now, what do I mean by that? Sometimes between features there are correlations, and sometimes this is called multicollinearity, especially if it's actually very strong. We often apply decomposition using PCA to remove that. So that's the one thing to keep in mind as another arsenal in your toolbox for you to pull it out should you actually observe that. Right, normalization is the process of scaling your individual sample to have unit norm. Okay, and this is the actual algorithm itself, but there are two types of normalization: L1 normalization and L2. The L1 is basically what we call least absolute deviations, and the L2 is least squares. So one is using the absolute operator, while the other one is using the bracket square or least squares normalization technique. So let's look at the two different types of normalization, an example of them. Remember, L1 is really least absolute deviation. L2 is least square. So running the first one, this is normalized using the L2 norm, you get this. Okay. The reality is that you're not going to be able to really differentiate between L1 and L2. It's just the actual tools and methods of normalizing your data. Just let me remind you what normalization is. Normalization really is to actually compress your data, okay, scaling it to have unit norm. Okay, so that's the part that we are really aiming to perform here. There are other ways to do this. It does provide an LPI to fit and transform your data. Not crucial, but it's something that you can actually utilize and make use of. And essentially, this is actually same as this line anyway, so it's just a different way of doing it. Okay, the last part really is binarization. Feature binarization is really the process of setting a threshold and then converting your data using that threshold to decide whether it should be a 0 or it should be a 1. Okay, so meaning converting it to Boolean 0 or 1 or slightly different. Okay, so looking at this here, what we have done here is really just withdraw data, and using the binarizer, notice that it's become switching into 0 and 1. And what we do want to know is that what exactly is the threshold, and the threshold here is preset at 0, and if it's above 0 then it's a 1, if it's less than 0 then it's a -1. So that's if it's less than 0 then it's a 0, So that's really the whole idea. Of course, you can actually change the threshold and transform the data. Changing the threshold depends on the situation and the projects that you work on. You can actually do that, and notice that there are some variation, especially when it comes to this. 0 is above minus 0.5, hence it's actually 1. Right, how about when you're working with categorical features, non-numeric data? I'm going to show you two. One is called label encoder. Label encoder just encode your so-called categorical feature into a number. The process really is from the pre-processing library. You instantiate a version of the label encoder, and here I call label underscore enc. You can actually use another name that fits your purpose, and then you fit and transform the source data, which is this one here, and perform that. And this is just a code to illustrate that for Australia is 0, Hong Kong is 1, New Zealand is 2, Singapore is 3. And if I provide the test data of these in different order from this, and I want to see what happened if I encode, just transform my test data, what would the result be? Hong Kong is 1. Coming back here as looking at my map, yes, Hong Kong is indeed 1. New Zealand is 2. Yeah, indeed there's a 2. So I'll let you check out whether the Singapore and Australia has been transformed correctly or not. Okay, so this is really label encoder encoding your categorical value into a numerical number, but there's no meaning to it. Okay, so that's the part that's important. And one-hot encoding, or 1 of k, is actually converting it into a sparse matrix, which is just purely binary result, 0 or 1. So let's bring back source, so that reminder, and the actual SRC, meaning the number that we use to encode these categorical value. We have to import one-hot encoding and look at the so-called output or the outcome of it. Just remember, we have to instantiate first, and then the way that it needs to be taken in or transform the data, it has to be in a specific manner. Then we've performed the fit transform, and then when we print out the one-hot encoding, this is what it looks like. Notice that they're all unique. This is 1, 0, 0, 0, this is 0, 0, 0, 1, this is 0, 0, 1, 0, and 0, 1, 0, 0. They're all different. Okay, so that part is important. And if I perform a reversion, meaning taking one number and go backward, what I've done is that I've taken one-hot encoding, taking the so-called 0, slice, meaning this is row 0, which is this one here, and inverse transform it so that I can actually see what my original value is. The first value is actually Australia, and sure enough, it is Australia. And you can do another one for the last value, happens to be 3 here. So that's really the last portion of the basic idea I want to cover when it comes to data pre-processing. It is a very important step of building a machine learning model. Is really the data pre-processing. What I've shown you here is what it looks like before and with and without pre-processing, and before you try and scale your data and after you scale your data, what happened. And I also talked about the 4 different types. There is the standardization, mean removal. This is the most common type. You have the min-max, meaning scaling it to a range. And then you have the normalization and also binarization. And one part that is not highlighted here is labeling, encode your categorical value as well as one-hot encoding. With that, I'm going to stop. Thank you for watching and appreciate you following along the lesson. Alright everyone, we're going to look into variance bias trade-off. Variance really, it tells you how volatile your predictions are, and bias tells you how much you are off from the actual observation itself. These are really useful as a way to assess the performance of your machine learning model's accuracy and prediction. But there is a trade-off. There's as you try to reduce variance, usually bias goes up. As you try to reduce bias, variance usually go up. So quite often we call this generalization error. It can be decomposed in terms of bias, variance, and also noise. Bias is the term whereby it's an average error. okay, for different training sets. So you have the so-called on average, how far does it deviate from the actual observed data, whereas variance indicate how sensitive it is to varying training sets. And last portion, an item which is a property is called noise. It's a part and parcel of the data itself. The noise can be from the measurement or from the actual data generation itself. It is very common and something that you can't remove altogether. And bias and variance is what we call an inherent properties of estimators, and we usually have to select an algorithm and also the hyperparameters so that both bias or variance are as low as possible. One way to reduce the variance of a model is to use more training. However, as you collect more training data, the true function is quite often too complex to be approximated by an estimator with lower variance. So let's look at these. We import the usual library and look at the versions that we're using here. And this portion here is actually from the scikit-learn documentation itself. So this is to actually illustrate some basic concepts. Now, the basic concepts that we're trying to illustrate here is the degrees of freedom. And what you have here, this first one is just a degree, 1 degree. And this estimator function is 4 degrees, and this one has 15 degrees of freedom. What do I mean by degrees? Degree, quite often you can probably think of it this way or use it as an illustration. Y is equal to mx, so you have 1x. Degree 4 means you have x to the power of 4, x to the power of 3, x to the power of 2, and on it goes. Whereby degree 15 will be x to the 15, and then x to the 14, x to the 13, and on it goes. So you can immediately see from the illustration or explanation I've provided that one has only one estimator, independent variable, whereas the other, the degree 4, has 4, degree 15 has 15. Naturally, the degree 15 is bound to be a lot better at, well, it has a lot of freedom to actually explain or model the data, but you might have provided it with far too much degree of freedom and creates what we call an overfitting situation. Ultimately, what we want to do with machine learning algorithms is generalizing the underlying data, but with certain amount of noise. We also don't want it to actually explain every single data point. So looking at this chart again, let's visit this again. We have the blue dots are the samples. The orange line is the actual true function, whereas this, well, what color would you call that? Blue. Let's zoom in a little bit. Yeah, I guess you can call that blue. It's our model. It doesn't it doesn't approximate the actual true function well because there's just not enough degrees of freedom. Whereas this 4 degrees is substantially better. It's a lot closer to the actual true function itself. Moving over to the degree 15, what you have is that the degree 15 is so flexible that it goes through every single dot, or attempt to go through every single dot or every samples. And what happened is that, well, it basically doesn't generalize well at all. It perfectly fits the so-called sample, but when you actually move it to predict in a test situation, it will be terrible. Okay, and if you look at the mean square error, what you have here, it tells you the actual errors, how much errors each and every one of these are, and this is actually a substantially large errors comparison to the 10 to the power minus 1, 10 to the power minus 2 versus 10 to the power of 8. This is a huge number. Right, let's zoom out again. Okay, so that's really what I want to highlight there using those Python code. And I want to move on right now to 2 concepts. One is called validation curve, and we're going to plot the validation curve to help you understand that. And the other concept I want to cover is called learning curve. So let's start with validation curve. What exactly is validation curve? You probably will remember that we have training set, we have a validation set, and we have a test set. You can actually think of it this way. You have a portion of data for training, and then you have another portion of data called validating your data, and then you have one more portion of your data set aside for testing. Quite often, what you don't want to do is keep using the test data. Ideally, you only use the test data once. If you keep using it to validate your model, you ended up, well, can't really tell whether your model actually works well or not. So hence, we often have three sets of data. Bulk of it is for training, a portion of it for validating, and another portion for testing. It may be that you have it in 80% training, 10% for validation, and 10% for testing. So validation is really good for identifying over and underfitting. What you do is that you plot the training and validation scores versus the parameters that you are playing around with. So looking at these, again, don't be too concerned with the Python code. That's not the main point here. The main point is really this chart that I want to highlight. This is the main concept here. Training accuracy, remember, training is the data that you supply to your machine learning algorithm to develop your model. So it will learn from those data really, really well. So the blue line is the actual data itself. So as it should be, it performed really well. And ideally, in the real world, you have the validation curve really, really closely approximate the actual training accuracy. And what you have here is that the green line, green dotted line, is the actual validation accuracy. As you can see, it's actually really, really closely approximating, the training accuracy. What we have here is in terms of the parameter alpha, and what you have here is the R square. And looking at this, what you can say, conclude from this is that, hey, our model is pretty good. It's pretty good because it performed well in the training accuracy, in the training data, using the training data. It performed well, reasonably well with the validation data as well, and is at the high 92 to 93%. So that's really, really good. So that's what I would call a pretty close and pretty, double quote, perfect model. Let's look at another example. Let's look at another example right here. Now, looking at this is what we call a validation curve, and in this case, we are using a support vector machine. And again, you have the alpha parameter here, and over here you have the actual score, and this is the accuracy score here. Again, our orange line is our training score. Okay, as you can see here, the training score is really, really good, and in fact, it's perfect once you actually go to 10 to the smaller value of y. And when you look at the cross-validation score, which is actually validation score, what you can see here is that the blue line closely approximates our training line until around here where it drops off precipitously. It went from 10%, 20%, all the way to 80%, and then close to 90 plus and almost 100%, and then it drops off substantially. So what this is actually telling you here is that on this part, we have what we call overfitting. This portion is what you will call underfitting. This portion is overfitting. And the lesson here is that over here, we're not giving our model enough flexibility. Over here, we gave our model far too much flexibility. And this is the ideal range. How do I come to this conclusion? That's why I was actually using this earlier concept to illustrate. You have degree 1 being underfitting. We didn't give our model enough flexibility versus degree 15, far too much flexibility. That is really the point here, is that there's not enough flexibility here, much like our 1 degree. Over here is degree 15, which is why it's actually in the training portion, it's really perfect. But when it comes to the cross-validation portion, it is terrible. Degree 4 is around this range here. So that's really the purpose of validation curve, is to look at your hyperparameter or the parameter that you are playing around with and to assess, whether it's underfitting, just right, or overfitting. So that's the purpose of validation curve, and that's really what this explanation here is about. For very low value of gamma, you can see both the training scores and validation scores are low, and that's called underfitting. And the medium values of gamma will result in high values for both scores, meaning the classifier is performing fairly well, which is much like our degree 4 before. If gamma is far too high, again, gamma is actually this portion. Actually, that's not y, that's actually gamma. Sorry about that. It's too high, the classifier will overfit. This is much like our degree 15 before. What you can read here is that the training score is good, but the validation score is poor. So that's really what I want to cover in terms of validation curve. We'll cover a lot of concepts. When we come back, we'll dig into learning curve. Welcome back. In the previous lesson, we covered the concepts of variance bias trade-off as well as validation curve. In this lesson, we're going to go into learning curves itself. And with learning curves, it's different from the validation curve. How learning curve works is that it shows the validation as well as the training score of an estimator when and as you add more and more training samples. It is a tool to find out how much we benefit from adding more training data and also whether the actual estimators suffer more from a variance error or bias error, and this is really the tool for that purpose. Now, if both the validation score as well as the training score converge to a value that's too low with the increasing size of the training set, now in those situations you will not benefit from more training data. And let's look at an example. Let's start with a really good example. And what you have here is that on the x-axis you have training sample size. So as you increase, it's just moving to the right. And as you go up, you have a higher and higher accuracy score. So you have this black line here, which is called the desired level of performance. And training, the training so-called score start to come down as you actually start to add more sample size or more samples. And the test scores usually start from here and it increases as you add sample size. And what you have here is there is the convergence of the training as well as test data closer and closer and closer towards the desired level of performance. Now you may ask the question, say, hey, why is this score so high here whereby the test score is so low? Well, the answer is really simple. At this point, you don't have enough data. You didn't provide provide the model with enough training data. And when you have small sample size, the machine learning model or the algorithm will learn those small samples really, really well. But that may and quite often is unlikely to be representative of the population. So while the score using with the training data set might be really high, it's terrible at predicting for test data when you use the test data, because the small sample that you provided is not representative of the whole population. However, as you provide more and more data, the training score start to suffer because you have noise, start to have errors start creeping in. While your test scores start to improve because it's starting to learn, and as it see more data, it start to actually get a bigger representation of what really happens in the real world. Right, so this is an example of a good variance bias trade-off learning curve. The actual level of performance, be it accuracy or R score, achieved is close to the desired level of performance. The training and also the test, which is also called validation curve, are tight and converge to a similar level. So let's look at another one. This is one with a huge bias or high bias learning curve. High bias means it doesn't hit the mark at all. So in this case, you have low training and test accuracy score, which means it underfits the data. The actual performance level is far from the desired level of performance. So let's look at this chart. What you have is that this is the level of performance that we wanted, which is the desired level of performance. Your training starts low and it keeps going lower and lower. Your test score starts low and start to increase, but notice how far the gap is. So this is what we mean by high bias. There's a huge gap between what we desire versus what the model is actually performing at. So it's just below par really. So this is what's called high bias. So you can actually address this by increasing the flexibility of your model, machine learning algorithm model, by increasing the number of parameters, adding or creating new feature, or decrease your regularization. Now give it more flexibility. All right, let's look at another example, which is what we call high variance learning curve. Now in this case, both the training as well as test level just do not converge, or they're converging really slowly. The training as well as the test level are still very far apart. And this is what we call an example of overfitting. This is what it looks like. Notice that the gap between the training as well as tests are really very wide. You know, that this is what's called high variance. High variance basically meaning there's a lot of noise in there. We are just not modeling the noise very well at all. So where does the noise come from? Let's come back here. The noise comes from this thing. Your model is far too flexible, which is why it's it is whizzing all over the place, and there's a really high noise level, which is also represented by the high mean square error here, 10 to the power 8 versus 10 to the power minus 2. So coming back to our high variance chart, how do you address this? You can actually collect more data, reduce your model complexity, and also increase regularization. Okay, so that's the basic idea there. So in summary, what we look for is that we look for issues with bias and also issue with variance. These are the two main things that we look at. Right, I have more examples here which repeat the whole same exercise. Looking at this versus this, you have this is the validation. And as you increase your sample, it starts to converge really well towards 85%. And this is another one using support vector machine versus naive Bayes. Notice that the training is really high and cross-validations also converge to very high as well. Both are good. Of course, the support vector machine is better. So where do we go from here? I want to give you an exercise on learning curve. So this is an example of the learning curve. I won't go through and explain the code, but I do want you to actually play around with it as an exercise and play it with your Boston data. Okay, and just to repeat this whole exercise and to see how your learning curves improve over time. Okay, and your validation curve as well, and see how it performs as you increases the so-called or vary the alpha parameter. The whole idea here is for you to actually play around with the learning curve as well as playing around with the validation curve so that you can understand or develop a better understanding of how that works. Now, you might ask me, well, how do I actually play around with this? Well, start with the code. Okay, start to break down the code, start to vary some of the parameters. In this case, we are playing around with the parameters called alpha and the range that we are playing with, varying the actual alpha itself. And over here, we're playing around with the test size, the sample size, and number of split, the estimator itself, and really just to actually get a good feel of how it works. One way is to change the model that you use. In this case, we're using rich regression. You can actually use other type of regression as well. What we actually discussed before, robust regression, lasso, all of those. Play around with it as an exercise to actually help you to develop a better intuition and understanding of it. With that, I'm going to stop here and thank you for watching. A good day, everyone. In this lesson, we're going to go into cross-validation, which is a really important concept. Why do we do cross-validation? The answer is a really straightforward one. In the real world, we don't actually have what the perfect answer is, and that's our biggest problem. Without the perfect answer, without knowing what is the real answer is, because we can't really go and get the model answer and check it, we have no choice but to do multiple sampling, and through the multiple sampling we gain in confidence in terms of the understanding of the data itself. Cross-validation is one of those methods. What you can do is that you take, let's just say you have 100 data, you take 80% of it to train, and then you use 20% to test it. But there's only one, and you don't really have much in the way of confidence, because what you ended up having is only one outcome. And what we prefer to do is do many of these so-called sample of train and then test, sample, train and test, and ideally keep repeating it so that we start to actually get a better appreciation of the model, how accurate the model is, because we have a sample of the model's performance. So essentially we are actually performing as a sample of the actual sample itself. I don't know if that helps, but they just want to illustrate the concept here rather than taking one R-square or one accuracy score. We do a few so that we have at least a range of the likely performance of our machine learning model. So let's go through the cross-validation concept here. There are two here. One is called holdout cross-validation. The other one is K-fold. A test set should always be held out for final evaluation. The validation set is no longer needed when you actually are performing cross-validation. So in the basic approach, which is called K-fold cross-validation, the training set is split into K smaller parts. Smaller sets. The following procedure is followed for each of the K-folds. A model is trained using K-1 of the fold as training data. What do you do with the one? That one is actually our test. Okay, so the resulting model is validated on the remaining part of the data. Hence, it is called K-1. The one that we have minus of is our test set. So the performance measure reported by the K-fold cross-validation is then the average of the values computed in the loop. So looking at the holdout method, and you have the original data here, and then you have your training set and your test set. So you can say that this is K-1 and this is 1. So you split your initial data set into separate training and test data set. Your training data set will be for model training. Your test data set will be used to estimate its generalization performance, or to estimate how well it performed in a generalization way, or how well does it actually generalize in the real world. So a variation is of this method, which is this holdout method, is to split the training set to two, training set and validation set. So you have the training fold here, and then you have a validation fold here, and then a test fold here. So training is for fitting different models, is to train your model. The validation is for tuning and comparing different parameter settings to further improve the performance for making prediction on unseen data. And finally, for model selections. This process is called model selection, which is what we use the training for and validation. And finally, once we've chosen our model, then we go over to the test data to test our model to get a final approximation of how it will perform. Let's look at K-fold cross-validation. This is randomly splitting the training data into K-folds without replacement. The K- folds are used for the model training. The 1 fold is used for performance evaluation. This procedure is repeated K times. The final outcomes will be that we have K models and performance estimates, and you calculate the average performance, meaning taking all the accuracy information and average it, okay, based on the different independent folds to obtain a performance estimate that is less sensitive to the sub-partition of the training data compared to the holdout method. K-fold cross-validation is used for model tuning, finding the optimal hyperparameters value that you a satisfying generalization performance. Once we have found the satisfactory hyperparameter values, we can retrain the model on the complete training set and obtain a final performance estimate using the independent test set. Remember, we've always been keeping the test set and not touching it until the end. The rationale is behind fitting a model to the whole training dataset after K4 cross-validation is that providing more training samples to a learning algorithm usually results in a more accurate and robust model. And the common K is 10. Of course, you can go to 20 if you like, but the common one is 10. For relatively small training set, then you may have to increase the number of folds to, let's just say, 100. So this is the essential idea here. You have the original data set, you have the training set, and you have the test set. So you have your training fold, your test fold is always kept one side, kept here, and this is technically called validation. So you split this training set to 10 parts, okay, keeping the 10th here, the green one for validation, then the next one is the 9 for validation. So 1 to 8 and 10 is for training, 9 is for test validation, and then the next one it was 1 to 7 and 9, 10 is for training, 8 is for validation. On and on it goes depending on the K that you've chosen. There is a variation of this called stratified K4 cross-validation, and this is typically for unequal class proportions, and stratified typically is for classes, okay, not classification algorithm rather than regression. So in class proportions, let's just say if it's 30% of your data represent one class and the other 70% represent another class, so meaning you have a two-class problem, then it might be a good idea to perform stratified sampling, okay, so that the proportion of your data maintain the 37 split. Otherwise, you may have sometimes have a sample that only that sample happen to have data from the larger set, okay, and that will create a problem with your algorithm because it never learned the minor so-called populations characteristic totally. So that's really the whole concept I want to cover for cross-validation. I hope you have found it useful, and thank you once again for watching. Okay, in the previous lessons we've been talking about the basic concepts of cross-validation. So in this lesson we're going to go through some illustration. Again, I'm just going to cover some basic ideas. The example is adapted from scikit-learn. So the first concept I want to talk about is relearning the parameters of a prediction function and testing it on the same data is a methodological mistake, so don't do that. A model that would just repeat the labels of the samples it has just seen would have been a perfect score, but will fail to predict anything useful on yet unseen data. This is called overfitting and also an error and mistakes at all in that approach. So to avoid it, it is common practice when performing what's called a supervised machine learning experiment to hold up part of the available data as tests. The test set quite often is called X test, Y test. X is for, well, you provide the parameters. Y is what we call the so-called the test for you to actually look at the data that you feed into, which is X test, and see what your model compute Y as or predict Y as, and you compare your Y predict to your Y test to see how far apart it is. Right, in scikit-learn, a random split into training and test set can be quickly computed using this helper function, train_test_split. So we're going to make use of iris data for this purpose and then to fit a linear support vector machine on it. This portion is the usual, importing your libraries. And then from scikit-learn, we're going to import train test split. We import data sets as well as support vector machine. And well, instead of iris data, we're going to make use of the Boston data set. So let's just load that and wait for that to run. And we're going to print out the shape of it, which is 506 samples and 13 features. And the target, which is really our Y, is also 506. This is just telling you our version of Python. Okay, now we're going to split our data. Let's start with this portion here. Okay, so we are using the helper function, train test split, and we're going to have to feed in our, this is dot data, which is our X, our Y, and we're going to have to specify what size is our test data. In this case, it's 40%, which is that part here. And random state is just to help us to actually specify where do we start, or the random number, pseudo random number generation. And because it's pseudo, it allows us to also to actually set the starting point. In this case, we can use 0, and some people use 42. That's not important at all. And then this helper function will spit out this for you. It will spit out x train, x test, y train, y test. And you can also, well, actually if I do this, it's not going to show anything. So let me just print that out and print that out as well. And here what we have is that we're going to have a regression in terms the model called regression, support vector machine, support vector regression. And the cardinal is linear. These are our hyperparameter. And then we're going to fit our x train and y train data. And then we calculate what how would our this regression model perform when we actually look at it or test it on our test data. So running that, you can see that it's 66.74. That's the performance. So when you're evaluating different settings, also hyperparameters for estimators, such as the C here, which is C equal to 1, must be manually set for a support vector machine. There's still a low risk of overfitting on the test data or test set because the parameters can be tweaked until the estimators perform optimally. Now that means knowledge about the test set can be leaked into the model, and the matrix no longer report on the generalization formula. Hence, quite often people use this validation set here. So in our case, we've already explained this whole concept. The test set will be used for the final generalization test. So what we're doing here is this so-called K-fold. Okay, so what I've illustrated here, first of all, is the so-called estimator of your performance of the support vector regression. But again, this is only one time. So we have to go through what is called a cross-validation, which we mentioned before. We can actually chop it up to 5 or chop it up to 10 or whatever numbers that you like. So let's look at this inbuilt function. Again, it's a helper function called cross-val score. It actually performs the scoring for you. So this is the line to import it directly from scikit-learn, and this is again instantiating our model. Again, we call it regression to override the previous one, and we provide the cross-val function or cross-val score and provide the basic parameters that input parameters that it requires, which is the model itself, regression, the x data, the y data, and then we say we want a cross-validation of 5. So, and then store it in scores, and we print scores out, and let's have a look. This is computationally quite expensive, so it can take a while. Now, this is the output. Looking at this, the first so-called accuracy score is 77%. Second one, 72. Third one is 56. Fourth, 15%. Last one is 8%. I don't know about you, when I look at this, it doesn't give me any confidence whatsoever. The range is so wide, it's scary. Okay, yeah, so that's a problem. And as you look at the accuracy score, you can see that it's the error is larger than the actual mean. The beauty of Python really is that you can actually use these dot method and calculate immediately the so-called mean, and this actually calculate the standard deviation once you actually times 2. Should really be square, ain't it? Yeah, should be square. Yep, then it's 8%. Well, that's better. Why does it times 2? Okay, there's just discover an error there. By default, the score compute at each CV iteration is the score method of the estimator. Okay, so that part is important. Of course, you can actually change your matrix. This is, let me just tidy this up a little bit. The scoring is you can use negative mean square error. Again, we'll run that. Whereas previously, what was actually being calculated is R square, I believe, because we are running a regression. And this is mean square error. You can actually see the output here. So those are the things to actually keep in mind. So that's useful as a reference point. If you want to use R square, you can also change it to mean square error if you like. And there are a few others as well. F1 score is one of them. Now, when the CV argument is an integer cross-validation score, use K4 or stratify K4 strategies by default. The latter we already talked about. Okay, let's look at K4. What it does is that divides all the samples in K groups of samples called K-folds. All right, so of equal size if possible. The prediction function is learned using the K-1 fold, and the fold left out is used for test. So here's an example of two-fold cross-validation on a dataset with 4 samples. So we have NumPy imported, and then we have the model selection, and then we import K4. Our X is A, B, C, D, and we are creating two-fold. Hence, we provide the n split is equal to 2. And as you run this train and test, and you print out the actual result, this is what you have. So let me just explain what this actually means. Because the K4 is splitting in the X. You have 2 and 3 is what we call our train data. 0 and 1 is our test data. Again, we have 0 and 1, which is the next fold. 0 and 1, the next fold is 2 and 3 is our test data. So essentially, that's the basic idea of K4. And what we've done here is actually splitting them up. The final concept I want to cover is what's called stratified K4. This is useful for data where you have unbalanced class, which we again explained before. As before, it's essentially we import all of these from model selection, and the name of the method is called stratified K4, or the library or the package. So here we have X is equal to 1s. We're creating 10 1s, okay, and Y is 0, 0, 0, 0, and then the rest is 1. And we're performing what's called a stratified K4 and split our data into 3, creating 3 splits. So if you look at this carefully, what do we have for X? And let's run this so that you actually have a rough idea what it looks like. So let me just add a few things so that you actually have a rough idea what X looks like, or a rough idea what Y looks like. So what does that actually mean, and where does these so-called numbers come from? Now, the essential idea here is this. These are index. Okay, so this is index 2, index 3, all the way to index 9. You have the index 0, 1, 4, 5. So essentially what we have here is that this portion here is trying to maintain the uneven sample class of, for Y, you have 4 versus 6. So when it actually is conducting this stratified K4, what it has done is this. It takes the sample 2, which is 0, 1, 2, 3, and then the rest from here. The next one is 0, 1, 3, 0, 1, 2, 3. So it took 3, and then the rest is from here. And then 0, 1, 2, 0, 1, 2, and then 3, and then the rest is actually 4, 5, 7. What you have here is this is the X, which is the training data, and then on your Y part you have 0 and 1, which is your 0 and 1. You have a 2 there, 0, 1, 2, which is also 0 is also included. 3 is 0, 1, 2, 3. 3 is also included. And essentially what you might not be able to see the actual chaos in all of this pattern is that stratified K4 has actually split your data so that the Y, this class here, the 0 class, is represented in each and every one of the slices. So be it this one, there's 0 represented in training and test. Be it the second one, 0 is represented in both the train as well as the test. And even also on the last one, 0 is represented in the train and test. This is the whole idea of stratifying K4 so that the actual minor class is always represented, and basically the so-called, as close as possible, the proportion is represented as the underlying data itself. All right, so let's look at this last one here. Last two samples that we have. We are looking at support vector machine. We're creating what is called pipeline. Essentially, pipeline is just you are chaining a whole few operations together, kind of like a workflow. Okay, so if you just imagine with me, you have an assembly plant. There's an assembly line. There is, if it's a car manufacturer, you have in the beginning maybe the so-called body, and then followed by installation of the door, followed by the installation of the, let's just say, windshield. Okay, so you have three things in order. So what the pipeline here does is exactly the same thing. You have a pipe. This is the name of the instance that we're creating. We're creating this make pipeline, which we actually imported from scikit-learn. Let me run it at the background while I explain this. First of the whole method is standard scalar. Standard scalar, as you probably would recall, I hope you do recall, is under data pre-processing. And then we have PCA, which is principal component analysis, which we haven't explained. Nevertheless, think of it as this way. PCA, what it does is that it actually, well, summarize your data. Let me just use a very generic concept here to illustrate what PCA is, but we'll go into that in a bit more details under unsupervised machine learning. What PCA does is that it actually slices your data in the so-called dimension or the angle that actually that helps to explain the greatest variance. So it does it in one direction and then followed by what we call perpendicular or orthogonal, if you prefer mathematically inclined. Then the next axis explain where the greatest variation is. So it will keep doing that. So in this case, we are just looking at two components, hence n equal to 2. And then the third, much like what I mentioned in terms of assembly plan before, is the windshield, is our support vector regression. So we're chaining three operations together and store in this thing called pipe underscore SVM. And we perform this fit of our data, and then we perform the predict, and then we actually print our score. So in this process here, it's only one score. You only have one test accuracy score because we didn't really do any cross-validation or K4 cross-validation. And this is where the piping part is powerful, that allows you to actually perform this cross-validation using one simple line. So here we import the cross-validation score. We provide the estimator as the pipe CSV, provide our train test data, and then we specify how many cross-validation we want to do, which is 10 in this case. And as you run it, notice that we have the CV score of 10 CV score, cross-validation score come out. We can also calculate our mean and as well as standard deviation. And here you can see in terms of what the CV accuracy looks like, the mean as well as the standard deviation. What I might do, let me come back to the original part here. Rather than variance, I'm just going to leave it at standard deviation and then just run the whole thing and run all on its own. Okay, so that essentially cover everything that I want to cover in this lesson. We talked about cross-validation, K4, stratified K4, as well as the whole out method. The difference here with this lesson is actually illustrating the actual code itself. We also learned something new in terms of the basic idea of the K4 as well as stratified K4. We exposed ourselves to new function called cross-validation score, and also this new function called train test split. We also expose ourselves to something new called pipeline. That's a new concept that you've come across for the first time here. And that's pretty much all that I want to cover. There's a lot of ground that we've covered. I hope that you found it useful. Thank you. Thank you once again for watching. right throughout this whole lesson. I look forward to seeing you in the next lesson. Well, welcome back everyone. In this lesson we're going to dig into logistic regression, a really key concept and machine learning algorithm that is used widely both in machine learning as well as deep learning. We want to start from this perspective at this point, also as an introduction, a fairly straightforward introduction to a classification problem. Up to this point, so far we talked about has been a regression-based problem, and I just want to use this concept to ease into classification-based problem. Now, just to help refresh your memory, classification really is splitting out into the so-called classes into two different camps instead of continuous like regression problem. So classification could be whether it's a cat or a dog, alive or pass on, whether it's binary meaning 0 or 1, and Boolean and the likes. So that's really what logistic regression is for under the umbrella of classification-based problem. And so looking at the resources that are provided for you here, please feel free to make use of them. It's resources for you to deep dive just to learn a little bit more about logistic regression. Now, logistic regression is what we call the go-to linear classification algorithm for two-class problems, which I mentioned before, whether it is blue or green. Probably not the best example, whether it's cat or dog. So that's the two-class problem that we're talking about, whether this applicant or this creditor's person who is applying for loan is likely to default or not. So that's really where the two-class problem comes in. The beauty of logistic regression is that it is really easy to implement, easy to understand as well, and gets great results on a wide variety of problems. Now, this is even when the expectation the methods has for your data are violated. So that's really the beauty of logistic regression, is that it's robust and it's easy to understand and easy to explain as well as a result of that. At the core of logistic regression is the logistic function. Another name for it is called the sigmoid function, originally developed by statisticians to explain the growth, population growth in ecology. How it works is that is what we call S shape. The growth originally is quite slow, and then it accelerates or rising really quickly, and then it plateau as it actually starts to reach the so-called maximum or saturation. And this really gives you that quintessential S-shaped curve that can take any real value number. And this is really the formula to use to describe the sigmoid function. So we're going to plot this out just for you to visualize. We're using the basic library packages. And if you look at this sigmoid function, I'll just explain a little bit about the code. We're using NumPy, breaking the space from -6 to 6, breaking it into 1,000 steps. And this is the sigmoid function based on this formula here, 1 divided by 1 plus x to the power e to the power of -x, and then plotting the actual title. So we go from -6 to 6, breaking into 1,000 steps, hence it looks like a smooth line. And if you take note of the so-called value itself, as you tend, or as x value, which is the input value, tends towards negative infinity, as the number gets smaller and smaller and smaller and smaller, the whole sigmoid function gravitates towards 0, but never ever gets to 0. It's just start to what we call ended up, well, close to 0 is probably the best way to say it. And if you look at the other side of the equation, is that as the number gets bigger and bigger, as the input number, which is x, gets bigger and bigger, it tends to the limit of 1. Never quite reach there, but it gets closer and closer. So that's really quintessentially the sigmoid function. Right, okay, so I'm going to skip these details and start looking at how do you actually learn the logistic regression model. This is really another way of saying how do you actually estimate the coefficients, or how does this algorithm actually learn using the data set that you provide. Typically it uses what we call maximum likelihood estimation. It's a common learning algorithm. The ultimate idea here is that it tunes the coefficient until your model predict a value that is really close to the actual based on the input data you provide, which is the training data that you provide. The intuition for maximum likelihood is that a search procedure continuously seek the value for the coefficient that minimize the errors in the probabilities predicted by the model to those in the data. So if you're wondering what I'm talking about, coefficient here, we come back to this. This is the logistic regression formula, the beta 0 and beta 1. If you recall, if we're looking at linear regression, beta 0 will be where the x intercept is, beta 1 will be the slope. Okay, let's move to make use of scikit-learn. This is really the core part of this lesson, is how do we make use of scikit-learn to build our logistic regression to learn from the data to perform prediction. Okay, let's start with the basics. So start from importing logistic regression from scikit-learn. This is the data set. Let me import the data set. Okay, so this is our data set. And let me just print it out on screen. This column here is X. This column here is Y. So we're gonna restore it accordingly, okay, whereby the column 0, which is this one here, the data will be stored in X, and column 1, which is this column here, will be stored as Y. So you will call this dependent, and X is our independent. So we're trying to use the information that's provided in X to predict what are the possible outcome, which is Y here. So plotting X, just to show you that I am referring to the first column here as X, and Y likewise will be in the form of 0 and 1. And this is what we are referring to earlier as that this is a two-class problem, which is also binary in nature. Either it is 0 or it is 1. Okay, so we're gonna, first thing, as you recall, we need to instantiate our model, and this time around we call this classification underscore LR. LR stands for logistic regression. These are the hyperparameters that we actually provided. You can use others. For now, this is just one of the many hyperparameters that you can use. I've chosen to use this to illustrate this concept. Please feel free to play around, tuning and changing the number, just to actually help you to actually get a understanding of it. So the next step then is to actually fit the problem. Right, so what is it actually saying here? So future warning, default solver will be changed to LBFS, FGS in 0.22, specify a solver. So in this case, what it's telling us to actually make use or specify a solver. Let me see, can we actually provide that here? It doesn't actually state that those options are here. So what we can do, and I'm just taking a little bit of a sidetrack here to illustrate to you how do we actually solve this problem. Okay, so scikit learn logistic regression. Okay, so this is all right, so multi-class option set to OVR and uses if the empty is multinomial. Currently, the multinomial is supported only by that or that. We specify penalty, tolerance C, fit intercept class where random state solver is equal to 1. What we can do here is that we can change our solver to LBFGS. Essentially, that's what the warning is saying. Make use of this. There are other ones as well. Please feel free to actually make use of them or just explore to understand it a little bit more. There are different types of solver to under the so-called maximum likelihood to actually help you to find the minima in this case. That's a little bit heavy on the math side, which I don't really want to go down to. but ultimately this is actually saying in the future, if you don't specify it, you're going to continue to get the error message. To remove the error message, specify. So in this case, we are using LBFGS. So we're having instantiated our classifier, having fit our data. The fitting part really is training our data to allow our logistic regression to learn the patterns of the data. Then the next thing is asking it to perform a prediction. Now, before I start going down to the prediction part, I want to come back to our data. So we have here when x is -2, y is 0. When x is -1, y is 0. It continues on until when x is equal to 3, y is still equal to 0. When x starts to x, but we don't really know what happened in between, or what are the so-called segregation that comes in. All that we can tell is that the next time we have a data value at 7.6, y is now 1. So somewhere between 3.06 and 7.6, the switch, all right, y went from 0 to 1. Unless we get the more data, that is what we call our gray area. We don't know when the actual switch happened. There are two ways to solve this problem. One is allowing the algorithm, in this case logistic regression, to find that segregation, or we can specify it ourselves. Okay, for now we're going to allow the algorithm to learn where the separation comes in. Ideally, we try to allow our algorithm to find that separation. So we're going to run that prediction now. Naturally, we provide all of the data to learn, for the algorithm to learn, and we're using the same data for it to predict as well. Okay, if we look at the so-called prediction, it learned exactly what it was before, or the actual training data, and we would expect it to do so. Because we provided the data. It's fairly clean data. It's not a very complex data with a lot of ambiguity. Hence, logistic regression learned that really, really well. Now, there's one so-called additional function that I want to introduce you to within logistic regression that is really helpful. And you will be able to see this come out again and again in classification problem. It's especially pronounced in right now, especially in this space, deep learning space, is in the visualization or computer vision problem. It would tell you the probability of this item, this image is a cat. It would tell you it's 80% or 90% confident that it is a cat. All right, so this is the same here with our data set. For each of these, is basically telling you is 99.8% sure with its prediction. And you notice that the confidence start to drop all the way down here, and then it start rising, but it drops again. It continues to drop, I should say. Whereas the confidence of it being a 1 is really low, and then it switch over and continue to increase towards the later part. Where the actual part that is not shown is after between the 5th and 6th value. So 1, 2, 3, 4, 5 between the 5th and 6th. You notice that this is the portion where it is least confidence. Interestingly, this number dipped as well. I'm not too sure why. It's something pays to actually dig in a little bit more. But for now, you can see that this split is actually here, where this portion where y split changed from flipped from 0 to 1. There are more resources here for you to look at. I want to do another classification exercise here. Now we have a second set of data where you have x 0.2 up to 0.1 where it is 0, but once it goes above, let's just say 1, it goes to y becomes 1. So any value that's pretty much right now, as you can see here, is when x is 0.4, y is 0, at least from the data that's given to us from 1 onwards, y is 1. So let's just run that. Again, we split and prepare our data to x and y, and then we instantiate and fit. We do need to actually provide a solver, LBFGS, and then we fit our data, and then we conduct our prediction. Right, so it's a bit hard to tell how well the prediction is, and if we actually compare, stack it up with the prediction versus the actual, you can see that it actually, well, the predicted value exactly matches the so-called original, the ground truth. So essentially, you can tell that the logistic regression has done really well. It's been able to actually predict the value exactly based on the training data that's given to it. Now let's take it one step further and play around these so that we actually understand our model a little bit more. Let's add a cell here. I want to actually continue to run prediction. So let's see if we can actually, yep, we can hide those. Let me just continue to hide these so that we actually have enough space to view all of these. Because these are essentially our data, as you can see here. So up to 0.4, y is 0. So we're going to run these. Okay, so remember our classifier, logistic regression, and then we conduct our prediction. We provide the numbers being 0.4, meaning our x is 0.4. Don't worry about the reshape, is exactly as what we have done in the past, just to actually tidy up the data so that the scikit-learn can actually take that as an input. So let me ask you this question. If it is 0.4, what do you think the outcome ought to be for y? Do you think it's a 0 or do you think it's a 1? Have a think about this. What does your original data tells you? So what do you want your models to do? Okay, take a second to think about that. Okay, so if you say 0, then, well, I will agree with you because our original data set pretty much say is 0. So let's just run that. Okay, good. Our model performed as what we wanted to perform, 0. Okay, so what about from time to time, we want to actually test what we already know the answer is, just to ensure that our model or our machine learning algorithm here really actually learn the right thing. So if we put 0.2, we have lots of 0.2. It ought to be and should be 0. So if we run 0.2 and we get 0.2, then, well, it's behaving as we expect it to behave. So let's go to the other end. Now, if I say 1.5, say, it's around there, then it should really be 1. Yes, and it does so. Okay, so this is the part whereby, all right, my data has roughly performed and behaved as I expected to behave. 1.3 is also 1. So I have some confidence now. You probably want to, test your model a lot more than what I've just done here. That's part of the tester's quality assurance role, is to just make sure that your model behave as it should be. And the next step that I want to do now is that I want to find where that flipping point, or where that point whereby y when is it that y flip from 0 to 1? Under what x input? So between 0.4 and 1, there's actually quite a big gap. So let's have a guess. Do you think 0.6 will give you 0 or 1? Okay, between 0.4 and 1 is about 6 steps. 6 step meaning 0.5, 0.6, 0.7, 0.8, 0.9, 1. So there's about 6 steps there. I'm not sure. So if I say 0.6, maybe it should still be 0. And yes, it does. What happens if it's 7? It's 1. What about if it's 8? Okay, switch over to 1. Of course, if it's 9, it should be 1 as well. So now I know it's between 0.7 and 0.8 value of x. You're actually getting the y flipping from 0 to 1. Why am I doing this exercise? This exercise is to help you to actually get a gauge of a couple of things. One is that, what did your algorithm learn? Number 2 is that you want to see how accurate in terms of its predictions is, and you want to see its behavior as well. This should, doing this kind of exercise help you to get become more familiar with the algorithm for one, 2 is to understand how it behaves, and how far does it deviate from your original data. Of course, this data is fairly clean, so it's easy to illustrate, but once you actually start to develop more complex model, you probably want to still do this exercise so that you can actually see where the actual decision, that boundary comes in. Okay, so really with that, I'm gonna stop. Thank you once again. We've covered a lot of ground under logistic regression. Using these foundations that we've learned here, I know I didn't dig into the math, but I also didn't talk about the stochastic gradient descent, which I think we'll park it under another day, another topic to talk about. For this, I just really want you to actually get a grip and understand how logistic regression works, how to model it, and how to perform prediction. And with that, I'm going to stop now and thank you for watching. Welcome back. In this session, we're going to go into a classification-based machine learning algorithm. This is really a start of a multi-part contents pertaining to classification. We will start with a bit of data preparation so that we can actually redefine this into a two-class, meaning a binary yes or no problem, followed by looking at the different performance measurement, much as we did with linear regression. We need some way to measure the performance of machine learning model, as in how well has it performed. And some of the different type of performance matrix we're going to make use of will be the likes of coefficient matrix, and then we'll look at different ways of pulling the lever to improve whether be it precision that we're interested in, or recall, or combination of the two, such as F1 score. So there is actually a trade-off between getting your precision right as well as the recall, and what happened when you actually set a high precision. We also look at different performance metrics such as ROC, and finally we'll look at another model, another machine learning model or algorithm to as a benchmark or comparison. The first thing I want to give a shout out to is Geron's books, Hands-on Machine Learning with Scikit-learn and TensorFlow. He has two books out. This is the earlier version, and this is the second version, which includes deep learning contents in there, such as Keras as well as TensorFlow. These are fantastic books. Geron happens to be one of the author for Scikit-learn as well, so he does write it in a manner that's really easy to understand. So I strongly encourage you to, if you want to expand your understanding, do dig into his books to actually develop further intuition and understanding. So this is, I'm not too sure if I say his name correctly, Aurélien Geron. He is French. Those are the two books, and this is just out in September 2019. Right. Of course, naturally, you can also go to Scikit-learn itself for some of the introduction on classification-based machine learning as well. So a little bit of the definition front. Let me just set the stage. We are looking at supervised machine learning, and specifically in this segment, we are looking at classification-based problem. So it can be two class, meaning whether it's a yes or no, or more classes or multiple classes. We'll look at multiple classes in the future. For now, we're looking at two classes and then build upon that as time goes on. Another way to think of classification-based problem is that it is discrete, meaning 0, 1 or 3, 4, or country names, whether it's Hong Kong or not Hong Kong, such like, as an example. The alternative, or the comparison or something different to that, is what you would call a continuous problem. Those will be linear regression-based problem. Okay, so we've seen regression-based problem where you are dealing with continuous variables. Those are what you call regression problem. So in this segment, we are looking at specifically classification problem. Now, the database or data set that we are playing with to develop our understanding is the MNIST dataset. Is developed by LeCun, okay, one of the early pioneers of deep learning. So this is his database. Okay, so there is 70,000 examples here, and quite often people split it into 60,000 training and 10,000 as test examples. So other things to keep in mind is that you can actually go through his website. You can look at the different errors, look at the different machine learning algorithms that he has tested, the accuracy, neural nets, support vector machines, and on it goes. It's really a great place for you to actually, as a starting base, to continue to tune your model to compare it against the state-of-the-arts. All right, so with that set as a platform, in the next lesson, we will start going into getting the data and playing around with it until we actually get a better understanding of it. So the next stage is really data preparation. I look forward to seeing you in the next lesson. Okay, in the previous lesson, we set the stage just to understand the actual tasks that we have at hand. In this lesson, we're going to look at preparing our data preparation, downloading our data so that we can actually start to play around with it. So for a start, we're importing NumPy as well as scikit-learn, and we're going to make use of the dataset called MNIST. We're not getting this from scikit-learn itself. It's already been deprecated. So we are making use of the library called Fetch OpenML, which is under the scikit-learn datasets, and we're actually getting it from the MNIST dataset itself. It is based on an open ML. So let me just show you scikit-learn OpenML under dataset. So you can actually come here and everything is actually extracted directly from the OpenML itself. So if I go over to openml.org, it is a public repository, so there are a whole lot of data there for you to, of course, for your hackathon, and yeah, there are really a lot of data for you to, well, 20,000 data sets for you to actually play with it. Okay, so strongly encourage you to make use of this. This is one place for you if you're looking for data, one place to actually look for it. We'll run this. We are looking at specifically the MNIST 784, and takes a wee while to download this. It really depends on the internet connection that you have. Of course, it depends on the server side as well. Typically for mine, it takes somewhere between 1 to 5 minutes. It does depend on the so-called size and the speed of internet. Right, the data has come through. If you're not familiar with Python, let me just quickly explain. When you see an open bracket like this, it tells you that this is in the form of what we call a dictionary format. For dictionary format, the data comes in what we call a key, and then the data itself. So in this case, the key here is data, and then followed by the actual content, which is the data itself. Followed by another key, target, and then you have the array, and then you have the feature names, and then followed by a whole lot of pixels. So let me just scroll down further all the way to the end. I just really want to show you at the bottom of this, it provides some descriptions on who the authors are, also other details, talk about the ID, the name, the version, and yeah, on and on it goes. So this is one place that you can actually refer to for more information pertaining to the MNIST datasets. So as I mentioned before, this comes in the form of a dictionary format, Python dictionary format. It comes with key and the actual data itself. So for now, I'm just going to minimize this because it takes out a lot of real estate. And we're going to just drill into specifically the data itself. So for here, I'm looking at the length, meaning how long is our data. It comes back, as you can see, that there are 70,000 data. Right, couple of things we do want to do is visualize our data. The actual raw data, which is also features, is going to be stored in the variable called x, and the target, which is the classes that we're interested in, will be stored in y. So let's run this. Okay, You don't see anything because we actually didn't generate any output. So let's visualize the X itself, and you can see that it comes in the form of an array. Doesn't tell you much. We'll come back to the shape itself. So let me just pull this up. Let's extend on this. And you can see that based on the shape, it's telling you that, well, we have 70,000 rows of data. And each of these data points has 784 so-called, it actually is this number here, 784. It's actually 28 by 28. Let me just show you. 28 multiplied by 28 is 784. It actually is pixels, but represented by number. Right, the next thing we want to look at is what is y. Okay, probably the first thing I should tell you is y. Okay, it comes in this 50. It's actually 0 to 9. The MNIST data set really is actually a handwriting data set. Okay, and let me come back to the actual MNIST database. Okay, it actually is a handwritten digit. Okay, and it's represented by a 28 by 28 matrix, and it actually is representation of the actual so-called handwriting itself. So let me just pull up data set. Okay, so I'll just pull up some images just so that you can actually understand. So this is what it looks like. So these are a whole lot of handwriting, and we have 70,000 of it. And that's the first thing. Second thing is that we have, these will be called the X, all right? And what is Y then? Y is actually telling you the actual ground truth value, which is 0, 1, 2, 3, all the way to 9. So let me illustrate this from our data here. Okay. There's one thing that we need to do before I go on to the illustration. We do need to prepare the data. The first thing is that notice that these are Python object. Now, when you get it in the form of Python object, you do need to prepare your data a little bit. Now, being Python object is a bit problematic for us. It basically means that they are strings. What we really wanted is that the y to be in integer, because 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 is really integer. So we do need to convert them to integer. What I've done is actually converting it into float. It doesn't matter whether it's integer or float. Either one, it's fine. I prefer to work with float because I'm more comfortable with it. Although it does take some more memory, but in our case, it matters not so much. Just to actually get a little bit more understanding, let's look at X, the last value of our data, and I want to see if which one of these looks X69999 looks like. What exactly is it? Well, you're kind of out of luck. So when I open it up, and what you can see is that, can I open this completely? No, I can't. What you can see here is that, well, there's a whole bunch of numbers, which is rather difficult to visualize. Okay, so we need some way to actually visualize that. Y happens to be a 6. Okay, that's the actual ground truth value. What we want to see is the corresponding raw data. What does it look like? And, well, don't worry about the shape of Y. We already know that. What I'm doing here is that this is actually a shortcut for me to visualize the actual data itself. When I say visualize the data, I mean visualize X. I've written a simple helper function called viz, and the n is basically the number that we provide in it. So let me just run the code. It's probably easier for you to get an understanding of what this function actually works. Recall this number here, the 69999x. It is a 6. In order to visualize that, instead of looking at something like this, which we can't make sense of, I plot this in the form of image and the form of pixels like this, and you can see that it actually is a 6. And by the way, it's 28 by 28, which is why we have 784 pixels for this. Looking at this, immediately, I hope at least you can understand the linkage now. You have the raw data, which is this one here, handwritten 6, and the actual ground truth is the number 6 itself. We have a whole lot of data that looks like this, handwritten data, raw handwriting. Of course, there's a massive variation of different people write the digits differently. You notice that these are probably right-hander, these are probably written by left-handers, and you can see all the various types of handwriting represent the digit itself. With our human brain, it's very easy. We are used to looking at these. We've seen thousands and upon thousands and millions of this type of handwriting. We can actually decipher whether that's a 6 or whether that's an 8. We can tell. But when it comes to machine learning algorithm, it cannot tell until you've trained it with examples. So what we are doing here is that we have 70,000 of these kind of samples. We're going to give a portion of it, in this case, roughly 60,000, to train the machine learning algorithm. And of course, if you're just training it without telling it what the actual answer is, it will still be confused at the end of it. You need to give it some sort of truth for it to learn what is the actual real value is. So we need to actually feed into it this handwritten digits. We also need to give it the answer. So basically this whole first row is 0. When we actually feed these data into the algorithm to train, we call it fitting. We also need to give it the corresponding answer, which is in the form of y, the variable y. So this whole lot is x, y is our answer, the truth. And this is another example. Y 1000 is a 0. Let's just visualize what 1000. By the way, this 1000 is the index, okay? The 1001 number is actually a 0 in this MNIST database. The reason I say it's 1001 is because, the reason I say it's 1001 is because Python start counting at 0. Hence, when you see 1000, it's actually 1001. All right, let's do an exercise again just to develop a little bit more understanding of our data. I've explained quite a fair bit, but it's good to actually do an exercise to actually understand a little bit further of the database we're working with. I've given you an example here, which is locating the number 4 and plotting the image. I mentioned before, we need to look at the type of data. It's a NumPy, so it's fine. It's essentially, we already converted it into a float. The next thing is that you can use y is equal to 4. It will come back and tell you with each index, which is actually the true meaning yes, it is a 4, false meaning no, it is not a 4. And we can make use of NumPy. There's a helper function or method called where to return to us all of the indices or index that represent that they are 4. Okay, so what you have here is a list of where 4 where is 4 in the whole data set. Index number 2. Okay, if we start counting, let me just show you. This is 0, this is 1, this is 2. So number 2, index number 2 technically is the third letter in our data is actually a 4. All right, and on it goes. Now, since we know 69977 or 69,977 is a 4, we can actually visualize it, test it, and then next thing we do is that we can visualize it that way, or we can use our helper function using this. Essentially, what I've done here is that I'll take the raw data of X, reshape it into a 28 by 28 matrix, and install it in this variable, and asked the matplotlib image show to plot it to give us the letter 4. I've used a helper function to shorten this whole process so that we actually can visualize the 4 right away without worrying too much about the code. Right, we've covered a lot in this ground, especially if you're not familiar with Python. This is probably quite a lot to take in. We talked about what is the MNIST datasets. what does it look like in terms of its actual structure. It's 28 by 28, so hence it's 784 pixels. We have the raw handwritten digits. We also need the ground truth, or the answer of what that raw handwritten digits is. So if I have a 2, handwritten 2, we need to tell the algorithm what the actual answer is, which is 2. So that's where y comes in. The rest of the whole exercise is just really so that you can actually visualize from the data how do you actually see that it is what it is, which is why we actually have written a helper function to do exactly that. All right, with that I'm going to stop. We've already done an exercise, and when we come back we will look at another aspects of data preparation. Welcome back, and what we've done so far in the previous session is to actually prepare our data in such a manner whereby we can actually start to build our machine learning model. In this segment, we're going to look at splitting our data into training as well as test data. The first thing to keep in mind is that the original MNIST dataset, which is provided by Yen LeCun, is separated into 60,000 training set, as you can see here, and a test set of 10,000 examples. Now, of course, there are larger data set, but for the purpose of our exercise here, we have 70,000. Now, it's a question of how do you actually split these data into 60,000 training and 10,000 test. Right, so the description here also highlighted there are a split of 60,000 training and 10,000. But in our case, however, when the data came through, let me just come back up here, they came in 70,000 in one go without actually having the data separated into training or test. So we actually have to do the post-processing ourselves, and by splitting the data into training as well as test set. I'm going to highlight two ways to do this. The first way is to actually just make use of the scikit-learn train test split, and actually splitting your data by providing your x and y, which we've prepared beforehand, and specifying the actual test size and shuffle our data. Of course, if you work it out, 10,000 divided by 60,000 isn't exactly 20%, is only 16%. So it's this is only a close approximation of the 60,000, 20 and 10,000 split. The alternative method, if you want to be closer and to the actual 60,000, is to do it this way, method 2. Right, so we specify 60,000 and store this in this variable called num_split, and we split our data to everything up to 60,000, and from 60,001 all the way to the end, and repeat likewise for y as well. And basically this first portion will be stored as train, this second portion will be stored as test, this first portion will be stored as y train, this second portion will be stored as y test. And typically what we do is that we do shuffle the training data set. This ensures that the training set is randomized and your data distribution is consistent. Don't do that for time series data, however, because you need that sequential relationship when it comes to time series data. Right, how do you actually shuffle the data set? We import from NumPy, and we use this function called permutation under random. So basically we're just shuffling it, and this is the shuffle index, and then basically instead of 0, 1, 2, 3, 4, 5, for example, if you have 6 data, you just use this permutation and shuffle it into maybe 0, 6, 3, 2, 1 or something of that sort. And this index essentially specified so that you actually store it in the X train. So basically this is actually rearranging your data in such a manner that it is actually shuffled. Okay, having done that, we're going to go into our next step. Now remember, our data comes in the form of digits, Digits means it will go from 0 all the way to 9. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And the first step, however, is that we are trying to perform what it's called a binary classifier. So binary classification. Now, naturally, that is not a binary classification whether it is on or off, because we have 10 digits, 0 all the way to 9. So to convert this to become what's called a binary problem, there are a few ways to do this. We can actually take, for example, numbers that's less than 5 is 0, numbers less than greater than 5, meaning 6 all the way to 9. 5 to 9 is 1, 0 to 4 is 0. You can do that as one way to do that. The other manner is what I'm going to show you is that I'm going to convert everything that is not a 0 to a different number. Okay, so basically this is to simplify our problem. We will make this an exercise of whether it is a 0 or non-zero, so hence making a two-class problem. So all the numbers where it is 0, we convert it to true. Okay, right. And likewise, we do that for the test. So by doing it this way, we're not touching the X data, meaning the features. We're only converting our test data. So let me just highlight this a little bit, just so that you have a rough idea what I'm talking about. Notice that we're just looking at the last two here. Okay, so we are showing the last two of this whole series of y value, of y train value. And you can see that the last value is indeed a 0, hence it is converted to a true. The value before that is not a 0 value, hence it is false. And for all of these, we do this, basically we repeat this whole exercise for the whole 60,000 training data that we have for y train, and store it into this new variable called y underscore train underscore 0. Hence retaining, not destroying our y train, and keeping it as it is, should we want to actually perform more experimentation on that part, while we store the data, the modify or transform data into this new variable called y underscore train underscore 0. And we of course repeat that for y test as well. So let's run our first machine learning model. Essentially this is a linear classifier. It could be a support vector machine or logistic regression, basically using stochastic gradient descent training. So let's start with this. We are importing from scikit-learn linear model library and import the SGD classifier. And we set our random state to 0 so that we all have the same starting point. And basically right now, all that we wanted it to do is actually fit our training data. We have our X-train. Remember, X-train was not being modified at all, so we kept it as it is. Where we actually make the modification was in the actual Y-train, and since we actually anything that's 0, we convert it to true. Anything that's not 0, we convert it to false, and store that in this variable called one underscore train underscore 0. So let's run a prediction. First thing we want to do is we look at the index number 1000, and what this is actually is, as you can tell here, it should be a 0. Okay, if our model is trained correctly, it's discerning enough, it's generalized enough, it should be able to actually predict that this is indeed a 0. So we supply the feature, which is our X, and perform our prediction using the classifier that we've trained, which is the COF here. Let's see how well it performed. Okay, good. That's a good start. It actually did predict that correctly. And let's try another one, viz 1001, which you can see here, this is clearly not a 0. Okay, and now let's see if our predictor, our classifier, is able to actually say and predict that this is indeed not 0. And sure enough, the answer comes back as false. Now, of course, this is not a very scientific way of testing how robust and how accurate your machine learning model is, because you kind of like have to do that for all 60,000. Even then, you still don't know whether that's actually a robust model or not. So when we come back, we're going to look at performance measures using a few metrics and different way of evaluating our machine learning model to see how what is its efficacy. Okay, meaning its performance, how well does it perform in test data. With that, I'm going to stop. Thank you for watching. I look forward to seeing you in the next lesson. All right, welcome back. We're going to look at performance measures. The first thing that we're going to do is actually use or utilize cross-validation. The reason that we're going to look at cross-validation is that having one data point is insufficient for us to tell how accurate or how well your model is going to perform in the real world. So ideally, what we want to do is actually perform a cross-validation to be able to extract at least 3, if not 10 or higher number of the so-called accuracy based on the matrix that we use to evaluate the range of likely performance of your model in prediction. So first thing that we're going to look at is the stratified K4. Let me run this in the background because it does actually take a while to run these. And in the meantime, I will explain to you what stratified K4 means. Stratified K4 is a combination of stratification as well as K4. It's a combination of the two. The first step is that the classifier was cloned and trained using the training folds and makes predictions on the test fold. Now, the stratified K4 utilize what we call the stratified sampling concept, which I mentioned earlier. You take the whole population. It's divided into what's called homogeneous subgroups called strata. And in our case, we have two classes, 0 and 1, meaning if the value is 0, it's true. If it's not 0, then it's false. And so what we have is that our population is divided into two homogeneous subgroups, so meaning the groups are divided into true and also false. True, remember, is that the value, which is y in our case, is actually 0. The next thing then is that the right number of instances sampled from each stratum. So we take, let's just say, 10% of our sample from 0, which is true, and also false. Okay, so you need to actually take the equal proportion. If the split, let's just say, is 10-90, then you need to actually, and you are taking a sample of 10, for example, then you must take 1 from the true and then 9 from the false, basically following the actual proportion itself. What this does is that it guarantees that the test set is representative of the population, and so that there are at least some data representing each segment of the population itself. Now, having explained all that, let's look at how it works in the actual code itself. What we're doing here, again, from model selection, is import stratified K4. We do need to clone package or clone library, and CLF is our classifier, and we actually state the random state as 0, and we perform our stratified K4. We split it into 3, and here we actually set the random state equals to 100, and then we store this in SK folds. Right, so running through for loop, and basically remember that we split it into 3. We just need to run through this 3 times because we have already split it by 3. And we're cloning it. We clone the original CLF. And for each portion that we're running it, we feed the train index as well as the test index. And we clone our classifier. And then we use our clone classifier, and then we basically fit the actual model itself. Remembering that the SK4 is from this portion here, all right, because it's actually based on this that we already instantiate. Every time we loop through it, okay, which is 3 times, it will feed different index into this so that they actually train and then perform the prediction on the X test fold and then compare it against the Y test fold and calculate the accuracy of our prediction. And if you look at the outcome of this, is that the accuracy is fairly good, 98%, 98.6 to be specific. 98.9 and 98.76. This is one way to do it. The alternative way of doing it is actually to use the cross-val score, which is a K4 cross-validation. But what it does is that it splits the training set into K4 and a make prediction, and then evaluate the performance on each fold using a model trained on the remaining folds. And when you run it through, what you get again is that in terms of CV3 and the scoring is the accuracy, you notice that it's exactly the same as this. And what this actually is telling you is that the cross-val score, let's look at this, well, I'm actually explaining to you, scikit-learn cross-val score. Okay, so 0.21, that's the version that we're using. So let's run through this. Okay, so the cross-val score is basically cross-validation. And what it does is actually, if you specify an integer, okay, the number of folds in stratified K4, it actually performs exactly what we have done prior using stratified K4. And that actually cuts down the amount of codes that you need to write. So in any given case, you would probably prefer to write this instead of writing this as Ken, or that you can actually make a lot of errors doing it this way, whereby this is just one line of code, provide the classifier, your training data, your Y training, actual target result, and cross-val score, and the actual matrix that you want to use. You can use accuracy, or alternatively, you can actually make use of others as well. Okay, right. And let's look at an exercise with the answer, albeit given to you. What if you would like to perform a 10-fold cross-validation test? How would you actually do that? Well, it's very simple using the cross-val score function. Instead of CV is equal to 3, you can actually substitute CV is equal to 10, all else being equal, maintaining it the same, and then just run this line of code. That's pretty much all that I want to cover. When we come back, I want to actually highlight a couple of danger using purely accuracy as the performance measure, and we'll also look at confusion matrix and some other measurement matrix as well. With that, for now, I'm just going to let that run and accelerate this portion of the video until the result come out. I look forward to seeing you in the next lesson. Welcome back. Having what we've done previously really is actually perform a K4 cross-validation analysis using cross-val score provided by the scikit-learn. So in this exercise, we are going to look at the danger of blindly applying a evaluator as a performance measure. As you are aware, what we've done just now was that with MINST, is that it's a digits, handwriting digits from 0 all the way to 9. And if you count 0 to 9, there's actually in total of 10 digits. And what we've done is that we kept 0 with the default as yes. Anything that is not 0, meaning 1, 2, 3, all the way to 9, are all defaulted to false. So basically our y, our dependent variable, which is what we're trying to model here, is either true, which is 0, or false, which is anything apart from 0. And by that, you can immediately tell it is quite an unbalanced problem. Assuming we have the equal number of samples for each of the digits, 0, 1, all the way to 9, which it is, then by default, what you will have is that you will have 10% of your data representing the 0 case. And then the remaining 90% is will be representing 1 all the way to 9. Why 90%? Because if 1 is 10%, 2 is 10%, 3 is 10%, 4 is 5%, all the way to 9, what you have is, when you add them all up, then you have 90% altogether. So what happens if I, without even building a really, fancy and amazing machine learning model, and I just say, look, 9 out of 10 times it's gonna be not a 0, then I will be pretty correct. Reason being, well, it is. Your data representing your 0 is only 10% of that. So you will pretty much be not correct 9 out of 10 times. So if we just use this really simple dumb classifier, then you will be 90.1% of the time is correct. And looking at our raw data, 90.1% of the images are actually not 0. So anytime you guess the image is not 0, you'll be right 90% of the time. So bear this in mind when you're dealing with skewed database, because of this, accuracy as a performance matrix is generally not the preferred matrix to use for classifier, especially for skewed database datasets. Right, let's look at another performance matrix that's frequently used. Let's look at this. Now, earlier you've seen cross-val score. So this is for the purpose of performing K-fold as well as calculating the accuracy score for each of these fold. So if we have 3, we will have 3 scores. If we have 10, we will have 10 of these accuracy score. So now we actually have introducing another scikit-learn library or package here called cross-val predict. It is a method within the model selection. So let's import that and let's perform the actual prediction. So now you don't actually just look at the cross-val score, you're actually looking at the prediction itself. And you're comparing the predicted value against the actual value. So you're now counting, because we are working on classification problem, they are discrete. Then you can actually compare how many of them you got correct, how many of them you got it incorrect. So we're doing 3 folds using our original classifier that we trained earlier, which is a support vector machine, SVM, right here. So this is actually set as SVM. What you have then is that we're doing 3-fold. We're providing the training data as well as the 0 and 1, meaning the true if it is the value is actually a 0, 1 if it is not 0. And from the matrix we import confusion matrix, and what we supply in terms of the information that's needed to build the confusion matrix is the training 0, which is our ground truth, versus the Y-train predict, which is provided or predicted by the machine learning model itself that we've trained using the training data. Now, one of the things to keep in mind is that we are using the training data. This is not on the test data, so the accuracy will drop when you actually move forward to the test data by default, which is very common. So right now we're just looking at how does it perform based on the data that we supply to train it, and how well does it perform based on that. And if you look at this, how do you read this? Along this diagonal line, okay, this way, 53,000 is correct, 5,500 is correct. The incorrect one are 373 and 365. Now, how do you actually read this? Let's take a step back and look at the confusion matrix itself. Let me just blow this up to, let's just say 70%. Okay, make it 70%. Okay, hopefully that's easier for you to read. So you have the actual, right? You have negative and positive here, and then you have the prediction, negative and positive. So anything that's within this space here will be correct. Anything within this space here will be correct as well. So why is it there? Why are there 2 of these so-called correct zone? You have negative, in our case, is non-zero as the actual truth, whereby your model has predicted that it is indeed a negative, then these are correctly predicted as negative. So you have true negative there. And the actual here is positive, and your model predicted it as positive as well. So in this case, what you will have is a case of true positive. So since the ground truth is positive and your model predicted it as positive, then your model got it correct. All right, so for the correct cases is 5550. For the false non-zero cases is 53,712 that it got correct. So if you look at your model prediction in terms of the false signals it's given, where it is actually positive, meaning it is actually a 0, it predicted a negative. So these are what we call false negative. It predicted it, your model predicted incorrectly that these are negatives, when in actual matter of fact it is indeed a positive. And what about your model predicted as positive, when in actual matter of fact it is actually negative? And this is what you have here called true positive. So 373 false negative, 365 false positive. Okay, so that's pretty much what I want to cover in terms of confusion matrix and how to read it. This is just another way that I want to display it, just to make it easier to read. So this is actually a replication of this picture here, so that with label, of course, this is the actual, this is the prediction, so that you can actually visualize it in one go. Typically, the confusion matrix is printed this way. It might not be the easiest or friendliest to read. This is probably better. With that, I'm going to stop. That's pretty much what we've covered in this situation here in terms of confusion matrix. Why is it actually a better measure versus just using purely accuracy as a measure? Because if in a situation like ours where it's unbalanced, 90% of the time it's going to be non-zero anyway. Your model, even though it predict 90% of the time is correct, that is fairly useless, because just using a really dumb classifier like this, you'll correct 9 out of 10 times. To be fair though, the support vector machine is actually better. It's around 98% or higher. So it does actually have an 8%, I suppose you can a head start or margin ahead of the just dumb classifier. But nevertheless, that's why I want to illustrate that this accuracy is not always the best measure for that. Hence, we use something like confusion matrix to highlight in terms of the actual breakdown. Okay, so with that, I'm going to stop. Thank you once again for watching. Welcome back. In this segment, we're going to look at precision. In the previous lesson, we looked at the confusion matrix in that we have here the actual negative and positive in terms of what the data provide to us, and this is the prediction in terms of our machine learning model. Along the diagonal, as I mentioned, the actual answer or the actual result is negative, and our model indeed positively or correctly predicted as negative. Likewise, this is positive, and our model correctly predicted it as positive. Along these off diagonal, these are the errors. The model predicted as negative, which is false negative really. The actual result or the actual underlying correct answer, if I may say so, is actually positive. Likewise, these are what we call false positive. As predicted by the model, the actual answer is actually negative. So breaking it down, precision is actually a measure of the accuracy of positive predictions. So we're looking at the prediction of the model itself. So it's along this column here, is that these are looking at all the positive predictions that's made by the model itself. We want to know how accurate they are. So that is really fairly straightforward. So these are the true positive, these are the correct result. And so it's really the correct result divided by the combined positive predictions as performed by the model itself. So if you want to translate this to a formula, it's really TP, which is true positive, divided by the total of TP plus false positive. So it's the true positive divided by true positive plus false positive. So this is what's called precision of your classifier. So looking at the example itself, we import from scikit-learn matrix library, and the two methods here called precision score as well as recall score. Recall we will look at in the next lesson. For this lesson, we'll look exactly or specifically at the precision score itself. Now, the result here may vary from the video, as the result from the confusion matrix are different each time as you run it, really depending on your random seed as well. So let me just delete that and run this. and I'm going to delete that. So looking at this, is 93.82% is the precision score of our machine learning model here. So just to illustrate how you calculate this precision score, let's come back up here and add a row of cell here. Then remember, the formula is the true positive, which is 5550, and divided by the combined total positive prediction, which is 365, plus the true positive. 365 is false positive, 5550 is the true positive prediction. So as you see here, is 93.82, which is this value here. So that's really the basic idea of precision, and what exactly it is to measure the accuracy of our positive predictions. Alright, welcome back. In this segment, we're going to look at recall. Previously, we looked at precision. What precision it really is that it's measure the accuracy of positive prediction. So it only look at the positive predicted by the machine learning model. We are comparing the two positive divided by the combination of true and false positive. So that's really what precision is. It measures the accuracy of positive predictions. Now we're looking at the recall here. The difference with recall is that it is a ratio of positive instances that are correctly detected by the classifier, whereas predicted whereas precision look at the prediction of your model, recall looks at the positive instances, the actual ground truth of positive instances that are correctly detected by your classifier. So hence, if we look at this chart here, it is the actual. We're only looking at this row of information here, whereas previously when we look at precision, it's this column that we're looking at, only the positive. Now we're looking at the actual and looking at just this row of data. So in terms of the formula of recall, is really the true positive, which is this one here, divided by total of the true positive and false negatives. So really the actual row of all the positive. Now take a note here, the result again may vary depending on the cause confusion matrix that we run. So let me delete that. So let me run this, and what you have here is 93.70. So this is the actual recall score, which is quite decent. Of course, we like it as high as possible. Let's come back here. So again, I just want to illustrate how you calculate this. Now is 5550 divided by, take a moment and think about it. We are looking at only the actual, okay, and the actual only the positive. So in this case is 373 plus 5550. So let me just highlight this. This is for precision, okay, and this is for recall. So for recall, we're looking at actual. For prediction, we're looking at your classifier. Okay, 93.7, which is precisely the value that is actually calculated here. All right, so we're gonna come back and revisit precision as well as recall and compare them later. In this video, I just want to explain the concept of precision. It is typically used with recall. Recall sometimes is also called sensitivity as well. So with that, I'm going to stop right now and thank you once again for watching. Welcome back. In this segment, I'm going to look at F1 score. Quite often, you may either not want to look at purely the precision score or the recall. You want a combination of the two. In the next lesson, we'll look at specifically if you want to skew towards the precision score or skew towards the recall score. But specifically in this segment, you may want to make use of a combination or of a measure that actually combine the two together rather than looking at them separately on their own. F1 score is that score, is that matrix. It is what's called the harmonic mean of precision and recall. I've given that formula there. I'm not going to dig into it, except that when do you actually make use of F1 score? Now F1 score works like this. It actually favors a classifier that performs well for both precision as well as recall. So it favors those. If you have a model that actually have really good precision but poor recall, then it will not perform as well. Vice versa, if you have a classifier that perform really well with recall but not with the precision, then it won't perform as well as one that actually has a good and decent score of both precision as well as recall. So that's really the basic idea of F1 score. And the best part really is that you don't actually need to calculate it because of scikit-learn have this matrix. It actually has this import score, import F1, and essentially you just need to actually provide the training data as well as the model or your classifier's predicted Y, and the F1 score will be calculated for you. So when we come back, we'll look into precision and recall trade-off. Welcome back, everyone. In this segment, we're going to look at precision as well as recall trade-off. To illustrate that, we're going to make use of the table as you can see right here. Here, what we have is 12 numbers, okay, 12 observations. So 4 here, 3 here, 5, 2 here, so it's 5 plus 4, 9 plus 3 is 12. What happened is that, just so that upfront spoiler, as you increase precision, the recall will correspondingly reduce. Likewise, if you want to increase recall, your precision will correspondingly reduce as well. So let's just say we have a scenario whereby we have a classifier that is designed to pick up all the zeros in these 12 observations. So we have 3 arrows here. So we have central arrow, arrow to the left, arrow to the right. Let's just start with the central arrow. Suppose that the decision threshold is positioned at this very point here and looking at everything to the right. Okay, so we have 1, 2, 3, 4 true positives. We have 4 zeros to the right of the central arrow and 1 false positive, which is the number 7. So at this threshold, meaning setting it at this point, the central arrow, the precision accuracy then is 4 correct out of 5 predictions. So 4 out of 5. If you calculate that, that will be 80%, which is this value that we have here. However, out of the 6 zeros, the actual 1, 2, 3, 4, 5, 6 zeros, the actual ground truth of zeros, the classifier only picked up 4 out of the 6. So the recall accuracy then is 4 out of 6. So it's only 67%. So we can see here in terms of the precision, I put this on the chart, same figure here. Precision here is 80% at the central arrow, and the recall is 67%. Just to re-jog your memory a little bit, what exactly is precision? Precision is the predictor classifying the positives. We want to look at the positive that the classifier has classified, and what is the proportion or percentage of it is actually correct. So that's precision. And whereas recall is based on the actual positive and how many of it was picked up by the classifier. So coming back here, so we're looking at precision, all the positive that it has picked up, what is the proportion? So what we have is out of the 5, 4 is correct, so 4 out of 5, that's 80%. Whereas recall, as I mentioned, is the actual zeros or actual positive and how many of it is picked up by our classifier. So we have 6 zeros, only 4 is picked up by our classifier, so 4 out of 6. So that's the central idea here. So let's just say we want a higher precision accuracy, so we move to the right arrow. Okay, so we want to actually increase our precision accuracy. So how do we do that? Just moving it to the right, what we have now is that out of 3 positive predictions, we got them all correct. So 3 out of 10, 3 out of 3. So our precision accuracy now is gone up to 100%. The problem, however, is that if you look at our recall score, out of the 6, we only managed to pick up 3. Okay, 3 correctly. So our recall dropped correspondingly to 50%. So moving to the left arrow, we have the precision, or our classifier picked up all of the 0. Okay, so in this case, the recall is perfect, 100%. The precision accuracy, however, picked up out of the positive 3, 4, 5, 8 out of the 8 predictions here. 6 are correct. 6 divided by 8 gives you 75%. So you notice that as you increased in terms of your precision, your recall dropped. As you increase in terms of your recall, your precision dropped, and vice versa. So that's really what this summary statement here is about. So I've also kept the notes here for you to refer to. Let's look at the worked out example here. This is following our previous classifier, and let me just add one more line here and set the random seed to 0, and ideally this will actually set everything to create the same result. So we have the classifier. This is a support vector machine. In terms of the losses should come out as hinge, and now we're fitting it as our X train, the features, as well as the Y train. And notice that it's underscore 0, so it's 0 and non-zero. So the loss is indeed hinge. So this is a support vector machine. Now let's look at the index 1000 for Y. It is a 0. We're interested to see what the decision function is. Now, decision function is basically a score that it provides to the specific of our model to figure out whether it lies in the 0, meaning it's true that it is 0, or it is not the 0 digits. So that's essentially what the decision function is. Now, the beauty of the classifier function is that it already computed all of these values for you. So let me just close these off so that you actually have a cleaner screen. So it's already calculated the decision function for you. So now what we need to do here is to just provide our feature, which is x1000, and just to see what kind of score do we receive. Just throwing it in there and see what kind of values that we get in return. So this is telling you the decision value for this is 7034. So let's look at another value just so that we can actually get a bearing on this. So now the Y is 7. Again, we provide the 1001, index 1001, and just to see what the value or decision function value comes back to us. So looking at this, what it's telling you is that at negative 47,945, that's where 7 is, and 0 is actually at strictly positive around 7,000. So the more negative it is, the more the higher the probability, or if you can call it that, or the more non-zero it is. The more positive the decision function value is, the more likely that it is going to be a 0. Let's assume we set the threshold being 0, and we have the y-score. Notice that we have the y-scores here, and if it's greater than the threshold that we set, which is 0 here, and we look at the digits that we predicted, it comes back as false. Why is it false? Because we've changed the threshold to greater than 0, right? So whereas previously, if we actually used this negative 47,945 as our value, which we are still using, and it's asking this question: is this value greater than 0? Of course, the answer is no. Okay, if it's not greater than 0, it's false. Then it's returning to us the decisions that this, based on the x, is not 0. That's the basic idea here. What happens if we set the threshold to 40,000? Of course, it's even less likely that the y-score, which we know is negative 47,000, is still going to return us false, right? So the basic idea that I'm trying to convey here is that you can actually shift the threshold to either let more positives, okay, or shift it more negative to allow more false positives. So I want to relate back to what I talked about here earlier with regards to this line here. So we can actually start at this point, we can shift it to the right to increase our precision, or shift it to the left to increase our recall. That's the basic idea here. So along this line is what we call the threshold. We can actually keep it at 0 or increase to 40,000 in the example that we had, or shift it to more negative. And that's basically allow you, the modeler or the developer, to actually decide how to do that, and for you to actually, well, basically change the value to either allow more true positive or more false positives. Right, so let's again use our classifier, train it, and then store the decision function, just conduct the cross validation prediction and store the y value. And then we plot this, and let's have a look at it. Okay, so this is our y-scores. Okay, so if you look at the y-scores, 0 is over here. You will see that there are a fair amount of overlaps here. This part is obviously where y is equal to 0. This part is y is not equal to 0. So somewhere here is a crossover. Ultimately, what you're looking at here is the two distribution. There are a fair bit of crossover around this area here. Okay, so with the decision score, you can actually compute your precision and recall for all possible threshold, up to you to set, using the precision and recall function or curve function. So let's do that. From scikit-learn, we import the precision recall curve, and we can actually use the precision recall curve providing the training score and also the y-score. So the y-train and the score 0 as well as the y-score, and this will actually give us the decision, recalls, and thresholds. This is a helper function to help us actually to plot it, and you can actually see more here. So the blue line is the precision accuracy, the green line is the recall accuracy, and this also illustrates really well what we talked about early on. As your precision accuracy goes up, your recall accuracy goes down. As your recall accuracy goes up, your precision accuracy goes down. So you need to actually find that threshold that works for you. Okay, so now is the question of how do you actually set this. Before we go there, I just want to finalize some of the key concept here. Is that with this chart, you can actually select the threshold value that gives you the best precision and recall trade-off for your specific task. So it really depends on the task that you want to actually achieve here. Some tasks may call for what we call a high precision value, accuracy of positive predictions, like designing a classifier that picks up adult content to protect kids. This will require the classifier to set what we call a high bar to allow any contents to be consumed by children. So let me explain it another way. When you want to only allow only the contents that you're absolutely sure that it is positive, before releasing it to allow your children to watch the contents. So the basic idea is this. I want to actually be 100% sure before I allowed the contents to be released to be consumed by the children. So that means you are setting a really high precision here. Another example would be, let's just say you have a really highly confidential facility. You want to ensure you identify the employee correctly before you allow them to access or enter the facilities. How do you do that? You basically have multiple checks in place to ensure high accuracy and high confidence before you allow the individual to enter. So that's really where high accuracy comes in, really high in terms of the ranking and importance. Another way to look at this is we all have a bank account. Who do you want to have access to your bank account? The best way to think of it is, well, you want the bank to make sure that they have positively and absolutely confidently and positively and without doubt that you are you before they allow anyone to, well, basically you really, to have access to your bank account. So that's where they have multiple checks in place to identify you before they allow you to have access to your bank accounts. So in that case, high precision is really, really important. So in this case, it is unacceptable to allow one false to get through. So let me come back to use this chart here. This figure will illustrate here. Now, is it good enough for you to allow 1 out of 5 errors to get through? To allow this one, let's just say this instant here, to allow someone to have access to your bank account? Of course, it's unacceptable to you. So you will move your position up to this point whereby it is 100% sure that you are you before you are given access to your bank account. Okay, never mind the frustrations that you have sometimes with the bank denying you access to your bank account, but you get my point. Okay, what about high recall? Under what situation would you actually want to allow high recall or have a high recall? Now, some tasks may call for high recall, which is the ratio of positive instances that are correctly detected by the classifier. Now, in this case, such as detecting shoplifters, intruders on surveillance images, is anything that remotely resemble positive instances to be picked up. Let me come back to this. Let me give you another scenario. Okay, when you want something that is remotely positive to be investigated, okay, shoplifting, for example, okay, if you suspect somebody to be, unbecoming, looking to shoplift, then what you want to do is that you're not looking for high precision anymore. You're looking for high recall, so that some are positive, negatives, like the 3 and 7s are negative, but what you really want to do is pick up all of the potential positive to be investigated. So that's where shoplifting comes in. Okay, another example would be cyber attack. Okay, where you start to have some sort of, let's just say, warning signals, albeit, you might have 5 indicators. Usually you look at 3 and above, then 3 warning signals, then you investigate. But in a situation, let's just say in a cyber attack, even when one actually is tripped, one is actually giving you a warning signal, you might actually want to investigate it so that you can actually have a high recall positions. Other situations I can think of is any anti-money laundering, chatters of terrorist attacks. All these, you will prefer that the machine learning algorithm to be set at high recall positions so that the warning can be flagged, the exceptions can be flagged for someone to actually investigate. Right, that's a lot of contents to be covered, and I know that there are a lot of technical contents that we've talked through here. What we've really covered in this situation is really setting the precision as well as the recall trade-off. We demonstrated using some examples and looking at how you actually can use the threshold to shift in terms of your precision recall, and when whether you actually want high precision or high recall. And so that's really the basic foundations of this portion of the contents. I hope you found it useful. When we come back, we're going to look at another topic just to actually see how we can actually set actual high precision using the code itself. I'll see you in the next video. Alright, welcome back. Let's continue what we actually have covered earlier in terms of the precision and recall trade-off. We're going to look at an example. First of all, the first part that we want to do is actually just plot the precisions against recalls to assist with the threshold selections. So let's plot this, and now how do you read this? Recall, precision. So shifting it this way give you a high precision. Shifting it this way give you a high recall. So that's really where the trade-off actually comes in. And of course, this is actually this chart displayed in a slightly different manner. All right, so if we are aiming for, let's just say, 90% precisions, we can actually approach it this way. So let's look at the actual length, meaning how many values that we do have. We can plot this and just to have a view of it. And let's find the index where the precision is less than 90% and recover the threshold. Okay, so the threshold whereby your precision start to drop below 90%. Okay, 90%. So basically we're taking 90%, draw a line here and come back down here to locate where the threshold ought to be. So it's negative 2858. So let me change this and just take this and put it here. Now if the y-score is greater than 0, okay, greater than this, we should and ought to have our precision being 90% and above. So we store that in y train pred 90, and we actually calculate the precision score, which gives us exactly 90%, and the recall score is 96%. Of course, you can actually push it further and say, look, I want it to be 99%. We can bring back the threshold. Notice that it's now 14,506, so it's actually substantially higher over here. And we just calculate the precision. Now is 99.01, and notice that the recall drop correspondingly as well. What about if we actually want to do this for recall? Again, we recover the threshold, the index first, then the threshold, and we provide the actual threshold value where y-score is greater than that, and calculate our precision, and we get our recall score at 90% or close to it anyway. So that is essentially how you actually vary your threshold, so that you can actually either push towards a higher precision score or push towards a higher recall score. Welcome back everyone. In this segment we're going to look at the receiver operating characteristics curve. In the previous segment we looked at the precision recall curve or PR curve. That is actually a comparison between recall versus the true positive rate. So the true positive rate, which is true positive divided by true positive plus false positive. Whereas the ROC is actually the plotting of recall versus false positive rate, which is the FP divided by TN, true negative plus FP. FP, as you recall, is false positive. So that's really this one, really, is false positive divided by the total of these two. So that's really what we're looking at in terms of the false positive rate. So let's go through some codes, and then we actually come back and see when do we use the ROC and when do we use the PR curve. The beauty of scikit-learn is that the ROC curve is actually included. We just need to provide the y train value and also the y-score, which we actually calculated earlier, define a helper function and plot it out. And here you have the true positive rate versus the false positive rate as you're actually plotting it through. What you get is actually the ROC curve. This is somewhat too large to see, so let me just change it to 10. Then, yep, just squeeze in. So maybe I'll just change it to 8 by 8. Okay, that's better. Right, and we can actually from the scikit-learn matrix import the ROC, area under the curve score, and calculate the area under the curve, which gives us 99.55%. 1 is the perfect score, 50 or 0.5, which is 50%. It's just really random guessing, really. So with this ROC, area under the curve, then you can actually calculate what is the area under the curve, which is this whole area here. And this portion is actually what we what brought the so-called percentage down from 100%. So it's 0.45 or thereabout, really. Okay, so in terms of when do you use PR and when to use ROC, is that you use PR or precision recall curve whenever the positive class is rare. Okay, so let me state it again. You use the PR curve whenever the positive class is rare. Okay, so in some sense, you can actually say you will use this when the actual underlying data is data set, the classes is fairly imbalanced. You will use the ROC whenever the negative class is rare or when you care more about the false negatives in your so-called use case or business example. So in the example above, the ROC curve seems to suggest that the classifier is good. As you can see, it's pretty much close to 100%. However, when you look at the PR curve, you can see that there are room for improvement. So improvement in the sense that if you are looking at the positive cases that you are interested in, then you will use the PR curve to actually adjust and improve accordingly. There are provided two further readings here for you to look up. They are both really good, especially the one by Jason Brownlee. I really like what he's written. It's a little bit not the easiest to read, but very thorough. It's a very thorough treatment. But of course, if you actually compare it to this statistics exchange, it gets a little bit even more terse. So I'd rather that you actually go and read Jason Brownlee's version. Okay, the final part that we want to look at is actually have a model comparison. So far, what we looked at is the plot vector machine or SVM. It's always good to actually have a comparison or another model to compare and see how well we actually perform. So we're going to make use of random forest classifier, and we're going to, as usual, do a cross-validation predict here and extract the value that we need to plot it, and also calculate the ROC area under the curve once more, and finally compute our confusion matrix. Let's let this run, and when it actually finishes running, I'll come back and talk to you a bit more. Okay, so looking at this, what do we have here? The random forest has finished running. The so-called cross-validation predict is finished, and we are plotting two here. We are plotting the support vector machine in the form of SGD as well as the random forest. The dotted line is SGD, and you notice that random forest is actually higher. If you look at the area under the curve, is 99.95, whereas previously is 99.55. So the random forest performed better. It's actually a better classifier. It's more accurate than the SVM, and we're still calculating, we're still calculating the so-called cross-validation and prediction using the random forest. This time around, what we're trying to do is actually we're trying to bring up the precision as well as the recall score and the confusion matrix. Okay, so the validation, cross-validation is completed. If you look at the precision score is 99.34, recall is actually 95, and if you look at the confusion matrix, it is better. The value here in terms of the number of false is substantially lower than before. So this is one example that I really want to perform for you. What we've covered in this lesson really is, first of all, the ROC curve, and we wrapped up with a comparison against the random forest classifier, just so that you have a reference point as a comparison. With that, I'm going to stop here and thank you once again for watching. Welcome back. In this segment, we're going to start looking at support vector machine, and it's a little bit of its history and also how it actually works. It's one of the more common machine learning algorithm, and one that is very popular, so it's a good place to actually dig in a little bit more, because it can be used for both regression as well as classification. It was originally invented in 1963 by Vladimir Vepnik. Vepnik moved on to Facebook AI research in November 2014. What they did in 92 is that they suggested a way to create what is called a non-linear classifier. Essentially, what it traditionally has done, we will go into a little bit more, is that we use a straight line to separate or segregate different clusters of data. But by 92, they started suggesting something that's a little bit more creative, meaning we don't work with straight lines no more. We can start using non-linear classifiers, and that's where this is called the kernel trick to solve that problem. And the current what's called a standard incarnation, which is really soft margin, was proposed by Kortz and Webnick in 93 and published in 95. There's a few more so-called references for you to actually refer to. This is actually a very interesting one by Kapathy. There's a few other links that are provided for you here. For visuals, let's have a look at Kapathy's support vector machine. So with this, you can always play with it yourself. Mouse click to add more data point. Shift mouse click to add green data point. So you have red one if it's just mouse click. Green if there's red, there's green, and K allows you to toggle between linear and RBF kernel trick. So this is really the non-linear version. So if I press R R to reset, so we have some minimum numbers here. So this is red, as you can see. I'm adding more red. If I click shift, these are the additional so-called green dots, and I can of course add more so-called dots as well. The C here is what we call hyperparameter. You can actually tune it higher or lower, okay, to adjust its flexibility. And then you can also tune the RBF kernel as well. These are the hyperparameters, and you can actually click K to switch. Okay, so what you can, while looking here, is that this is what's called a linear separator. And if I press K again, now it's gone back to this non-linear. This is really quite fascinating to observe, and it's really a very powerful one at that. What you can see here is that we can actually, prior to the RBF kernel trick, what you have is that it has a lot of problems separating between the red versus the green, because there are a lot of basically there are a lot of overlaps. And of course this is actually with soft margin as well. And when we actually switch over to RBF, the kernel trick, what you can see here is that it actually allows it to start to work around, start using curve to actually solve this separation problem. Right, so let's start with some basic introduction. Now, support vector machine is really what's called a supervised learning methods. It is used for classification, regression, and outliers detection. Now, just for visual purpose, illustration purpose, let's say we have two classes here. We have a purple class and then we have a black class. In classification, what we're interested to do is to find out the best way to separate these two classes. Now you can of course draw a straight line like this, and this can be done using logistic regression, and it will do that very well. Of course, there's more than one way to draw straight lines. There are in fact infinite lines that you can actually draw. If it's 3-dimension, you can actually draw a hyperplane as well to separate these two class problems. The term hyperplane essentially means it's a subspace of one dimension less than its ambient space. It's a very complicated word. If a space is 3D, then its hyperplane are the 2D planes. Okay, so it's basically one step down. So if you have 3D, basically you have a hyperplane which is 2D. In support vector machine, the separating line, which is the brown line here, this line here, is the line that allows for largest margin between the two classes. What support vector machine does is that it will place the separating line in the middle of the margin, also called maximum margin. What it does is that the algorithm will optimize and locate this specific hyperplane or line that maximizes the margin of the two classes. So the biggest margin, really, the wider it is, the better it is. And the samples that are closest to the hyperplanes are called support vectors. These 3 dots and these 2 dots are called support vectors. Right, so that's really the basic concept of support vector machine, and the beauty of it is that it's really intuitive. It's very easy to understand. Visually, it's immensely helpful for you to actually grasp the basic concept. It's just really drawing a line. If it's 3D, then it's hyperplane. And what are we trying to do? We're trying to actually find a line that actually has the largest margin. So that's essentially what support vector machine learning algorithm is all about. Now, don't let the simplicity of it fool you. The math is complicated, but the good thing is that we don't have to worry about that too much. We can just utilize support vector, to utilize scikit-learn to, well, just essentially go and solve our business problems or the day-to-day problems that we face with. All right, when we come back, we're going to look at linear support vector machine first before we start exploring into the kernel or the non-linear. In this segment, we're going to look at linear support vector machine classification. The key concepts, as we mentioned earlier, using the JavaScript is support vectors. They are the one that actually provide the so-called closures and provide the support to the line. Okay, so these are what's called the support vectors. And basically, it's linear, so it's supported by a straight line. So it's only, and it's really only good for problems that's linearly separable as well. As for the margin portion, remember when we talk about margin is this gap here. The margin can be hard margin or soft margin. When it comes to hard margin, this is strictly based on those that are at the margin between the two classes. Now, keep in mind, if you are using hard margin, which is not ideal actually, it is very sensitive to outlier. So let's just say add a green. You notice how much it actually shifted the whole line. If I add another green here, it'll continue to actually shift it substantially. So those are the one key thing to actually keep in mind. Right, the other portion is that you can actually make use of soft margin classification. What it does is that it widens the margin and allows for violation rather than using a single point, which is susceptible to outliers. You can actually use multiple points, weight, meaning clusters of points rather than using a single point. Now with using the Python scikit-learn, you can control the width of the margin, and how you can control that is by using the C hyperparameter. When you have a smaller C, it leads to a really wide street but more margin violation. And if you can also choose a high C, whereby it leads to fewer margin violation but end up with a very small margin. So shifting C to the left gives you a really wide street. Shifting C to the right gives you a very narrow street. There's one key concept that I want to leave with you, which we will illustrate as well, is that support vector machine or SVM are sensitive to feature scaling. So it's important that you actually do perform that before you start fitting your model. Right, so let's look at some code. It's the usual libraries that we are importing, with the exception of this is new from scikit-learn. We're importing support vector machine. And this illustrates the system, the versions of the software that we're using right now. And we are downloading the dataset iris directly from scikit-learn itself. We need to name the column, or rather we want to narrow down the column, which is just looking at the petal. We're leaving sepal out this time around. And looking at the unique species type, there are 3 types here. And what we're trying to do here is that we are rather than leaving it as setosa versicolor and the actual name itself, which of course the machine learning algorithm will have difficulties to work out. What we can do is actually convert them or map them into an ordinal number with 0, 1, 2. Okay, so the actual mapping here will basically gives you the so-called number, the classes itself. So 0 will stand for setosa, 1 stands for versicolor, and on it goes. Do refer to the documentation for more information. Now let's start with modeling. We specify a really small c. Recall that when we actually specify c, a smaller c leads to a really wider street but more violation. And the next thing is that we instantiate this, and then we call this classifier CLF. Notice that the kernel is linear. I have a few commented out code. That means they won't run. This is for experimentation. You can actually play around with them to see the actual effects of it. But I've basically hashed them out, commented out, so that we don't affect the code right now. All that we wanted to look at is just the linear version. And then fitting the data itself. If we perform a prediction of 6, 2, you get array of 2. Now this is the part that you probably have forgotten when it comes to our original data set. If you look at this, since we are looking at specifically petal length and width, so we're looking at petal length and width. If we specify 6 and 2, essentially what you have is that this is most likely to be class 2, which is the Virginica. Okay, so that's the prediction of this. Now it's difficult to visualize like this, so we're gonna plot this out so that's easier to visualize. These are just basic code to convert the whole plot into a grid-like structure. So remember that our x features is 6 in terms of the length and 2 in terms of the width, so it actually sits right in here. So this portion is Virginica, this portion is versicolor, this portion is setosa. And of course this is actually a class on its own. It really stands out. It's very easy to separate out, whereby this is not. These two classes is a lot harder to actually separate out. And this is just another plot denoting the same thing, although the color is a little bit faint, but nevertheless you can actually see it from here anyway. So performing another implementation of this, what we can do is that we can actually choose model selection, train test split, to see how well the actual model really performs. So basically these are all the codes from above, except now we have train test splitting, keeping 80% for training, and setting the random state at 0, and just really run through the whole thing. Notice that we are still mapping the name to a integer, okay, so that we're working with a number rather than the actual string itself, which will throw up an error if we do that. The first thing we need to do is that we do need to scale our training data. Okay, this will of course speed up the training, and we store this in the x underscore standard scalar underscore train. Again, we're working with linear kernel, which is linear support vector machine. Notice that C is now 1. It's more narrow now, remember. Let me come back here. Smaller C, wider street, higher C, smaller margin. Okay, alright, back here now. Let's fit our data once more and import the so-called model selections, cross validation, score and predict, confusion, and also the usual suspect that we need to evaluate the performance of our classifier. Alright, let's perform the cross validation. We are using 10, okay, CV of 10. Looking at the accuracy is 95%. The standard deviation is around 5%. If we perform the cross-val predict and look at the confusion matrix, there are 2 errors here. Along the so-called diagonal, these are the correct, so it's actually pretty good in terms of its performance. In terms of precision recall, it's 95%, likewise F1. And if we look at the test set so far, what we've looked at, all of these, okay, these are within the training data, so it's supposed to perform better. So if we look at the actual test set, now looking at CV of 3, looking at the confusion matrix, there are some errors here, although the data set is indeed quite small. You'll notice that the actual performance did indeed dropped down to 94% for the precision score. The recall is now 93 and F1 is 92.9. And that really is a very quick walkthrough of linear SVM. What we have done is talked a little bit about linear SVM, the hyperparameters that we can make use of, run through some basic codes to look at the actual underlying data that we're working with. So far we've only selected purely the, if I recall correctly, the pedal length and width, and just really using this to actually separate it out. And this is the actual implementation of it. And this is essentially how you actually develop a model. You load the data, you choose your machine learning algorithm, you choose your hyperparameter, you prepare your data so that there is a train and test split. You scale your data, followed by performing cross-validation within your training dataset so that you know how it's likely to perform when it actually start looking at data that hasn't seen. And you notice there's 95 plus and minus 5%, so the worst that it's going to perform likely to be around 90% in terms of the accuracy. So once we've done and we're happy with our model, we test it with our test data set. And if you look at this, this is well within what we suspected or what we expected, which is higher than 90% but less than 95% during the training phase. Thank you once again for watching. I hope this really instructive lesson has been helpful to you and you found it useful and help you to understand SVM much better. When we come back, we'll look at kernel or non-linear SVM. Okay, let's look at polynomial kernel. Typically what happens is that when you actually have an example like this, where you have, let me just blow this up a little bit, height 30%, let's push it to 40. Okay, so you have a straight line here, is that you have these blue dots or purple dots and you have two green dots and then you have two purple dots. Well, there's no way that a simple straight line, one-dimensional space, is going to be able to separate these. So what we can do is actually perform what is called a kernel trick, converting this into this. Okay, basically transforming it using a polynomial kernel, and now you can actually draw a straight line to segregate these from these. Right, so that's the basic idea, and let's have a look at how you will actually do this. We have just specified degree is equal to 3, so it's no longer linear, and then I've specified polynomial as well. Just be mindful that the larger the number of degree, the more flexibility that you have, the more likely that you're going to overfit your data. So that's something to keep in mind. So let's again plot this out to visualize. You can see that there is indeed a curve here, and the curve has improved the separation between these two classes. Well, let's see if this actually does translate to our underlying machine learning model. We start with importing the data, train test split, importing the standard scalar. These are the column that we're working with rather than the full set of data. Once again, we need to actually convert our y or our dependent or our classes to a numerical value so that the algorithm can work with it. And also splitting our data into train tests, and also keeping 80% for training. Okay, so having done that, then the next step then is to actually perform what's called fit and also transform of your X trained data and store in this variable here, and actually fitting the data itself. So this is the scaling of your data or data preparation, pre-preparation, and this is the actual fitting of your classifier or the support vector machine. Let's start with looking at the cross-validation within the trained datasets. It's substantially worse than the linear, surprisingly. So the accuracy score has dropped down to 78%, and the actual standard deviation is also rather wide. And if we look at the confusion matrix, well, it does seem like it is somewhat confused. looking at the precision score as well as recall, including the F1 score, it's actually a market drop of almost a 20% drop. If we look at the cross-validation with respect to the test data, again, there's no improvement there. It's still very, very poor. So that's basically, I know this is probably not a good illustration of how the polynomial can improve your model, your machine learning model's prediction, but don't be fooled by the actual performance or the worst double degree, quote, performance of this polynomial kernel. Of course, what I haven't done is actually, I didn't tune it. I didn't actually, the number that I've chosen is just a random number that I've chosen. So the degree, maybe 4 is better, for C, maybe a smaller number is better. There are a whole lot of things that you can tune here to actually improve the actual output. What I've only done is actually just really a very, it's basically chosen a random number, which doesn't really, it's not going to be good. I mean, if I happen to choose one that's good, it also doesn't show you the actual strength and performance of the underlying machine learning algorithm. The concept is there that they can use a kernel trick to separate what is not separable in terms of a linear kernel. So that's our linear line, straight line rather. Make use of this and just to compare and contrast against a linear, so that you can actually develop again some intuition and compare how much better this polynomial kernel perform in comparison to the linear SVM. Okay, thank you once again for watching. Welcome back everyone. In this segment we're going to look at Gaussian-Redal basis function. The math of this looks like this. Again, I won't go into the absolute details of this. It's just really to highlight that this is very similar to polynomial to the extent that it is non-linear, but that's about where the similarity actually stopped. Okay, so moving on from there, we are gonna go dive straight into the actual code itself, and just so that you can understand how powerful this method is in terms of its ability to model non-linear characteristics in the underlying data. Right, let's start with, let me just run these codes in the background, because it does take a while to run on a simple MacBook. Let me run this and then come back here and let that run in the background. Okay, so to begin with, we are doing the usual importing train test split standard scalar, working with petal length and width, again transforming the class name to 0, 1, 2 integer really, and basically perform the actual train test split itself. As before, we do need to perform scaling because support vector machine is really very sensitive to this. In terms of the hyperparameter, we provide C is equal to 1.0, gamma is 0.7, and in terms of the kernel, we specify Redal basis function. Okay, having instantiated our model, the next step then is to actually fit it. In terms of the X standard or the standard scalar train as well as the Y train. Right, so the next step then is to actually just perform cross-validation within our training data set, just to get a feel of how well the underlying model actually perform with the use of Redal basis function, of course. And if you look at this, you can see the average accuracy is 95.01, and the accuracy in terms of the standard deviation is 0.05. Now, just to re-jog your memory, let's come back up here in terms of the linear. Okay, 95.01, and the accuracy is 0.053. It is exactly the same. Okay, so it's exactly the same. Right, the next step then is that we do need to perform the cross-validation, prediction, and looking at the confusion matrix as well as the precision, recall, and F1. And the F1 score, which is, as we mentioned before, is a combination of harmonic mean of precision score as well as the recall. So F1 score come in at 95.84 as a comparison against the linear. It's an improvement because on the linear front, the F1 score is at 95% with 3 and 3 errors. Before we move on, so that we don't have to scroll back up, the F1 score for cross-validation of the test data set is 92.9. Right, we got up to this point here whereby it's 95.86 in terms of the F1 score. It is better than the linear function. Now, this is something that we haven't done before or have come across before. So let me walk through this with you carefully. You've seen pipeline before. Essentially, we are combining, much as the example that I mentioned in the past, which is like an assembly line, whereby you perform, for example, scaling, then you perform the model instantiation, followed by the so-called prediction itself, fitting, then prediction itself. So likewise, what we're doing here is that we importing the train test split as well as the grid search cross-validation. Now, we of course will perform the scaling. The pipeline here is that we are doing this step, which is the actual model itself, the support vector classification, and the parameter that we want to actually tune is the C as well as the gamma. Okay, and the next part then is to actually perform the actual fitting itself. I probably should have specified the so-called IID, but never mind, it's not crucial. It won't create, just warning right now, it will actually sort itself out once the new release comes out. So we perform a grid search. Basically, it's actually a brute force grid search going through these 1, 2, 3, 4, 5, 6, 7 parameters, and then for gamma is 1, 2, 3, 4, 5, 6, 7 parameters. This can take quite a long time to go through this process, especially if you don't have a GPU on a MacBook Pro. Typically, it doesn't come with a GPU that the notebook utilizes well. If we look at this, that's part of the reason why I wanted to run this ahead of time. And if you look at the so-called support vector machine grid, after having done the grid search and looking at the radar basis function, the best score or accuracy score is 95.83. And what we really wanted to know is the actual parameters that actually achieve this best score. And from this, it basically tells us that the C score will need to be 0.1, the gamma score will need to be 0.25. And we continue on to perform the prediction. Notice this is on the test data. This model has never seen the test data before. So you compare the test versus our prediction. What you get is that this is one of those rare cases whereby it's a perfect score. It's 100% accurate without any error whatsoever. Now, of course, in real world, that's not gonna likely to stand. The reason that this is perfect, in part, is because there aren't a lot of data points. Okay, so as you add more data points, it's more likely to have increasing number of errors. If you look at the data itself, plotting that out, you can see that there are 2 mislabeled, misclassify, another one misclassify here. Kind of hard to tell because for this part here, but you can tell there's 1, 2, 3 at least misclassification. So that's one thing to bear in mind. Although it says 100%, that's actually a bit of a fluke, really, from my point of view, and it's more likely that you're going to get close to the 95.8% score that you observe here. Right, that's pretty much the last portion of SVM with the use of radar basis function. Of course, within here we included one additional topic here, which is grid search. So I hope that has been useful for you. Thank you once again for watching. In this segment, we're going to explore the topic of support vector regression. SVM is not just purely for classification, it can also be used for regression. Right now, the slight variation in terms of our comparison to our previous code is that we are importing SVR, which means support vector regression, and we imported different matrix, which is the mean square error, as well as R square. You use this because it is slightly different from your traditional classification. Classification use different performance matrix from regression. Okay, so this is our fairly familiar friend here, or database or data set that we've utilized in the past, which is the Boston housing data set. In this segment, the only so-called feature that we're looking at is the LSTAT. Likewise, we need to actually instantiate. In this case, we need to fit our data after instantiation so that our model can learn from the data that we provide to it. So the XY here is the full data. Okay, full data, full Y, which is the medium house value, and full X, which is all the value of the LSTAT data. So the next part then is to actually plot our chart, and if you look at this, you can see that it isn't exactly a really straight line. You can almost argue that this is actually overfitting it somewhat, especially when you start to see this kind of behavior exhibiting, and basically this kind of behavior is fairly undesirable as well. But it's very characteristic of support vector regression because it does have a fair amount of flexibility to go with it. So you might want to actually increase the regularization for this model, meaning don't give it too much flexibility. So let's just break it down a little bit in terms of our performance. If we're looking at purely linear and we instantiate, fit our training data, perform the prediction on our training as well as the test. Let's look at the actual performance itself. In the training, it's 41.81. In the test, it drops to 36.83. So in the R square, it's 52%, while in sample and in the test score, it drops once again to 50%. So it's pretty mediocre. When you're looking at this, is 50% of the time, with the R square only explain 50% of the so-called variability of the underlying data. What happens if we actually use polynomial? If you look at polynomial, it just takes a bit longer to run these codes because of the flexibility that comes with it. In this case, we are using 2 degrees, and we perform the prediction on using X-train data and store it in white_train_predict. Again, we do likewise with X-test and store it in Y-test predict. And we'll wait for this to run. In the meantime, let's run that as well. This may take a wee while to run. And beyond that, the next step then is to actually calculate the performance and look at the performance of the model itself to see how well it performs in and out of sample. So I'm going to stop talking right now and speed up this portion. Well, good thing is that I don't have to wait very long at the actual results already out. So looking at the mean square error, it actually improved surprisingly from 110 to 114. Well, is that really an improvement? What do you actually really want to achieve when it comes to mean square error? When it actually comes to mean square error, what you really want is actually a drop. So technically, this is not an improvement, okay? And with the R square, well, I don't know about you, I don't know how to interpret negative score for R square. Usually R square is between 0 and 100%. So when you have a negative score like this, it kind of doesn't make any sense at all. And So in this case, we kind of have to discard this model. It's rather bizarre, whereby the linear makes more sense. The mean square error improved, but the R-square actually didn't perform so well. So it can be that your mean square error and your R-square does not report the same thing when it comes to support vector machine. All right, the next step, then the last step really is to look at the RBF kernel and assessed in terms of the performance. Well, looking at both the value for mean square error as well as the R-square, it actually performed the best amongst the three model of linear, polynomial, as well as RBF. So looking at RBF itself, you notice that the R-square is substantially higher at 64% in the test, and the mean square error is actually substantially lower at 26 when you compare to 36 here. With that, I'm going to stop discussing this in this lesson. Really, we have covered support vector regression using the three different types of SVR: linear, polynomial, as well as RBF. And there are a couple of things to bear in mind when it comes to the advantages and disadvantages of SVM. It is very effective in high dimensional space. It uses only a subset of training data in the decision function rather than all the data. There are many different kernel functions can be specified for the decision function. Linear, polynomial, RBF we've looked at. Sigmoid, we haven't really looked at it. Now you can also create custom kernel function as well. A couple of disadvantages of SVM. You do need to be aware of overfitting when your number of features is greater than the number of samples. We did see some of it when we are looking at the support vector regression. The choice of kernel and regularization can have a large impact on performance, so that we already see as well. Choice of kernel, yes, definitely. Regularization, and yes as well, definitely. Especially when your model is far too flexible. The unfortunate part about SVM is that there's no probability estimates, unlike logistic regression. Right. This is kind of cute. I won't be too concerned about this. This is really about kernel trick as well as out of core support. The key idea here that I really want to emphasize is that all of these require feature scaling as well. The reason being SVM algorithms are not scale invariant, meaning a difference in scale will have a high impact on the actual performance of your model. Right, so that's really pretty much all that I want to cover. There are a lot of information here, where to from here. I strongly encourage you to actually go carry on and read a bit more and research more if this is a topic that is of interest to you. Thank you very much, everyone, for paying attention. I appreciate that you follow along. I hope you have enjoyed this lesson. Good day, everyone. We're looking at decision tree, embarking on the study of decision tree for these lessons and the few lessons following from here. Decision tree is also called CART, which is classification and regression tree. From that, you can pretty much deduce that decision tree can be used for both classification as well as regression. Now, what exactly is decision tree? Here's an example of it, where if you want to read this carefully, what you have is that if the petal width is less than or equal to 0.8, if that is indeed true, then you have the class which is equal to setosa. For this, you have a sample of 50. Value is 50 for the first class, nothing for the second, nothing for the third. So that is essentially this less than or equal to 0.8. If that is not true, meaning it's greater than 0.8, then you have a false. True will come to this bucket here. If it's false, it will come to this bucket here. And within this bucket, there's further breakdown, meaning further splitting of it. What is the splitting criteria? The splitting criteria is if it's less than or equal to 1.75, then you have another class called versicolor. The remaining will come to this class here called Virginica. So what you can deduce from here is that Well, if it's less than 1.75 in petal width, it will come to this category right here. And yeah, and on it goes. That's pretty much the basic idea of decision tree, and each split provides you with further information. And until a point whereby it can no longer split anymore, what you have is purity that looks like this. Gini is equal to 0, Gini is equal to 0, Gini is equal to 0. Once it reaches 0, it cannot split anymore. With the 0 here, you notice that it cannot split anymore. When you have impurities, then your Gini will be at 0.667, meaning it's greater than 0. Then it can be further broken down or split. So that's the basic idea of decision tree. So let's look at a few more key facts before we move on into the codes. First step is that it is a supervised learning. It works for both classification and regression. It is the foundation of random forests. It is extremely attractive because of interpretability, meaning it's really easy to interpret. What we just did, looking at the decision tree, it doesn't take a rocket scientist to understand it. It just basically keeps splitting. There's a splitting criteria. So if it is this, it will go into this bucket. If it is not, then it goes to the other bucket. The split is based on set impurity criteria, and there is also a stopping criteria as well. Now let's look at some advantages and disadvantages. These are based on the source from scikit-learn. Advantages is really the fact that it is really simple to understand and interpret. Trees can be visualized easily. It requires very little data preparation. It is able to handle both numerical as well as categorical data. It is possible to validate a model using statistical tests as well, which is one strength that a lot of other models does not have. It performs well even if its assumptions are somewhat violated by the true model from which the data were generated. So that's the advantages of decision tree. There are some disadvantages of decision trees. Overfitting is really easy to overfit. There are a few ways to work around. You have to set things such as the minimum number of samples required at a leaf node, or set the maximum depth of the tree are necessary to avoid this problem. Take for example here, we can actually specify the minimum number of samples being 50, and this only have a samples of 1, and that's fairly meaningless really. If you set it at 50, then it will stop here rather than continue splitting. The second thing, mitigant or way to work around that, is the maximum depth of the trees. You can actually do that. When we have 1, 2, 3, 4. You can of course say, look, 3 levels, that's pretty much 1, 2, 3, stop at this level. That's one way to actually work around the problem as well of overfitting. Decision tree can be quite unstable. There's some way to work around it. You can use decision trees within an ensemble. The ensemble is really a fancy term for combination or combining multiple trees. You also cannot guarantee to return the globally optimal decision tree, meaning you may not be able to find the best solutions. You might have found a local minima rather than a global minima. Well, the mitigant or the way to solve that is to train multiple trees in an ensemble learner as well. I think you're starting to get and see the theme here, ensemble. And finally, decision tree learners create biased trees if some classes dominate. That's a real problem. There are ways to work around that. The recommendation here based on scikit-learn library is to balance the data set prior to actually fitting it. There are some questions here. I shall leave that for you to actually explore and attempt to answer them yourself. So that's really the actual basis and the very brief introduction to decision tree, where I just want to set the foundation before we start digging into the codes. Once we get into the codes, there's a few libraries that we don't have that we do need to install. I will show you how to do that on a step-by-step basis. For now, gonna wrap that up. Look forward to seeing you in the next lesson. Okay, let's start training a decision tree using the scikit-learn library. We do our usual, importing the libraries. From scikit-learn, we import tree, which is basically our decision tree. We are providing with only two sets of sample data. With the x, we have two sets of value, 0, 0, and 1, 2, and y is 0 and 1. So this is 0, 1, 2 is 1. So let's run that, and we instantiate our decision tree classifier. We fit our data, and we perform prediction. What happens if the value is 2, 2, which is, well, you just kind of have to imagine 0, 0 is obviously the origin, 1, 2 is actually one step to the right and two step northward or upward, and this is two step to the east or to the right, and two more steps to the upwards. And what you have is, it's more likely based on decision tree that it is to be a 1. And you can also calculate the prediction probability. 0 in terms of class 1, 1 in terms of class 2. The class 1 here is class, as this is 0 here, 1 here is pertaining to this. So basically the classifier, decision tree classifier, say I am 100% confident that it is a 1. Okay, it's definitely 0 probability that it's going to be a 0. So what happens if we say 0.4 and 1.2? So this is 0.4 step to the right, 1.2 step to the north. Naturally, you're starting to get in between. Okay, so start to get a bit vague. It's still predicted as a 1. Let's see what is the probability. Well, it's still returned as 0 and 1. What happens if it's 0 and 0.2? Well, it defaults to 1, meaning 100% probability that it's class 1, which is 0, 0% probability or 0 probability that it's a 1. So the decision tree classifier is capable of both binary classification and multi-class classification. That makes it extremely flexible, and that's really one beauty of it, of using decision tree, is that it is extremely flexible for both binary as well as multi-class, which makes it a lot easier to work with. So that's a really brief introduction using very simple data sets. And now let's look at something that's a little bit more complicated, which is our iris data set. Okay, so this is just viewing the data, looking at the features name, and we're storing the data, the to, meaning this portion here only, rather than all of the data. And y is the iris target, which is our classes. If we look at y, is 0, 1, or 2. And we create the decision tree with fit. And the next step is this. Right, this is the part whereby I'm going to help you walk through this process. So let's copy this line of code. Come over here. We go over to the environments. We need to open up a terminal and copy and paste this. We need to install GraphViz as well as Python-GraphViz. So this might take a while to run, so we're going to let it run and speed up this video. Alright, the installation is now done. So the next thing that we do need to do is to actually run these two lines of code. Okay, having run that, we do need to run this in our command prompt. So let's just copy this, come over to this, and we do need to go to our directory. So let me just go to my desktop, the way I actually have the file. Okay, clear that. Okay, so let's go to codes. Okay, right. Notice the file there, tree dot. What a terrible name. So I'm gonna call this 42, and let that run. Okay, it seems to be all right. No issue being thrown out there. Okay, I'm gonna call this 42 and read the file in, and here you go. Voila. So this is the actual tree itself visualized for you. Right. The next portion is to actually import GraphViz, which since we already installed it, so there's no errors being thrown out. we can also export the graph, and I think we should be able to visualize this. Now let me see why. Okay, so it does actually visualize out. It's rather large though. That's probably the only catch. This is actually the same as this here, and there are two ways to visualize this. This is actually a little bit more complicated in that you have to go out and do the command line to do this, whereas this allows you to actually visualize within the Jupyter Notebook itself. Well, I think for now we're gonna stop right here. There's quite a fair bit that I have gone through. I have what we've done here is that we've trained our decision tree. We applied it to the iris dataset. We also visualize it two ways. One way is to actually use the graph viz and then using dot to convert the PNG from dot file to a PNG file, and then the final way is to actually use the tree, export the graph viz, and then convert it into a graph for ourselves to visualize within the actual console itself. For that, I'm going to stop right now. Thank you once again for watching. Look forward to seeing you in the next lesson. In the previous lesson, having trained our classifier on the iris dataset as well as visualizing the decision tree itself, let's take it one step further and visualize the actual decision boundary itself to see how the decision tree separate out the three different classes of iris flower data classes, I should say. So as usual, we import NumPy and Seaborn basically to in preparation for our visualization. Download our data. We're just selecting the petal length and width. It's easier to visualize using just these two columns. We're converting our flowers classes to 0, 1, 2, 3 integers, so that it's easier for the classifier. Otherwise the algorithm is going to crash because it is in text format. It just has difficulties with that. So let's create the mesh and visualize this. This is the decision tree, and you can see that it is really extremely flexible in the way that it actually work around the so-called data, and you can almost argue that this is actually overfitting somewhat. It can be dangerous to do this. This might work really well with your training data set, but whether it will continue to work like this or whether this is really indeed the case or not for real-world data set is questionable. This part, it's a bit suspect in my view. Alright, so that's really the basics of visualizing the decision boundary. Let's move on and understand some of the algorithms or the underlying algorithm of decision tree learning. Now, when we were looking at support vector machine, we have linear, we have polynomial, and then we have RBF, sigmoid, and on it goes. Likewise can be said with decision learning. There are a few iterations of it. Again, for these, I won't go into the depth of the mathematics or the differences between them. You have ID3, 4.55, as well as CART. These are all progressive improvement of the previous algorithm or learning algorithm to segment the so-called tree itself. All these actually are pretty much based on the same Gini impurity. We touched on this previously. That's the important part. Really is that where there's impurity, you can give the decision tree the flexibility to separate it out until you get a pure node. Okay, the pure node here is when Gini coefficient is equal to 0. Now, as the variation increases, where there are more and more heterogeneous classes, or meaning increased diversity, the Gini coefficient increases and approaches 1. So the whole concept is that when the Gini coefficient is high, then there is the impetus or rationale to split the tree until a point whereby the Gini is equal to 0. This is an example that I've created. Let's see if I can magnify in such a way that you can actually see this. So there are 3 examples here. Okay, if we look at this, this is a homogeneous example based on this formula here. So it's basically 1 minus summation from j to r, probability square, and this is a representation of all the j. So if you look at the formula here, is for all the male, because they're all male, so there are 10 of them, and it's 0.1 square, and you sum them all up. And when you actually sum them all up, 1 minus, with the summation of all of these, it actually will be equal to 0. So it's 1 minus 1 is equal to 0. Hence, you actually have the Gini equal to 0 here. So when you have 50-50, the probability then is actually half, 0.5 square, and 0.5 square. And what you have is actually is a combination of 0.5 plus 0.5 gives you 0.5, 1 minus 0.5, hence is 0.5. Whereas male here, the probability of being male is 1 here, so it's actually 1 minus 1. And if you actually have heterogeneous or variation of it, and what you basically have is all of these, and basically is 1 minus a summation of all of these, you get 0.9. So this is basically telling you it's approximately close to 1, and you actually have a very heterogeneous, lots of diversity. And this is smaller in diversity. This is what you call a pure node. So feel free to play around with that until you actually get a better understanding of how it works. I won't go through entropy. Which one should I use? Sebastian Rascal basically said they tend to generate similar tree, and Gini tends to be faster to compute. So it's not really major which one you choose. You can actually run both just to actually get a feel for it. I believe these codes are directly from either Sebastian or directly from the scikit-learn. This is to illustrate the difference between entropy. The red dashed line is Gini, and then the green dashed line is misclassification error. So in any case, the way that to read this is that this is the impurity index. So this is highly impure, and over down here is actually pure. One more point that I really want to highlight is about information gain. It's not always the case whereby you want to actually keep splitting your decision tree until it's pure, completely pure, with the Gini coefficient of 0. You want to actually look at the expected reduction in the entropy caused by splitting. So usually the approach is that you keep splitting until you obtain as close to homogeneous class as possible. Okay, there's an extra A here. Okay, so there's the general consensus here. There are some caveats or exceptions to the rule here, is that if your numbers or observation or the leaf node has too small a sample, like 1 or 2, there may not be any point in splitting it to that level of details. Okay, so this is a really quick whirlwind tour on a couple of things. We visualized the decision boundary. That's the first step we did. Second one is really quickly touch on decision learning, and also Gini impurity. And these are just to give you an exposure of it, not really to grasp the full details of it. There is this formula which are provided here for you to play around with to get a better understanding. Ultimately, that's not the purpose of this exercise, is to highlight to you that this is the Gini coefficient. You can actually work it out. It's not something really complex, and by and large, in fact, all the calculations is computed for you within scikit-learn itself. With that, I'm going to stop right here. When we come back, we're going to look at decision tree regression. Welcome back. Let's dive into decision tree regression. Well, first of all, import tree from scikit-learn, and we have two values here. We have two x points, where 0, 0, then y is 0.75. When x is 3, 3, y is 3. So we instantiate our decision tree regression, followed by fitting it, and let's just perform a prediction. If the value is 1.5 and 1.5, what would happen to the actual y value? In this case, it actually predicted it as 0.75. Let's run this and visualize the decision tree regression. Now, what's the purpose of this exercise? The purpose of this exercise is to show you a couple of things. We have the red dots, which is, as you can see, is kind of like a sine wave. Kind of like sine wave because the numbers doesn't actually correspond exactly to sine wave. And then you notice that we have noise. There are outliers all over the place. Now, if you are using a decision tree regressor with maximum depth of 2, basically what you have is this blue line here that represent the decision tree regressor. And if you actually have a maximum depth of 5, what you have is that the decision tree is actually pretty much trying to, has so much flexibility, it tries to fit through all of the data points, including the outlier. With that, this is what's called overfitting, and basically you prefer to use max depth is equal to 2 to restrict and not provide the tree with so much flexibility that it tries to actually fit all the data. And the reason being, if it's overfitted, it will not generalize, it will not perform well when it's dealing with non-training data, meaning it's working with test data. We can actually perform what's called regularization to force and not allow the decision tree to have so much flexibility. These two maintain the same 2 and 5 maximum depth. However, the difference is that the 5 maximum depth of 5 has this so-called regularization that forces it to must have minimum leaf sample size of 10. If it's less than 10, it is not allowed to split. So here you have it being forced. In essence, the idea here is actually regularized. The regularization forces it to not overfit into all the actual outliers itself. Why 5? You can choose a different number, but what you can actually basically see here, well, there's only one sample here, so it's gonna basically just ignore that. All of these, one sample, it's just gonna ignore. And that's what the whole idea of regularization is, that you wanted to actually describe or generalize the general consensus in terms of the trend or the underlying data, rather than trying to explain and try to fit all the slight variation and outliers. Okay, so looking at overfitting itself, let's see if we can visualize this. And this is an example of overfitting. Well, the earlier one stopped a lot earlier on, so-called decision tree that we had, whereas this have absolutely no so-called regularization or restrictions at all. So wherever there's impurity, meaning with Gini that's greater than 0, it keeps splitting until Gini is 1. Gini is 0, Gini is 0, Gini is 0. So it continued to split, and suddenly you have this one big giant massive tree. Yeah. Whoops. Let me just see if I can shrink out one more. Yeah, well, I still can't fit it into one screen. And you can see how big and massive this decision tree is. It's pointless really going down to this kind of size. But well, that's the one thing that you need to be mindful and careful of, especially when you're working with decision tree. It is able to actually keep on going until it gets ridiculously excessive. Right, finally, we want to actually perform or what's called end-to-end modeling with decision tree. Let's go through this one by one. The first part is make moons. The idea of making moons is to actually create data points, but with the shape that looks like a moon. We have two classifiers, classifier 1 and classifier 2. These are both decision tree. One is without regularization, another one with. Of course, we have our train test split, and we're also going to perform grid search. But in this case, rather than performing too many grid search, we're just going to have a minimum samples leave between 5 to 20. And let's run the grid search. We have, what is this? Okay, so using concurrent silences, CV warning, future value. The default value of CV will change from 3 to 4. Okay, so basically the CV will be changed. Okay, so continue to run this. It basically tells you in terms of the best fit here is to actually make use. The best estimator here is these parameters. Minimum samples leaves is actually 19. Okay, so that's the key one there. And when we look at the accuracy score is 83%. And if we look at so this is the accuracy score based on the grid search, and this is on classifier 1 is 74. If you look at the classifier 1, this is the actual parameters that we can actually obtain. Oh, okay, let's take a quick look at this and summarize what's the lesson out of this. There are a lot more parameters that we can tune. For now, what we've done in our example here is just the minimum samples required of a leaf, going from 5 all the way to 20. We have two models, CL1 and CL2. Technically, we didn't really touch CL2 at all in this whole exercise. We have a grid search to identify the best so-called parameters. This is in sample, but when you look at the actual out of sample test itself, it comes up to 83%. And likewise, if you look at the CL1, in terms of the test, it comes up to 74%. So without grid searching, which is purely instantiating, the performance is actually subpar. After we perform the grid search and looking at the test data, by the way, we're not looking at the training data. These are out of sample tests. The grid search performed better at 83 versus the classifier 1 of 74%. So ultimately, where do we want to go from here? Couple of tips on practical use. As we've encountered, decision tree tends to overfit. That's the one thing to keep in mind. Second thing is consider performing what's called performance dimensionality reduction. Using PCA, for example, beforehand. Do visualize your trees as you are training by using the export function. Use maximum depth of 3 as an initial tree depth. Use the max depth to control the size of the tree to prevent overfitting. Continue to tune either your minimum sample split or minimum samples leave to control the number of samples at a leaf node. Balance your dataset before training to prevent the tree from being biased towards the classes that are dominant. How you do this is by sampling an equal number of samples from each class. That's one step. The other step is by normalizing the sum of the sample weights. Now, this is really a foundational class on decision tree. In real world, you're not going to stop at decision tree. You will start looking at random forests and ensembles. And that's really where the power of decision tree comes in to its own compared to many of the other so-called machine learning algorithms. There are more links here for you to refer to study further. For now, I'm going to stop here and thank you for watching. Thank you for your patience. I really look forward to seeing you in the next class. Hello everyone. In this segment, we're going to look at a project using a decision tree. So the project here is called Project HR. Ultimately, the basic idea is to predict the attrition of your valuable employees. The data is from Kaggle. It's a really interesting data set because it is unlike what we've seen so far, which is fairly simple, fairly straightforward data sets. This is a really rich data set with lots and lots of features for you to utilize. It is provided by IBM from the HR analytics group to basically evaluate employee performance as well as attrition. So that's the basic idea of this data set. Right. For a start, we go through and import our basic libraries. The data or the file, the data set's already been downloaded in the data folder. So we just have to read that in using pandas. So if you look at this, we have 35 columns of data. So this is what we meant by rich, really rich data set. It's gonna take a little bit a while to actually get used to the data because it is so vast. There's so much information, so it pays to actually study each and every one of the column carefully. That's the first step that you really need to do before you actually start building any machine learning model. For a start, I have a so-called note here or remarks here which state this column here is attrition, is the actual specific class that we're looking at. Later on when we study in details, there's really only yes or no, so it's binary, okay, in terms of its outcome. So there are further description here of the so-called data field itself. I'm going to leave that for you to actually explore that yourself. There are a whole lot of other information that you can actually browse through. These are really rich information, as you can tell. There's job involvements, job level, job satisfaction, there are text data, there's numerical data, there's binary data, and all of it. So this is as real world as you're going to get when you actually start working with data real world problem. So let's dig into it. We just start with exploratory data analysis. Looking at the shape of the data, it's not really a big data set. It's 1,470 rows with 35 columns. Looking at the information itself, integer 64 means this is an integer. You have object, which means that it's pretty much string. Again, these are pretty much the two types. You have integer 64 as well as object. This is to display the first so-called row of data. This is one way to, again, get familiar with the data that you're working with. You can see that the first row of data, the gentleman, or I'm presuming it's a gentleman, or the first employee is 41 in age. There's attrition, meaning this person has left. He rarely travels. Daily rate, which means his pay is 1102. He comes from the sales department. How far from home does he live? 1, 2, or all the way to 5. His education level, the education field, or the her first, I suppose, bachelor degree is from life sciences. He is employee number 1. How satisfied is he from his environment? Oh, it turns out it's a female. Hourly rate is that, and on it goes. Okay, so these are really rich information to actually give you, without telling you who it is, but give you enough in terms of features for you to work with to build your model. The second thing that we want to actually just extract very quickly is to look for any null, or not a number, any data errors that we need to actually clean up. Fortunately, this data is cleaned. It's already been tidy for you to work with. The next step then is to actually look at the data. You can actually look at it from here, or alternatively, you can actually display in pandas. The slight difference here is that I need to actually allow the pandas or tell pandas to show more columns of data, which is why I actually have display maximum columns and basically increase it to 500 and the width increased to 1,000. This allows me to actually scroll across to see all the data. Now this is describe. Describe only work with numerical data, so it automatically ignores all of the categorical data. And what you have here is that for each of these columns, it performs some really basic summary statistics. For the age, you can see that you have 1,400 entries. The mean age is around 37. The standard deviation, youngest is 18, oldest is 60, the median is 36. And then you have the daily rate of the individuals going as low as 102 per day all the way to 1,500. Distance from home, presumably this is 1K to all the ways to 29K. Education range from 1 to 5. Employee count, I think this is actually basically telling you whether this gentleman is employee or not. So, but they are all one. So I guess if you look at this, the mean is 1, the lowest is 1, the highest is 1. So that means it's everything is just 1. So I will presume that they have another so-called data dictionary describing 1 is employee and maybe another so-called number or integer to denote that this might be a contractor or some other information. But I don't have that information available, so that's all that I can deduce from that. The other thing is that this is rather useless for building any model, because it doesn't contain any information, because every single one of the entry is actually 1. So this is probably one column that I will just drop and forget it, because it's just chewing up my memory and my computational power. Employee number range from 1 to 2068. These are just basically how many employees that they have. First one is 1, second one is 2, all the way to 2068. Again, very little information here. It's just gradually increase. It doesn't mean anything. Environment satisfaction is that, hourly rate is that, their job involvement, satisfaction, monthly income, the monthly rate, number of companies worked before, percentage salary hike, the performance rating, and if you look at the standard hours, you can see that again it's 80 for everyone. How do I tell? Because the lowest is 80, the highest is 80, mean is 80. Not the only way they're going to achieve that is if everything is 80. At 25th percentile is 80, at the 75th, at the 50% percentile, they're all 80. So that essentially means that that column of data, it can also be dropped as well. There are other information such as how many working years they've been with the institution, training, how many times they went for training, the work-life balance, years of company, years in current role. You can see that these two columns, years at company and years in current role, is almost correlated to a large extent, but it's not always true. Number of years since last promotion, it's also available here, and years with current manager is also provided here. So I've summarized here is that just by looking at that, looking through it, studying it carefully, applying really basic understanding and looking at the data, you can see that there are 3 columns that you will not include in your modeling, because it just contains very little information. So hence I have these 3 provided here. Right, I have these 4 lines of code. First one is that we want to obtain all of the names of the columns, but they are numerical columns. So we're using describe, which is this portion here, and because describe only works with numerical data, so it automatically already narrowed down to the numerical columns, columns with numerical data. So doing this list and with this dot here, basically extracting the names of the column, that's the first thing, and the second thing is converting it to a list. And for the categorical, what we are doing here is that we again extract the column names. This time the difference is that I'm extracting the column names for the whole data set, and I'm calculating the difference between the numerical column, which is here, provided here, versus all the columns, and I'm calculating the difference. I'm using a set functions here. Basically this is saying I have 35 columns. I have maybe 26 columns that's numerical in nature. Tell me the difference between them. Okay, so that's really tell me the difference, meaning list down all the names, and then I'm converting it to a list as well. From here, I want to remove these 3 which are highlighted here, and that's really taking these out from the numerical column. So that's what this function is. Okay, so running that, that's completed. The next one is this is another way to identify categorical columns. You'll recall that when we look at this earlier, .info, which is this one here, there is a label here called object. You can actually loop through all of these, and for those that actually the data type is object, you can actually save them or park them in a separate category altogether. So hence I've created an empty list, and then for each iterate through the items. If the data type happens to be an object, then append the name of it to this categorical underscore column, which is this one here. And when we print it out, these are the 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. These are the 9 columns that's categorical in nature. So if I can print all of these in terms of the length, how many columns there are, we have 26 numerical columns. The length of all of the numericals, but removing the 3 here, gives us 23, and then the categorical is 9, so 26 plus 9 bring us back to the 35. The shape, there you go, 35 that we have originally. So we accounted for all the columns, we haven't left out any one of them. But when we actually start modeling, we're really only looking at these two. So we have 3 that we left out, so 23 is what we're looking at, 9 is what we are interested in as well. Okay, so the next step of the process is to look at the relationship or correlation between the columns. Now, the last thing that you want to do is to have your columns of data having really close correlation with each other, and that will create a fairly unstable coefficient or unstable model that you build. So one way to deal with that is to actually study the correlation and just to actually get a basic understanding of it. So we can actually do it this way, just using the pandas.corr, which stands for correlation. The only thing is that this is rather hard to read because it's all numbers and there's so many columns, 23 of them in fact. So one way is to actually just visualize it this way using the Seaborn's heat map. Then you can actually see. Again, there's a bit too much data here. Of course, as we know for correlation along the diagonal, it's always going to be 1 because it's a correlation between itself. The upper half is going to be the same as the lower half. So one way is to actually remove that altogether. Hence, I've created a mask which basically make 0, and the beauty of Seaborn is that you can actually provide a mask to actually remove the top half, which is what this is about. And when you look at this, it's actually a lot better. Anything that's really deep red is what you call close or high with high correlation coefficient value, which is what we have here. What I would prefer though is that I want to see the numbers, okay, because this is a rather broad scale and I can't really tell how high is high. 0.24 from my perspective is not really high. So I've created, again, only showing the lower half. I've changed the light in terms of the color platelet, and also wanted to show the annotate as well with the values. So running this, and I get this. It's a bit small. You should be able to see it from the notebook itself. I'm not too sure if you can see it on your screen. It really depends on the so-called it depends on a few factors, your monitor and also your internet streaming speed and the platform itself as well. But I'll highlight those that I am interested in to look at. Recall that for correlation coefficient, -1 means is perfectly negatively correlated. 0 means they are independent of each other. If it is 1, then are perfectly correlated with each other. So in this case, everything is positive from 0 all the way to 1. Well, close to 0 anyway. It's not always, it's not 100% always positive. So since the correlation coefficient range from -1 all the way to +1. So what I'm interested in is to look at the value. You have a 0.95 here, so this is really high. 0.68 is close to being high. 0.78 is high. 0.77 is high. There's a few more that's 0.7 and above. And the observation that I have is that are these. Monthly income and job level are really closely correlated. Job level as well as monthly income, which makes sense. Okay, the type of and the nature of your job, will demand a different salary. So the other things that I actually can study and bring out some of the information is the number of years that you work and your job level, the number of years that you have work, and also your monthly income. your performance rating as well as your percentage salary hike. They're closely correlated to each other, which makes sense. The number of years in current role and the years in company, years with current manager as well as years at company as well as current role. These are all really closely correlated, which you can actually tell from the correlation coefficient itself. Right now, I'm not going to do anything with this information to sharpen up your machine learning model. You can actually take this into account. None of these really warrant my attention, with the exception of this one item here. For now, I'm going to leave that and not be too concerned by that. Right, so this is categorical that we looked at earlier, and this is also categorical we looked at earlier. And remember that we actually did it two ways. One is that we use set function and look at the difference. The other way is to loop through and look at the data type. And if you compare the two, they're exactly the same. Although the sequencing is a bit different, they are exactly the same. Right, the next thing is I do want to look at our attrition. If I look at the unique values, that's all the unique values that's in that column, it's only yes and no. Now, for the machine learning model to make sense of the data that you have, you cannot work. It doesn't work well with string data, or characters. So we need to actually convert it to integer, which is what we did here. Just basic mapping altogether. Right, having done all the preparation up to this point, the next step then is that there are still a lot of information that's contained within the categorical data. So what we want to do is that for the categorical data, we will actually convert them into a format that the machine algorithm can actually make use of. There are two ways to do this. One is actually what's called one-hot encoding, which we have covered previously under data preprocessing, as well as label encoder. Now, the label encoding is not so suitable for this case. The reason being is that the label encoder will convert the string or the text into sequential numbers, meaning 1, 2, 3, 4 all the way to 10, assuming that you have 10 different types of entries or unique values in there. So the one-hot encoding then is more suitable ways of encoding your text into something that the machine learning algorithm can actually utilize. So just a couple of points to note. We need to perform what's called the one-hot encoding before we conduct the train test split. So this is fine as long as you are transforming the data. It's not going to create what we call a data leakage. And when you perform data processing, you perform it after the train test split, because when you actually utilize some of the min-max, the standardization that we looked at previously, because the algorithm or the method such as standardization as well as min-max, what it does is that it look at the data and compute mean and standard deviation to transform the data. In those cases, what you want to do is that you don't want to allow any leakage to go over, so you will actually split the train test, learn or fit and transform your data with the training set, and then apply the transformation to the test. Never, you don't actually do the fitting inclusive of the test data. Okay, with that out of the way, let's have a look at the categorical columns that we're looking at. So you can see here there's 9. Attrition is really not a categorical value, so we need to actually remove that. So having done the remove, notice that it's gone. And the next step then is to actually conduct what we call get dummies. Literally is the one-hot encoding using the pandas library. If we look at this, just show you the first 5 rows of data, you will notice that it has been completely one-hot encoded. Okay, one-hot encoded, all you have is 0101 all the way through. And having done that, because the df underscore categorical or cat here is standalone, what we want to do is combine that with our numerical column, and this is how you do it using pandas.concatenation along axis 1. And if you look at the first 5 row data, you have your numerical data. These are all the numerical data, and up to this point, then the rest from here onwards are all one-hot encoding. Ideally, you do one more steps of standardizing your data, meaning try to center it around 0, 1. But for now, I'm gonna leave that. This is just really the first run of it, just to actually help you get used to the actual process flow. Now the attrition has been converted to numerical data, hence it's all 0 and 1. If we look at the value, notice that the actual data is actually rather unbalanced. This is one thing you need to keep in mind. Again, with this project, we're not going to account for that. So I've just illustrated to you so far there are 2 or 3 areas that you can improve upon with this project. So I'm going to give you a baseline in terms of the real skeleton of going through this whole workflow. See if you can actually improve upon that utilizing some of the techniques that we cover in this course. The next thing is I want to look at the X, our feature data, and go through them just to make sure there are no object there, object being string, otherwise it will throw an error. Everything is fine. Notice that from its integer 64 until this point onwards is actually integer 8. These are the 101010 one hot encoded information. Alright, having done all that preparation, the next step then is to actually start building our decision tree. This part you should be very familiar with. There's no deviation from what we've done from the previous lesson. So we perform our train test split, we import our decision tree classifier, instantiate it, fit our data, followed by importing the matrix, and then perform the prediction. Within the training data, you can see the accuracy score is 100%, which is really, really good. And if you look at the confusion matrix, there's absolutely no error there. And if you look at, however, the test data, you notice that, well, not so good. From 100% dropped down to 77%. And there's some issues with our model that we can actually work on to improve upon it. The confusion matrix shows you that there are some error, and notice that it is quite an unbalanced data as well. So that's something to keep in mind. And last thing that I want to show you is that if you look at the training data, you can see that it's 100%. And if you look at the so-called test data, it drops down to 77. And in fact, the ROC is actually only 60%, which is substantially lower than 100%. You will recall that 0.5 is basically 50-50, meaning it's actually kind of like a dummy model. So this isn't that much better than a dummy model. It's marginally better, but there are some issues in it. And you can see the precision and recall for identifying 0 is really, really low. Right, with that, I'm going to stop. Thank you for watching. I look forward to seeing you in the next lesson. Welcome back, everyone. In this session, we are going to go into utilizing what's called Collaborate, provided by Google. This is a deviation from using Jupyter Notebook that we've done so far. The Jupyter Notebook that we've used so far are all run based on your laptop or your desktop, basically using your local machines. There are pluses and minuses in doing that. The plus side is that it's on the go. You can actually run it anywhere with or without internet access. But you're going to come into a problem when you actually have issues in the sense of computational power or storage space or things of that like. So I want to actually introduce you to Collaborate. This is an opportune time to actually introduce this because a couple of reasons. One is that the so-called platform has matured substantially over the last few years. The deep learning library as well as the framework as provided by Google in the form of TensorFlow as well as Keras has matured substantially over the last 2 to 3 years. And the other additional benefits of using Collaborate is that the Google itself has provided computational power that you will not have access to as an individual. GPU, maybe, okay, you can buy it and use it on your laptop or your desktop. However, something like TPU is not something that you can actually buy. Google doesn't actually sell that at all right now to the marketplace. So to illustrate this, we're going to make use of the project HR that we have just looked at earlier. And I'm going to connect more apps just to show this to you, because you have not collaboratory. So basically that's how you actually spell it. So this is Google Collaboratory. Okay, so you just need to actually search for it, connect, and once it actually is available, it's connected, then you can actually click this and run this or on your browsers. So literally you don't actually need anything else except your browser and connection to the internet. Right, so let's wait for that to actually get set up. Yeah, so this is the part that you do need the internet, so give it a short while for it to actually get up to speed. Right, hopefully this should look somewhat familiar as well as somewhat unfamiliar to you. Somewhat familiar because this is actually Jupyter Note. Somewhat unfamiliar because the layout, it's a tad different. Okay, so I wanted to introduce this to you just so that you can actually start to get comfortable with this. As we proceed more and more in this course, we will start utilizing Collaborate more and more, simply because, well, number one, my MacBook Pro it's going to take a long time to actually perform grid search, cross-validation, and to some of the more computational intensive algorithms such as XGBoost and Ensemble. It's just going to take too long using my local machines. Likewise, when we start going to deep learning, it's just going to take too long, which is why I want to actually introduce you until you get familiar with Jupyter Note up front first, and because it's so easy to run it on your local network, on your local machine, so it makes sense to use your Jupyter Notebook on your local machines. But now when it comes to computational intensive portion, I don't want you to be sitting there for 3 hours while your deep learning algorithm is being trained. So that's really some of the basic fundamentals that I want to cover with you and don't be too concerned really, because this is actually very similar to Jupyter Notes. It's just layout somewhat different. Alright, the first thing is that we need to choose a runtime. So come to runtime and change the runtime type and select a GPU hardware accelerator. I mentioned before, this is non-GPU and TPU. You have access to this for free, absolutely free. Okay, and Google has provided it to you for free. I don't know how long they're going to do this for, but as long as it's there, make use of it, because it really makes your life so much easier when you're actually doing your training. Okay, so having done all that, the next part then is to run through the codes. And I'm not going to run through the codes as much as I did in the previous lesson, simply because the codes are exactly the same. I will highlight to you the variation. So we're just going to run these two, importing the libraries as well as print the version. The version will be slightly different from the local machines, depending on what you actually have what you have installed on your local machines. And the other added benefit of using Collaborate is that they really have incorporated a lot of the packages and libraries. The pain that you suffer when you actually have to learn how to import your packages on your local environment, how to install them, you don't actually have to do it mostly. Okay, I say mostly because there may be some that you do need to install, but so far I haven't encountered them myself. Okay, right, the next thing then is that you do need to install the file or download the actual data file. For that, this is the portion that will be a little bit different from the local machines. Okay, for a start, we need this line of code from google.colab import files, and upload files is equal to files.upload. So we run that, it pops up with this choose file, so we just need to actually run that again. wait for the server to run. Okay, now it's asking me to choose a file. On my local station, meaning on my desktop, within my data folder, I have this CSV file, which is the one that I'm going to make use of for the purpose of this study, which is actually the same file as the one that we used earlier. So let me zoom out. I'll try to zoom out. Okay, so saving now is actually saved onto the local server. Okay, so let me just add a cell and just ls, and you will notice that there's actually one folder here called sample_data, and this is the file that we've uploaded from our local desktop onto the server. We need that because the browser can't read directly from your local desktop. It's as a protection mechanism. So the next thing then is exactly the same as everything that we've done, which is pandas.readcsv. You specify the file name, and then you can view the header, and you run them as you go. So you can look at the shape, look at the data, look for the now. This is the describe, is exactly the same. There's no change there. And when we run each and every one of these code, it will operate as per normal when you're running it on your local station. And we can also run the Seaborn, as you can see here. All right, everything is exactly the same. There are no difference whatsoever. So you can also see the number comes up exactly the same. We can actually perform the data preparation, further preparation, now one-hot encoding, and finally we are at the stage where we can actually perform our decision tree modeling. So you can actually run these cells, and you'll notice that the actual computation is quite fast, although it's probably not discernibly different from your local machine, partially because the file, the dataset is not very big. But as you proceed, when we start working with 10,000, 100,000, 300,000 rows of data, or really starting to look at 500,000, 1 million rows of data, then you will see the marked difference between running it on your local machine as well as running it on the Google Collaborate. Okay, so that's really the very brief introduction on how to actually run Collaborate, and just want to actually break down the barriers so that you can actually start utilizing this. This is probably the one line of code that is different, plus this, but this is just to list all the files in the directory. This is to actually show you how you upload. You do need to upload your data file for it to actually be able to basically unpack the CSV file for the training of your algorithm. With that, I'm going to stop. Thank you once again for watching, and I look forward to seeing you in the next lesson. Good day, everyone. In this segment, we're going to go into ensemble learning methods. Let's start with the first lecture, which is on the introduction of this very unique methods which combine multiple machine learning models together. Now, the file can be accessed from the share folder, and basically I will provide you with the links on how to access this. Starting with this is that it's on the ensemble learning methods. It's really based on supervised learning, and the idea here is that you use a group of predictors. Can be classifiers, can be regressors. The ultimate aim here is to combine many different types of machine learning models so that they each complement each other. So the ensemble methods here, there are a few types. There is the first type, which is called bootstrap aggregation, more commonly known as bagging. Bootstrap sampling really is what we call sampling with replacements. Replacements basically means that the samples that you've used to perform your training get placed back into the whole pool before you draw another sample out. How this works is that it combined by averaging the output. This is for the regressors, or combined by voting. This is in the case of classification. So this is really how bagging actually works. Now this can be applied to many classifiers, which includes ANN, which is artificial neural network. We've also looked at CARD, which is decision tree really. So that's bootstrap aggregating or bagging. The second clusters is sampling without replacement. This is called pasting. For all these, I've provided the links, so you can actually click and come over to understand and study more should that interest you. Now, boosting is to train weak classifiers. What happens is that you add them to a final strong classifier by weighting. Now, the weighting is by accuracy typically. Once you've added, the data is then re-weighted again and again and again. The misclassified samples will gain more weight. The correctly classified samples will lose weight. There are some exceptions, but the essential idea here is that where we make mistakes, much like how humans learn, where we actually aren't strong in, or there's certain so-called topics that we're not good at, it will place more weight there so that the algorithm keep learning or place more emphasis on learning that portion. So the essence here really is that the algorithm are forced to learn more from the misclassified samples. So that's really boosting or boosting. The next one is called stacking. It's also called stacked generalization. Now from Kaggle, the definition comes this way. Combine information from multiple predictive models to generate a new model. So it's again, that's why it's called ensemble, because you're combining multiple of them. Oftentimes when the stacked model, also called second level model, will outperform each of the individual models due to its smoothing nature and ability to highlight each base models where it performs best and discredit each base model where it performs poorly. For this reason, stacking is most effective when the base models are significantly different. Training a learning algorithm to combine the predictions of several other learning algorithms. Now, step one is really train your normal machine learning algorithm just like usual. Then you actually have a step 2 here, which is called the combiner algo. Is trained using algo predictions from step 1. So it's actually hence the term stacked. There are other ensemble methods. There's Bayes, optimal classifier, there's Bayesian parameter averaging, model combining, and bucket of models. I also releases a few others. There's one final part that I want to highlight is that ensemble methods works best with independent predictors. If they're all the same, then there's really not much value to it. It's a little bit of diversification effect here. And it's best to utilize different algorithms to get the most out of ensemble methods. Welcome back. Let's dive in and look at ensemble methods 2, the bagging method. So let's open up our Google Collaboratory and wait for that to run. Okay, now that it's up and running, the first thing that you want to do is actually change your runtime type. Yes, I've set it as GPU. So remember bagging, what bagging is about. The idea here is bootstrapping, basically sampling with replacements, and we combine by either voting or averaging the output. Right, we're going to make use of the Titanic data for this. The usual is that we import the NumPy, Seaborn, and Pandas, and as well as Matplotlib. And we're going to make use of the Titanic database or datasets that is in that comes shipped with Seaborn, which is we call SNS here. And looking at the data, you have 991 rows, and 15 of it is the 15 columns or 15 features. Okay, so the data comes through like this. You have the survived or not survived, and you have the passenger class 1, 2, 3. You have the gender, and on it goes. We're gonna drop all of the not a number, and let's have a look at the unique class. It comes in the form in terms of the 3 value 1, 2, and 3. If we look at the value counts for each of these classes, it's actually heavily skewed. towards the 1, class 1. And if you look at 2 and 3, they are substantially smaller in terms of its what do you call it, representation. So this is a very skewed data set, and it seems like when we actually have dropped the not a number, what you actually get is that, well, the size of the data shrunk significantly, from 891 down to roughly 170, 182. That's okay. Really, for the instruction or learning purpose, that's fine for this. Essentially, what we want to do is just understand the bagging machine learning algorithm and the process. When we actually start looking at the exercise itself, that's when we actually start to look at a little bit more in depth or utilize a larger data set. And notice that these NaN, not a number, will get dropped from this drop NA exercise here. And if we look at the gender, it's likely to be fairly balanced, as you can see. And if you look at the age distribution, from really young newborn all the way to 80 years old as well. Doing a bit of data pre-processing here. Remember P-class, what do you call it, the gender as well as the age. Okay, so we just need to convert the sex or the gender to 0 and 1. The class, we also want to actually just looking at these specific 3 columns rather than looking at all the data. So if we look at the first 5 rows, and what you can see is that you have the P class, the gender, as well as the age. And finally, if we're looking at the shape, we have 182 rows of data. And if we run the describe, and this is actually what you see. Now, because I'm running on the cloud here using the Google compute power, what I will do as a slight deviation is to actually remove this drop NA. Ultimately, in terms of our model, we are really interested in just building our model with only 3 columns of data. So let me run this again. We have the data. Okay, let's load the data. This part won't take very long. We're gonna just have the P class, the sex, as well as the age. We only need to transform the gender to 0 and 1. And now we have 800 over, 891. And looking at the described simple stats, you have 1, 2, 3, and then the gender is 0 and 1, and finally the age is the final factor here. So looking at this, it'll be interesting to see what is the outcome. So we've tidied up our data. We have X, which is represented by the passenger class, their gender, as well as the age. These are the only 3 features that we are utilizing. And in terms of the target, it's just we extract it from survive. We should really copy this so that we don't actually get any errors. Right, so we are looking at the decision tree classifier, and we are using from the ensemble library, we are importing baggage classifier or bagging classifier. Of course, we're using our train test split, and we're keeping 30% for testing. And this is the so-called simple procedures that I've written. Basically, we have the pre-processing, cross-val score, cross-val predict, accuracy score, as well as the classification report, confusion matrix, as well as the ROC, area under the curve. And essentially, this little simple procedure here is just really taking the classifier. We need the train test for XY, as well as whether the actual training data, we are looking at the training data or the test data. Okay, so right now default it is training data. What we've done here is that we basically have a binarizer for the Y train. Y train is this is 0 and 1, so this is not too major, assuming that it comes in the form of yes and no. And then we actually perform the prediction. we print all of the relevant performance matrix and look at the average score in terms of the average accuracy as well as the standard deviation. We are performing 10 cross validation. And if it's false, meaning we are looking at the test performance, we perform the same as well. This is I've written this little simple function here just so that we can actually quickly test out rather than having to rewrite everything again and again. We just want to actually put in our classifier. It could be logistic regression, it could be decision tree, just so that we can actually quickly see the performance. So this is the instantiation of it, and what do we get? Input contains not a number. Okay, so we do need to actually, now that we have copied this X-shaped X head, what we can do is that at this very point we can add X dropped NA. Okay, so X is equal to X drop NA. So instead of dropping it up front, which is over here, we drop it a little later, and this should actually allow us with a little bit more data. Let's have a look. Yep, we've dropped the NA, the now, not a number, and it should actually allow us to run this now. Okay, we're still getting another error, still have the infinity type. Let's see. Inputs contain not a number. Why is that? The not a number comes in here. Found input variables with inconsistent. Okay, so let's... Oh, that's because we drop X without dropping the Y. Let's come back here. Okay, let's add a code. We call this a subset is equal to df, and we have the p class, and then we have the gender, and then we have the age, and then one more thing we need is the survive. I believe it's down here. It's called survived. Yep, survived. Okay, so the subset, we need to copy this. And then the next thing is from the subset, we need to actually drop the NA in place. It's equal to true. Key error. Okay, we need this one more column. That should be fine now. Okay. Now, having done that, having actually dropped that, we need the subset data. Copy that to our X, and then perform these pre-processing, and yep, this is not df, we should actually use subset. Okay, so our X should be fine now. Yep, tidied up, and our shape is 714. Good. And info, and we no longer need this line of code. We need to copy the Y from the subset survived, and we look at our value counts. This should be 714, which is the same as the 714. Right, having done that preparation, let's see how this works out. There's no more errors. Okay, so if we now run our code again, and on the classifier using decision tree, there's no more errors. And if we run the so-called score, looking at both the train as well as the test, looking at the train score, the accuracy is 91.58. The area under the curve, or ROC, is 90.44. The accuracy is actually 80% with a range. Fairly tight range. The accuracy score comes out at 80.47. And if we look at the train, okay, let's we do need to actually print new line, and let's use this as a separator. Otherwise, it's kind of hard to tell. There we go. That's much better. Okay, accuracy score 91.58, and in the test it dropped. If you look at the classification report, this is precision and recall under the train seems to be reasonable. For 1 is much better, but the recall is lower. The coefficient matrix is that the ROC is 90.44. It drops quite substantially when you actually look at the test score. That's the first step. The second step is if we look at the out of bag score is equal to 0. Now the question that you might have is, what does out of bag mean? So let me just out of bag machine learning, just to illustrate this basic concept for you. Out of bag error, also called out of bag estimate. Now this is a method of measuring the prediction error of random forest, boosted decision tree, or other machine learning method using what's called bagging, which is what we are doing here. And now out of bag is the mean prediction error on each training samples using only the trees that did not have their bootstrap sample. Okay, so hopefully that actually gives you a rough idea of what out of bag actually means. Now, having prepared that, we can perform the fit now and look at the score. Again, we should really have that line of code. Let me just come back here and just copy this. Too lazy to retype that. Okay, so now we have the separation. So the training score in terms of accuracy is 91.58. It also dropped once again under the test score. If you're looking at the ROC, it's 90.44 and 78.75. What happens if we actually use OOB score is equal to true? So that means we use out of bag samples to estimate the generalization accuracy of our model, machine learning model. So let's run this. We set the OOB score to true, whereas before we have the we didn't set OOB, so it's by default is equal to false. How do you tell? Here you have the OOB score is equal to true. If we come back here, you will see that the OOB score is equal to false by default. Right, so let's look at the OOB score. It's 80, so that gives us a perspective how likely that it will perform. In the real world, it's about 80% in terms of the accuracy. So, and the training is 95.58. The accuracy is 80, as we have extracted from the earlier exercise. ROC area under the curve is 90, and that drops down to 78.75 when you're looking at the actual test data. Now, let me just summarize this really quickly. So, what we have done is the bootstrap aggregating or bagging. Remember that this is a sampling with replacement, and what we have done slightly differently from using purely tree method is that this is actually doing multiple sampling of the data. So let's just say you have 100 data. Each time you take 10 and you perform training of your model. And after that, you're actually combining it by using voting for classification. This way, what you've done is that you actually continuously allow your model to be trained to actually learn and continue to be improved as you actually perform more and more and basically sampling. Just two last points that I want to actually highlight just to wrap up this session. First thing about bagging. We mentioned that bagging is really a method to actually A bagging, the whole method of bagging is what's called an ensemble meta estimator. It basically fits the classifier that we use. In our case, what we actually make use of is just a simple decision tree. And what it does is that it uses random subsets of the original data set and then combine it or aggregate their individual predictors to form what's called a final prediction. What this meta estimator or this so-called ensemble bagging method does is that it can be used in a way to reduce the variance of the underlying estimator itself because of the randomization that was introduced by sampling without replacement or sampling with replacement. It doesn't matter. Both of those are just statistical method. The idea is because of the sampling part of it, it reduces the variance of a single decision tree or single random forest. That's what's powerful about the bagging classifier. Let me just again walk through the code in case that you've missed the steps that we've done. Now we imported the decision tree, okay, and we also imported the bagging classifier. So in terms of the decision tree, you can actually fit it, and you can actually basically calculate your usual performance. Okay, so that's the decision tree. You can make use of the bagging classifier and provide the so-called base estimator, in this case is the decision tree. And if we didn't provide the out of bag error or score, basically we set it as false, what we can do in terms of the generating a rough estimate of the how it will perform in a test environment, then we will actually have to run this here. This line of code, meaning asking or instructing the so-called running of the test, okay, on our actual estimator. Alternatively, you can actually do this without running this line of code, and that's the purpose of setting out of bag underscore score is equal to true. What this will do is actually it will estimate the accuracy when it is dealing with the test data. So that's what this OOB score will actually provide for you. It gives you the estimate without you having to run this whole line of code. Okay, so again, these are the three things I want to highlight. We've done the decision tree. We're using the bagging to actually get a more consistent performance estimate, and finally we use OOB or setting the OOB to actually get an estimate of the generalization accuracy, meaning out of sample, hence the test data. With that, I'm going to stop and thank you once again for watching. I hope that this lesson has been useful to you, both in terms of how we actually solve problem when we get stuck. Okay, earlier we had some issues in terms of the dropping the NA too early, leading to actually loss of a lot of the data. So the other alternative method is to actually drop it later, but you actually have to ensure that you are dropping it when you actually have both the whole data set without having the separate dropping of X and Y individually. Hence we actually got a fair bit of the error, but I want to actually keep that in the video so that you can actually see how the thought process, how you actually tackle these problems when you actually do encounter these problems yourself. With that, I'm going to stop. Thank you for watching. Welcome back, everyone. This time around, we're going to look at bagging machine learning algorithm, except that this time around, instead of looking at decision tree, we're going to look at this in the form of random forest and how you can actually apply this bagging in the form of random forest. The early portion is the same codes, so we're just going to run through these. I actually did make a mistake, so let me just change the runtime. Oh, well, they're still using GPU, so that's fine. So let me just continue running these codes. Okay, sunset. There's a typo here. Subset. Okay, that runs fine. So these are as before, so there's no change really. Okay, finally, we are at the random forest end of it. Okay, how does random forest works? We haven't really explained this. Random forest is really actually on its own is already an ensemble. It is an ensemble of decision trees. How it works is that it runs training via the bagging method, which is the repeated sampling with replacement, meaning once you actually have run the actual, if you've extracted the sample, you do all your test and modeling and you put it back again. The beauty of random forest is that it utilizes what's called uncorrelated trees. It look out for trees that are uncorrelated rather than correlated, and doing so gives it number one, diversification. Number two, it learns from specific features that is not or overlooked in another tree. And that's the beauty of random forest. And random forest sample both observations and features of training data, whereby bagging samples only observation at random. And decision trees select best features when splitting a node. So these are some of the key features of this. So let's just run these codes. We're importing random forest classifier. We also need to import the train test split as well. We're keeping 10% for testing. The rest of these are exactly the same as before. There's no variation here, so let me just run this. And let's run the classifier. We should really change the estimator to 100. And fit that. We can use the 100 quite easily because we're running on GPU. It makes it substantially faster. So let me just make sure that there is actually a clear separation here, so that it's easier to read. So running this, coming back here, so running the performance evaluation of the training as well as the test. Of course, the training is really for building our model, and the performance come back at 90.65%, and the ROC comes in at 89.56. If you look at the accuracy score in terms of the test, it comes through at 72%, which is a substantial drop. And if you look at the ROC, the drop is not as big, but it's still a substantial drop. It's still a drop. Now, what we've done here is just random forest and without actually choosing the best hyperparameter. We're going one step further this time around. We're just going to perform grid search to actually seek out the best parameters, hyperparameters that can generate the best result in terms of our machine learning model to see under what hyperparameter it will perform or provide the best predictions. And we're going to make use of pipeline to actually combine our steps together. Again, we create instantiate the random forest. These are the parameters that we're gonna get the grid search to identify what is actually the what will actually provide the best result. The 5 parameters we provide, and let it run in terms of the grid search and perform the actual fitting to identify the best combination. Now, this is the part whereby it's really good to actually have a GPU. If you don't have GPU, this process of grid search might take days. I still remember when I was running this on a simple PC, which is actually a desktop without GPU. It took easily 24 hours to run all of these. Of course, it's not a high end, although it's still an i7, but because it's running on CPU, it was really slow. In our case, we're running this on GPU. It doesn't actually take very long at all, and it's already done. And what this is actually telling us in terms of the best score is 81.92, and you can actually, from the grid search, tells us what is the best estimator that will actually generate this best score here. Bootstrap is true, class weight is none, Gini maximum depth is none, so we give it a lot of flexibility, and yeah, there's a few things that's actually provided there. So let me come back up here, because I really am a very lazy in terms of typing this. So I'll come back all the way down here and run this. The difference now is that we are using the grid search rather than the classifier that we provide earlier. So notice that we used the random forest classifier earlier. Now we're actually just purely feeding the grid search outcome, or the best parameter that it actually has identified, and run this and see what the outcome will come out as. So let's wait for it to run and see what the outcome is. I may speed up this part of the video so that you don't have to watch the paint dry. Welcome back. As you can see there, I got tired of waiting, so I switched over the TPU, and that's the beauty of using the Colab, that once you actually got tired of waiting and you realize that it's going to take a lot longer, switch it over the TPU so that you actually get a faster computation. So the accuracy score come out 86.76%, and the area under the curve is 85.5. So scrolling down, looking at the test score, the accuracy score has improved to 84.72. It's not too far removed from the 86.76 and 85.5 for the AOC. That is the beauty of running the grid search, so that you can actually find a much better hyperparameters and give you a better performance overall. Moving on to extra trees. What is extra tree ensemble? Random forest is actually built upon decision tree, and decision tree node splitting is usually based on Gini or entropy or some other algorithm. What extra tree is different is that it makes use of random threshold for each feature, unlike decision trees. So let's dig into the actual code itself and see how well it performs. Now, the beauty of this is that it is more or less very similar in terms of the process as we have done so far. And if you look at the performance of extra tree, 89.41 and 90% for test score, it turns out that it is actually better in terms of performance in comparison to the random forest. And because this is really because of the random threshold. And let's dig into it a little bit more. Let's see. Begging. Where's our extra tree? Okay, here you go. This is the extremely randomized tree, or extra tree. And the extremely randomized trees, randomness goes one step further in the way that splits are computed. In random forests, a random subset of candidates feature is used. But instead of looking for the most discriminative thresholds are drawn at random for each candidate feature, and the best of these randomly generated thresholds is picked as the splitting rule. Okay, so that's really the idea here, is that it goes to each and every single one of the features. This usually allows to reduce the variance of the model a bit more at the expense of slightly greater increase in bias. And this one of the beauty of extreme randomized tree is that because of the randomized nature of it, but it's targeting each feature on its own, and quite often you can actually get a better result than just purely random forest alone. With that, I'm going to stop, and thank you once again for watching. Welcome back, everyone. In this portion, we're going to go into another ensemble methods called Adder Boost. To begin with, we need to prepare our data. These are the steps that we've gone through previously, so I won't go through them in details. If you do want to understand how the pre-processing is done, please watch the video from previously. We also split our data to train and test, keeping 30% for testing. Right, having prepared all of that, we really want to actually come to the boosting part, which is to do with AdaBoost. That's the specific algorithm that we're working with. I've also provided a few links for you to actually look at. The idea of AdaBoost is that it combines several weak learners into a strong learner, and it trained predictors sequentially. Now, this is the portion which is both a strength and also a weakness. Because it trained the predictors sequentially, how it works is that it works like human learning. It learns from past mistakes by focusing more on difficult problems it did not get right in the first place. In machine learning language or speak, what it does is that it pays more attention to training instances that previously underfit. Okay, so that's really from a boosting point of view. Now, if we follow through with the scikit-learn documentation, how it works is that it fit a sequence of weak learners. It means models that are only slightly better than random guessing, such as small decision tree, on repeatedly modified version of the data. The predictions from all of them are then combined through a weighted majority vote to produce the final prediction. The data modification at each so-called boosting iterations consists of applying weights to each of the training samples. Now, initially, these weights are all set to equal. That means the average 1 over n here, depending on how many so-called learners that we have. If we have 10, then n is 10. So it's basically average. So the first step simply trains a weak learner on original data. Now, the successive iteration then is that the sample weights are individually modified, and the learning algorithm is reapplied to the reweighted data. So at each given step, those training examples that were incorrectly predicted by the boosted model induced at the previous step have their weights increased, whereas the weights that are decreased for those that were predicted correctly. So what we essentially are doing is that we're putting more weights on those that we got wrong, and those that we got right, we pay less attention to it. So as the iterations proceed, examples that are difficult to predict receive ever-increasing influence. Each subsequent weaker learner or weak learner is thereby forced to concentrate on the examples that are missed by the previous steps. So let's start with importing AdaBoost classifier from scikit-learn, the ensemble, and we're going to instantiate it with 100 estimators and then fit our data. So the algorithm is provided here, and these are the so-called hyperparameter that we just use the default value, learning rate 1, best estimator, we provide none. What I might do is that I'll set the random state to 42. It can be anything. The reason I want to actually set it as the same is so that when you're running this same algorithm, you're going to get the same result as me. That's really the point of having a random state. Right, so we're looking at the outcomes now. If you look at the accuracy score of the training set, you're looking at 92.13%, and the precision is pretty good. Recall is not so good for class 0. And if you look at the ROC area under the curve is 87.48, which isn't too bad, but if you look at the accuracy score plus the standard deviation, it is quite substantial. And you can see that it dropped when we actually come to the test result, and this is symptomatic of overfitting of our original data source. You can combine AdaBoost with random forest. Now, previously we did not specify the base estimator, as you recall. Let's come back here. This base estimator, we didn't actually provide anything, so it default to decision tree. So if we actually make use of random forest classifier, and you notice that the base estimator is set as random forest, and if we perform the training now, it will tell you what is our parameters that we provide. So let that run. Notice that our base estimator is now random forest, and the rest are actually kept at default, with the exception of n estimators being 100. Of course, if you want to improve this, you can perform the grid search as we did in the past. If you look at the result now, it's 95.28 and ROC is 90.3.2. Now, of course, as the test is really looking at the test result. how well does it perform with the test result. Okay, let's wait for a while for the result to come through. Looking at the recall, it's improved from previous, if I remember correctly, is 77%. So let's come up here. Yep, 77. It's substantially better now because random forest is actually a stronger estimator than a decision tree. So it's 94, 89, 96, 98 for both the precision as well as recall. So let's just wait for the result to come through. I might accelerate this portion because of the length of time it takes to train. Alright, welcome back. You can see that this result has come through. It's not too good. The accuracy score is 61.82 and the ROC is 60.11. Continuing on the theme of boosting, we want to look at gradient boosting now. Previously is zeta boost, now looking at gradient boosting as well as gradient boosting machine. This works for both regression as well as classification. Wikipedia says how it works is that it sequentially add predictors. Now each one correcting its predecessors, and you fit new predictor to the residual errors. If you compare this to AdaBoost, which alter the instant weights at every iteration, so therein lies the difference. One adds predictors, the other one actually changed the instant weights. Gradient boostings involve three specific elements. The loss function to be optimized. So that's really the functions we want to optimize to improve the problem. In the case of regression problems, it's mean square errors that's used, and in classification problems, logarithmic loss will be used. In boosting at this stage, unexplained loss from prior iterations will be optimized rather than starting from scratch. And weak learners to actually make predictions, and decision trees are used as a weak learner in gradient boosting. Additive model to add weak learners to minimize the loss functions. Now trees are added one at a time, and existing trees in the models are not changed. So the essence of gradient descent procedure is used to minimize the loss when adding the trees. So at each point that you add a tree, what we use what is called a gradient descent procedure to minimize the loss. So let's walk through an example. We first of all import the gradient boosting classifier, and we instantiate as well as fitting our data, just using the basic default value. And let's run in terms of the training and compare it to the test score. This runs really quickly. If you look at the result, the accuracy score isn't so ideal. It's around 50%, which is really low. Obviously, there's much more tuning that needs to be done. Now, these values here are from my own research previously, from the previous run that I had. I would encourage you to actually run your own tests, compare all the different types from decision trees to bagging to random forest, optimize random forest, which is where we have the grid search with cross-validation, extra trees, AdaBoost combined with a decision tree AdaBoost combined with random forest, and finally gradient boosting machines that we looked at in this portion. With that, I'm going to stop. Thank you once again for watching. Welcome back, everyone. This is an installation instruction video on how to install XGBoost. I'm just going to quickly highlight them. The links provided here are sufficient for you to actually follow through on how to install them. Installing in Windows tends to be a bit more tricky, but these instructions as provided here are sufficient to achieve that. You can, for Mac, it's fairly straightforward. It's just really using conda installation. Once you've installed them, you just run these codes to check that it is indeed correct. And this is part of the reason why I want to run this on Collaborate. The idea is that the whole team and Google already have installed all of these dependencies and packages and libraries for you. So your role in your job really is to focus on being a data scientist and just get on with it and building your machine learning model rather than having to worry about the engineering side of things. And as you can see here, I don't have to do anything. I just need to fire up this IPython notebook or Jupyter notebook, and off I go. with this one error, of course, that just have to pop out. Let me have a look through and see what the actual issues are. Positive or negative. Okay, right. Having done all that, the reason was that the sample size is actually just too small with 5 entries. Sometimes with 5 entries, what you get is that you get the problem of the so-called target variable, which is this binary target here. Could be that under your training, there's not enough representation of both the classes, or you have the same problem in the test classes. But usually where the flags out problem is within the actual training classes itself. So here it's basically highlighting some of the issues here, but if you really went back to our issues earlier, it's really because we have far too few so-called data point. Alright, so that's really a very quick introduction to XGBoost and on the installation side of things. Look forward to seeing you in the next video. Welcome back. In this segment, I'm going to look at extreme and gradient boosting. So this is really an extension from the boosting topic that we covered. XGBoost, for short for extreme gradient boosting, is very popular and in fact really stormed into the competition realm and the data science world around 3 years ago when it started winning all the competitions to come with it. There are a few documents here as well as the paper. I'll leave that for you to actually dive in. What is interesting about extreme gradient boosting relative to its predecessor, such as gradient boosting as well as EdaBoost, is really this objective function, where it combines both the training loss as well as the regularization, and that allows it to achieve, well, substantially more than its predecessor. The training loss, of course, is provides a guide on how predictive your model is and how well it generalizes when it starts to look at the test data. The regularization terms allow you to control. It gives you the lever to manage how flexible your model is. Okay, so and that basically gives you the freedom to increase the flexibility if you feel that it's underfitting, or reduce the flexibility if you find that it is overfitting. So just a quick comparison, summarized notes here. Specifically, XGBoost use a more regularized model formalization to control overfitting, which gives it a much better performance than gradient boosting machine. For model, it might be more suitable to be called as regularized gradient boosting. So let's dive into our Titanic that we worked on, and again I won't go through these because we've already gone through them many times. Just needed to run. Actually, what I should have done, let me just check my runtime. Okay, it is running on GPU. I'll just wait for that to wait for the thread to run. Okay, it is running well now. We've imported our libraries. This is the helper functions that I wrote. Okay, let's import XGBoost as XGB, and we're using maximum depth of 5 and 10,000 estimators with a learning rate of 0.3. These are default, just plug out this guy. Of course, you can actually use your gradient search, grid search, to identify the best combinations. For now, this is sufficient for us. So if you look at the so-called training score as it runs in the background, it's pretty good at 94.49. It's continuing to run, and this portion here, it allows me to actually get estimates of the average accuracy, because this is just one. Okay, and what I did basically when I was writing these is that I'm doing 10 CV or 10 cross validation. Because I now have 10 samples, I can calculate the mean, I can calculate the standard deviation, how well it's likely to perform out of sample. meaning test data. If you look at the average accuracy is 77, the standard deviation is 0.1. So then you can tell that there's quite a margin of error. So 80% or 0.8 is the accuracy score, which is within our average that we actually suspect is gonna be. And this is the comparison across the board. I didn't actually include XGBoost here, but it is an improvement. Of course, there are much more tuning required for XGBoost, and that's part of the nature of building your machine learning model, is the actual tuning part. Of course, your life will be so much easier now that there is GPU and also TPU. It speeds up the process substantially and reduce the waiting time for you. And that's it for this portion of the video. Thank you, and see you in the next lesson. Good day, everyone. In this segment, we're going to look at the project HR, and we're going to make use of the various algorithm that we've played with or have been explored ourselves in, and apply it to this IBM HR Analytics employee. And this is, of course, from Kaggle. Do have a read through. There are more information here for you to actually glance through. I know that we've touched on this before, so I'm going to go through this a little bit quickly. Now, one part of the data is that we do need to import the data. Let me just upload the file. This is obviously from your local station. It could be in your desktop, it could be sitting in the folder or thumb drive. Just make sure that it is available for you to upload as and when you're ready. So once you actually upload it to the server, then we can read into the memory, and we just need to do a few of tidying up, which we've shown you before, and also in terms of the converting some of the string into one-hot encoding. Right, the next portion then is to perform train test split, and we're going to import our decision tree classifier, instantiate it, and perform the actual fitting itself. And let's run our training and test. So this is the actual test here. It comes out at 79.35. Result is clearly not that satisfactory. We want to actually compare this to the ensemble method. So let's start with the, let me just delete that, accidentally added that line of code, bagging classifier. So the usual, we are using the classifier from before. Where is it from before, which is this one here. So we're using decision tree, and we actually name it CLF. So now we are actually using that as a base estimator for our bagging classifier. So let's conduct the fitting and then run the actual train and test to see our outcome. Now, this is the one part I do need you to remember. For our test score, original test score is 79.35. Let's see if bagging improves it. 79%. Okay, just remember that it's 79%. I need to remember that myself as well. Let me just jot it down. Okay, welcome back. Looking at this, you can see that for the test score, the accuracy score has improved to 82.61%. So originally we have our decision tree. After using bagging the process, it improved to 82.61. And what about if we actually use random forest as our classifier? So let's run random forest and run this again, train and test. Okay, so random forest on its own is already 84.24, better than the bagging of our classification or decision tree. Of course, we can actually view the importance in terms of the important features as set out by random forest. It does highlight the monthly income, age, total working years. These are the things that's important predictor when it comes to the likelihood of the staff attrition. Okay, so let's take it one step further and look at AdaBoost. And again, we're using just standard parameters. Okay, so there's nothing extremely different there. For this, you notice the average score for AdaBoost has improved to 86.96%. So it's an improvement over random forest. Now, what happens if we combine the two? So let me just run that while I explain what we did here. So we can use the boosting method, which is AdaBoost here, but using random forest as the classifier or base classifier, or base estimator, I should say. So looking at this, 84.51, there's no improvement over the AdaBoost on its own, which is AdaBoost with decision trees. So random forest plus AdaBoost didn't actually improve the performance at all. Of course, you shouldn't just look at this. You should look at the average accuracy plus the standard error, and to see if it actually is an improvement. 86.48 versus 86.48, so it's the same, but the difference, however, is that the standard deviation has dropped when you actually use a combination of AdaBoost and random forest. Though the accuracy did not improve, the margin of error in the form of standard deviation or volatility has gone down. Okay, so don't be despaired. So sometimes it pays to actually compare all the matrix that is generated. So now let's look at gradient boosting classifier. So let me run that, and while we explain a little bit of what we're actually running here. Base estimators, we use 100. Again, we're fitting it, and just look at the output here, 86.41. Marginal, it's around there. There isn't really a major improvement. But in terms of the accuracy, it's seemed to have improved to the AdaBoost plus random forest. I remember this is about there. This is 1.8 versus 1.4. So okay, it's about there. All right, there aren't actually much difference there. So next one is look at XGBoost. Now XGBoost does take a while to learn, so let me run those and come back here and explain a little bit. We're using 100 estimator. These are just very standard instantiating and fitting. And now let's look at the output. So with XGBoost is 85.87. No major improvement there.